will cause your great interest. Thank you.
Oh, Natalia, thank you very much for your brilliant open remarks. So, so gentlemen, let's go further. I should say that we are compressed in time. We have less than 3 hours for 5 reports. So I have a request to the speakers not to go beyond the time allotted to the report. If you can deliver a talk in 25 minutes, it will be very welcome. Anyway, so the first speaker is Professor Alexey Starobinsky. The title of his report is Present Status of Inflation, the Simplest Models and Expected Discoveries. Please, Alexey, 30 minutes.
Okay, how can I open my my screen?
Now you may share.
Okay, I open the file in my screen, but can you see my screen?
Not yet.
And how to? What should I press to? Or I see my screen in my computer, but I don't see it in your screen.
You should press the green button, screen demonstration.
Yes,
at the bottom of Zoom.
I press it, but I don't see any. Okay,
Yes, now it's it. Yes, now we can see your screen.
You can see my screen.
Yes.
Okay, well, let me open it. Okay, so thank the organizers for inviting me. Previous time I spoke at your series of conferences 4 years ago, and so okay, so what happened? During these 4 years? So once more, please inform me if you don't see my screen and my cursor. Do you see it?
Yes, I do.
Yeah.
Okay.
We see it. Yeah.
So the main change during these 4 years, that first we have much better observations. I shall mainly use the final results of the Planck hub observations. It was issued 2 years ago. Recently, a new experiment was made at the Gamma Cosmology Telescope, but still it appears only a month ago, so we still are thinking about it. So once more, I shall speak only about the Planck. And so really the statement is it will be the main statement from what follows from observational cosmology that can be also used for particle physics. The statement is that the all existing data about the very early state of the universe can be described using, in the simplest case, only one parametric inflationary models. So they use only one constant, which status is, I would say, the same as the fine structure, as the state use of a fine structure constant. It is not derived from any more fundamental theories taken only from experiments, in our case from observations. But of course we are prepared for future observations which may discover new constant, and so of course we have much more complicated model. But once more, at the present time, I shall show you one parametric model which in fact produce practically the same prediction formally the same. I shall explain in which sense. Okay, and so this is from observation. From the theory, we speak about small corrections to these models. In particular, I shall speak about quantum corrections. And from the absence of this correction, actually, it is expected we see really that this general hypothesis does work. So, okay, and still once more, in one way, in one point, I shall say you about possible discoveries, expected and not expected. And so in particular, is to show you that we are really prepared to some unusual things. I shall speak about this possibility, additional possibility to generate large peaks. And finally, the third thing which about we are thinking, we now understand that inflation as always it is unstable state. It's metastable, but it's an unstable state. No quantum system may live in an unstable state an infinite period of time. So something was before. At this moment, we don't have any observational data which would permit us to give a choice between different theoretical possibilities. But still, I shall list some. So something was still before inflation. And this is where a very compressed picture of what we know in the standard, I would say, in the standard model, cosmological model about the history of our universe. And this behavior, it's just this curve more or less presents the behavior of a scale factor. And you see that it is convex here and that is convex here. So during inflation and during the present state. And this means that at least the first stage and the fourth stage, the expansion of the universe is accelerated, and just the opposite, it is concave here at the hot Big Bang. So hot radiation dominant stage and hot method and cold, excuse me, and method dominated stage. And so in this second and third stage, the expansion of the universe was decelerated. Okay, so I shall mainly speak about inflation, but I say in a few words what might be before inflation. Okay, so inflation, once more, I shall speak about inflation in a narrow sense, in the sense of viable inflationary model, because sometimes it is used in a very broad sense, and this results in critics. So in the minimal variant of the inflationary scenario, once more, of viable models is based on actually not on one hypothesis, but on two independent hypotheses, or you may call them ideas. So, and once more, I emphasize the independent, and I shall explain in a minute why. So the first hypothesis is a hypothesis about the behavior of background. It's just the hypothesis of the very existence of inflation, or better to more exactly, more rigorously saying quasi-de Sitter stage, a stage of accelerated close to exponential expansion of our universe in the past, which preceded the hot Big Bang with decelerated polar expansion. And the second assumption is what is the origin of all inhomogeneities, because we are not interested only in the exactly homogeneous and azeotropic universe, where almost all interesting effects are connected with inhomogeneities. So what's the hypothesis about the origin of all inhomogeneities? It is the hypothesis that produced just from this effect, gravitational creation of pairs of particles, antiparticles, and field fluctuations in the course of inflation. So in the course of the stage which was assumed in the first hypothesis, from which initial state? From which initial state we cannot define that for all modes, so it is not an absolute vacuum. So, but what we can introduce is adiabatic vacuum, adiabatic no particle state for some range of Fourier modes, of spatial Fourier modes, not for arbitrary long modes, long wavelengths, for, as I said, for finite range of scales, but it covers all observable scales and actually and much beyond them. Okay, and so the second effect, notice very short notice, it's actually of the same type as particle creation, but in black holes. But fortunately, in our case, we don't have any problems with loss of information, firewalls, transporting energy, and so and so on. Actually, even making more compression, both assumptions can be combined into one. I just follow the way of presentation, which was actually in my paper in 1979. It's an assumption that some part of the world, speaking, so it may contain many universes, which includes all its presently observable part, was as much symmetric as possible during some period in the past. And when formulated in this form, you will really have an explanation of the error of time in our world. It is non-universal exponential because it is due to specific initial condition, but okay, it's work. So once more, this hypothesis, as compared to other alternative mode, I would say that for me, once more, of course, these are two hypotheses which have to be compared with observation data. It's where I should emphasize that where have analogies in the existing physics, so they are not completely opposite to what we see now. So the first hypothesis is actually based, though it was not initially, but now it can be presented in this way. It's also that substance which produces initial inflationary stage by its properties from the not quantitative but qualitative point of view is very similar to present dark energy. And so inflationary hypothesis may be formulated just in the form that we have something similar, that we have some primordial dark energy which qualitative properties were very similar to properties of a present dark energy. The only point, of course, I should honestly say that we assume much higher degree of metastability when we actually see that it existed for about 60 e-folds at least. For present dark energy, it was more or less similar to the cosmological constant, I would say, at least for 3 e-folds. And the second effect is it's just constructed in complete analogy to the effect of creation of electrons and positons in an external electric field, which I would say almost confirmed by experiment, not exactly. Okay. So what we have from this hypothesis, we have a prediction for something which we see here, and where really the most once more I shall it will be written a little bit be low, but I shall emphasize once more we assume that up to energies of inflation, the main properties of the present physics, namely Lorentz invariance and the absence of additional spatial dimensions still remain. Of course, once more, it's a hypothesis, but at present, my statement is at present we don't have any necessity to assume that Lorentz invariance was broken at these energies. I show you exactly at which energies and additional spatial dimensions, if they exist, they still gonna show themselves. And what we obtain, what we have to obtain from any concrete model. So the general property of all the inflationary models that we are predictable. We choose these initial conditions. Once more, it's not the absolutely all the initial conditions, but for sufficient amount of initial conditions, we have models, we have equations, and so we can make all predictions what we see now. Okay, and the most important other prediction about this perturbations which we actually see now from the fluctuations anisotropy and polarization of the cosmic microwave background. In particular, we can determine the structure, for the structure. So you see, I try to write this in this way. So isotropic spatial curvature is, if it exists, is included into monopole component of this perturbations. So that's why I can expand all spatial inhomogeneities into three-dimensional Fourier harmonics, and when we have power spectrum, so it's the square of the amplitude in the Fourier component, and we are interested in this quantity. We are interested in this slope defined in this way. Y-1, it's only for historical reasons. Actually, it was introduced initially by for some other quantities which will leads to -1. In this reiteration, it was introduced in one of the early papers by Jim Peebles, who has just got Nobel Prize for his contribution in cosmology. And also the generic prediction, it will be that this perturbation, they have trace component, which is scalar perturbation, and they have priceless and transverse component, and this is simply a normalization condition. And we're also interested in the prediction of this quantity. And non-trivial prediction of all viable inflationary models, because there exist many models which have been already studied by observation, that this quantity is small and at least of the order of this. So this quantity is small. This is the prediction of also, and this quantity is also small and no larger than no larger than first order in this small quantity, but actually it can be much smaller. It's another question in which I shall only mention, but I don't have time to speak it in more detail. Of course, this quantum effect is my second assumption is the quantum gravitational effect. So of course, magnetic perturbations are quantum even at present time, but it appears that after emitting a very small part of them, they become effectively classical but stochastic. So essentially, the prediction about the present space-time magnetic, but it is stochastic, and in the first approximation, it's Gaussian. And this is confirmed. But I just want to emphasize that all predictions are beyond semi-classical gravity. By semi-classical gravity, we mean the very approximate figure in which we have quantum net, and classical gravity, and the classical net is driven by the average value of the quantum energy momentum tensor. So no, they are all beyond this approximation, because in particular the prediction for the average value of all perturbations is 0, but the fact that the average value is 0 does not mean that the perturbations are absent. So it is, once more, it's a Gaussian quantity with 0 average value and non-zero dispersion. And this is the actual picture of the anisotropy. Of course, make microwave background, and typical deep depth of these oceans and typical height of these mountain ranges are of the order, relative order 10 in power -5, so about 30 microkelvin. And you see, as I said, we have this. That's why we mostly use this spectral expansion into multiples, and this is how this one parametric models, which I shall show you in a minute, just how well they actually fit this very complicated curve. And this is in case of temperature anisotropy. Then on the level of 10 in -6, so a few microkelvins, there appears only linear polarization. And this is the picture. You see how well it is also fitted with polarization. And non-trivial, also another non-trivial prediction is this polarization, like the traceless tensor on the sky, can be decomposed into a so-called E mode and B mode. And the non-trivial prediction is that primordial B mode is absent. It indeed also is confirmed, and the prediction we expect, but we expect with EB mode on the level below 10 and minus power minus 7. So we are now speaking about the effect that less than 1 microcarry. Okay, so you see in general how good is the prediction. So apart from possible deviations from here, that's a possible 10% effect, which is still not confirmed if it is really primordial, is for future. I shall mention it in possible future discoveries. But speaking about now translating this graphic information into numbers, I would say what we obtained from this experiment, from this the final general announcement of a Planck experiment, we obtained two new numbers, two new dimensional numbers, the amplitude of the spectrum, and this is square of the square of inhomogeneities of the universe. So it's a kind of generalized cosmic Newtonian potential divided by c squared, the velocity of light squared, all is squared. So okay, so this shows you. So what's more, in all models, and not only in inflationary models, actually in alternative models too, we have to take this number only from observations. So once more, at present, the status of a small number is the same as the status of fine structure constant. But also what is measured, the spectrum, this quantity is small. As I said, it is generic prediction of all inflationary model, but it's not simply small. We actually know its number. In S minus 1. Well, once more, it's not exactly constant. It's actually the prediction is a slowly changing function of a scale. Its average value of a range of scales in which it was measured, approximately from 1 megaparsecs to 10 to the power 4 megaparsecs. Okay, but once more, we are interested now in this number, and this is from the theoretical point of view. For me, it's the most remarkable achievement of the Planck experience, that we really know this number with good accuracy. As for the gravitational wave, we don't discover the primordial gravitational wave, and this is expected, and this is where it present upper limit, which in particular includes all, I will say now, naive scalar field models, in particular m² phi squared models. That model predicted the value of R at more than 2 times more. So it is certainly excluded. Okay, and so as I said, the fact that this quantity is simply small is the property of all viable inflationary models. But the fact that it is not simply small, but close to some another number, and I shall show you here. It's just gives us a possibility to choose a very narrow class of possible inflationary models. And the statement is that in any inflationary model, why this number should be taken only from observation, this can be predicted, and it was actually predicted more than 20 years before it was actually measured, and predicted in terms of which quantity. When we say that we are predicting some fundamental quantity, immediate question, in which terms? The answer is, and I would say it's a very non-trivial result, this refers to the properties of the inhomogeneities in the universe long time ago. It is predicted in terms of this quantity, which simply characterizes, in fact, how large is the present universe, because actually what happens here, what appears here is the Boltzmann constant, the present cosmic microwave background temperature T gamma, and H naught, Planck constant, H naught is the present Hubble constant. So okay, so once more, this concept shows how, in fact, it's characterized how large is the present universe. Of course, it's not a constant at all. It slowly changes with time as logarithm t, and this means that also this constant is not exactly constant. It's a slowly changing function of K. And up to small corrections, I shall show them later, up to 10% corrections, the prediction for this narrow class of models, which you can see, check by your own eyes without using a complicated computer program, is that models with quantity multiplied by this quantity is approximately 2. And really, to show you that this number 2 is which accuracy is needed, I would say that completely different variants of inflationary models will be viable if this constant will be over 1 or approximately 3. So the fact that it is just 2 and not 1 and not 3, really, it's very important. And so once more, just because I'm speaking about, and I'm addressing now in particular students or not specialists in the field, just because we may see in literature many, I would say, general and not very specific critics of inflation. That's why I would like to give you answers to these critics. And just because this critics is not, I would say, it's not very scientific. It's in popular terms. So my answers would be also only reliable. So one statement which you may find in the literature: inflation is not falsifiable and cannot predict anything. Reply: wrong statement. Any concrete, just the same situation is that with any models of any extensions or any extension of the standard model of elementary particle physics. Any concrete inflationary model is falsifiable much more. Most of the proposed models that have been already falsified, including the original 1981 model by Arthur. But fortunately, still some models exist which are still viable, including my pioneer 1980 model. Okay, about the predictive power, of course, the less is the number of parameters to be fixed by observations of remaining viable models, the larger is their predictive power. And once more, the present state of that, the most predictive models have only one free parameter. Okay, the second critic is the beginning of isotropic and homogeneous inflation requires extreme fine-tuning of pre-inflationary conditions. Reply: wrong. Intermediate inflation attractor is generic and inhomogeneous. It is approaches quasi-specific state only inside the Hubble it reduces. And simple answer that I would say inflation in that model, which I shall show you, is as generic as black holes in general relativity. So this does not mean, you know, of course, that black holes exist and we really discover them, but this does not mean that black holes are omnipresent. But still, it simply means that they exist somewhere, so you can find them. Okay, and final remark once more. It refers to the so-called eternal inflation, of the fact that inflation model generally predicts many, the so-called multiverse picture. Eternal inflation leads to multiverse in which no quantitative prediction can be made. Reply: it's not relevant, if not wrong at all, because irrespective of some problems with making prediction in this case, which are due to unjustified manipulations with conditional probabilities, eternal inflation still occurs outside our past and light and future light count. So it's an unfinished process which happens somewhere, I would say, in other space and other time. So it does not affect what we see in our universe up to first, up to small terms which are first exponentially small, and second, which was omitted in all previous quantitative considerations of eternal inflation, beginning actually from my 1986 paper. Okay, and so this simplest models produce this observed scalar slope. As I said, first is my original, a little bit simplified R plus R squared models, where R is the richest scalar. So it's modified. It's not Einstein gravity. It's modified gravity because this is Einstein gravity and this is modified. And we can use the first observational constant from which I measured to fix unambiguously this constant. So in this model, this appears new characteristic mass scale, energy scale of this order, and it's really an interesting scale because it's significantly less than unification scale. It produces the correct value of ns-1. You may compare. I wrote 35 here, so it's 36, and it has a definite, I will say, target prediction for the future possible discovery. And also, what is important is the first time that we really see that there was real, something very close to the singularity in the past of our universe. The statement is that there was, we see now the traces of a period where the curvature, the Hubble parameter was as high as this quantity. The same prediction follows also from the non-minimally coupled scalar field model with this asymptotically like Higgs-like potential and with strong non-minimal couplings. That's important.
Dear Professor, yeah, I'm very, very sorry to interrupt you. I just want to say to you,
yes.
only 5 minutes left. Yeah, please take it.
Okay. So I shall very shortly say you. Okay, and so the statement is that this model produces the same prediction. So okay, so I shall actually interested people can see from the whole my slide what other, but what I want to say to you. Okay, I shall show you why these two models, completely different models, produce the same result. It follows from the following fact that in this model, in this non-minimally coupled scalar field models with asymptotically Higgs-like potential, if psi is negative, is very large, then in the first approximation, only during inflation, you may emit this term. And when this appears, that can be called geometrization of a scalar, that the scalar phi is locked to the Ricci curvature. And so if you introduce, generically, it's not possible to introduce solutions into the action, but here during inflation it's possible. So if you do here, this model take this lock into account, this model just transforms into my R plus R squared model. So these two models, the Higgs inflation many models and R plus R squared model, and this is the reason why they produce the same results. Okay, but this lock suddenly breaks just after the end of inflation, and the real reason why it's called, because during inflation R is positive, but after inflation R becomes negative, and so this condition it cannot be satisfied. Okay, I think I shall stop here because you and let me only I think I still 2 or 3 minutes, and let me remind you so once more. Okay, still let me show you about because expected discoveries. So expected discoveries, as I said. Okay, sorry, let me only show you. No, it's not here. I skip it. Okay. So the most, I think, from the fundamental point of view, the most important expected discovery is primordial gravitational waves from inflation, and we have, I would say, a target prediction. So of course it may be falsified, but we have definite prediction in this one parametric mode that it was this quantity, and I think it's very good because in many other problems, in particular, we don't have any target prediction for the breaking of the supersymmetry scale. Okay. And then a more precise determination of NS-1, it gives us information about the duration of inflation and information about the properties of physics at least energies, and two features which are not contained in one-dimensional, in one parametric models. It's local non-smooth features in the power spectrum and local enhancement at the power spectrum of small scale. So it's possible to do. Once more, we don't have a present observational data, but if it appears, it will be proved that some of the black holes which we see now from gravitational wave antennas, if they are immortal, then in fact we are prepared, and we have several variants how to add more parameters to our inflation models, in particular, and this is the topic of my recent paper. So it's possible, but once more, it's not the expected prediction in the minimal one parametric model. And let me only finish with my conclusion. So we have confirmation of typical inflationary predictions that NS-1 is small, and of the order always quantity. Once more, it's the quantity which simply defines how large is the present universe, and the R does not exceed this quantity are confirmed. And then the interesting predictions for the elementary particle physics, that we have this characteristic mass scale 10 to 15 GeV. Once more, it follows only from observations, from the fact, and from how small are actually the present inhomogeneities of our universe. In the F over R gravity, we have definite prediction for this quantity. So it's, as I said, it represents a dynamical attractor. So in inflation, it's sufficiently generic. Then really, I don't have time. I only announce that I can consider different quantum corrections are considered, including running of constant are considered, and we don't see this effect. And this is expected. And finally, speaking about what may happen before inflation, there are several possibilities, including bounds, but one generic possibility is that before inflation there was something more inhomogeneous and something more anisotropic, a kind of space-like curvature assembly. Thank you.
Yeah, thank you very much. Okay, so I don't see any questions in chat. So
can I have a question? Sorry.
Okay.
Okay.
Can I ask?
Yes. Yes.
As I understand, during inflation, you have a huge velocity of inflation of expansion, much larger than speed of light. Yes. But we know that space is not empty. There are a lot of fluctuation of particles. Maybe there is contradiction between this because this fluctuation will have a huge velocity, much larger than speed of velocity of speed. What do you think about this?
First, I did not quite understand one of the statements in your question. No, I would say no. There is no all the velocities properly measured are much less than are less than velocity of light. So once more, I remind you that one of the actually the fundamental assumption was that the Lorentz invariance is not broken at the energies, just as I said, 5 magnitudes of order less than the Planck scale, and actually even up to 10 in power 14 G.
So expansion velocity is lower than velocity of light. Yes.
Once more, actually, if you are speaking about these perturbations, they actually do not in the so-called super Hubble region, they actually do not depend on time at all. So in some sense, you may consider them as aesthetic.
Okay, so we should finish soon. I just got one question in the chat. Maybe it will be the last question. So the question is, what observables from galaxy surveys could be relevant to constraint inflation theories?
Okay, it is just from galaxies where obtained where either speaking about our space, coordinate space, it's the relation functions or the power spectrum. So from the galaxy surveys we obtain, but the same information as we obtained from the cosmic microwave background, only from for a smaller scales. So speaking now of scales, let's say from 100 megaparsecs up to scales of say of even kiloparsecs, speaking about galaxy size. So essentially the same. So first, as I said, either correlation functions or it is Fourier transform power spectrum, or more complicated construction, the so-called B spectrum, T spectrum, and so on, which also gives us a possibility to check not only the spectrum of perturbation, but its statistic too. As I said, the statistic, the essential prediction actually following from the assumption that initial states for any Fourier mode was adiabatic vacuum, it follows what in the first approximation it's Gaussian, and up to only due to non-linearity of gravitational interaction. So there it contains some small corrections of the order of a square of this quantity. So inhomogeneities are also of the order of 10 in power minus 5. So of the order of 10 in minus power 10, 10 in power minus 10. We expect some deviations from non-Gaussianity, and it is this effect which is just now searching from galaxy surveys. The present accuracy what is achieved is about 10 power minus 9. So still we need to extend it somehow one order of negative more.
Okay, dear Alexei, so thank you very much for your very impressive report. And gentlemen and ladies and gentlemen, we have to move further. So the next speaker is Aranta Ruiz Martinez, and the title is Standard Model Measurements by Atlas and CMS. Please, 30 minutes.
Hello, I hope you can hear me.
Yeah, we hear.
Okay,
Very well. Yeah.
I'm sharing now the slides, so I will start. It is a pleasure for me to present an overview of the standard model measurements performed by the Atlas and CMS experiments. Okay, just as a brief introduction, as we can see in the summary plots on the right-hand side, the production cross-section measurements performed by Atlas on the top and CMS on the bottom. As you can see, we have many new run-to measurements. And in this talk, I will just cover really the most recent ones that I have highlighted and listed here. Okay, first, I will present the measurement of the transverse energy-energy correlations and the extraction of the strong coupling constant. As you know, the even-shaped observables are used to perform precise tests of perturbative QCD calculations and to extract the value of the strong coupling constant. In particular, for Hadron Collider experiments, we consider two observables, the transverse energy-energy correlations, which are defined in this formula, and their associated azimuthal asymmetry is also defined here. In the equations, the I and J indexes run over all the jets in a given event. The transverse energy is defined as the sum of the transverse energies of all the jets, and then phi is defined as the angle between the jets in the transverse plane. We can see in the plots on the bottom of the page the distribution of these observables, the transverse energy correlations on the left-hand side and the asymmetry on the right-hand side as a function of the cosine of phi. These distributions are obtained for a value of HT2, which is defined as the scalar PT sum of the two leading jets in the event above 1 TeV. Then the measured data are compared to the predictions by different generators such as PITIA, Sherpa, and Herwick. The data are divided in 10 bins in HT2 in order to study the scale dependence of these observables. We can see in the plots on the top the systematic uncertainties for the transverse energy correlations on the left-hand side and the asymmetry on the right-hand side. And we can see that the dominant uncertainty here is coming from the jet energy scale. Then the strong coupling constant is determined from fits to these two functions. We can see on the bottom of the page the running of alpha S, where different measurements performed by the LAC and Tevatron experiments are shown. And we can see in the tail at large values of Q the 10 points with this measurement performed at 13 TeV. Okay, now moving to the measurement of the diphoton production cross-section, the main challenge in this analysis is to have a proper estimation of the background coming from non-prompt photons in jet events. We can see here the Feynman diagrams of our signal for direct photons, single and double fragmentation photons, and on the right-hand side for non-prompt photons from hadron decays, which is our dominant background. In this paper, the inclusive cross-section measurement has been obtained, as we can see in the plot on the left-hand side in the vertical line. And this is compared to the most accurate predictions that are available. This is compared to the Monte Carlo multi-leg generator, Sherpa, and also to the fixed order calculations provided by NNLO-JET and by DIFOX. We can see that the best agreement is achieved for the multi-leg generator, Sherpa, and for the most accurate calculations at next to leading order provided by NNLO-JET. In this measurement, we have also performed differential cross-section measurements as a function of different relevant observables, such as the transverse energy of the leading and subleading photons, the diphoton invariant mass, and the diphoton transverse momentum. Here we can see the measured data compared to the predictions by the multi-leg Sherpa generator and from the fixed order calculations provided by NNLO-JET and DIFOX. And as we have seen in the inclusive cross-section or fiducial cross-section measurement, the best agreement is achieved for the multi-leg Sherpa generator and the NNLO-JET calculations. If we compare now the measured data with the fixed order calculations provided by NNLO-JET at leading order, at next to leading order, and at next to leading order, we see that a very good agreement can be achieved with the calculations at next to leading order. And this illustrates the need to include higher order corrections in our calculations to properly describe the distributions from data. Okay, now moving to the collinear set boson emission. Here, a measurement of the set boson angular distributions in events where there is a set boson emitted collinear to a high PT jet is performed. We can see here the differential cross-section measurements as a function of delta R separation between the set boson and the closest jet for two different regions. On the left-hand side, requiring the leading jet PT to be above 300 GeV, and on the right-hand side, requiring that the leading jet PT is above 500 GeV, which is a more extreme phase space and where we have less statistics. we can see that in these plots there are we can distinguish two differentiate regions: the collinear region where the Z boson is emitted close to the high PT jet, which is the region with low delta R values, and the back-to-back region between the Z boson recoiling against a hadronic jet, which is the region around pi. Then the measured data is compared to the predictions given by MATGRAPH plus PCA8 with up to 2 partons at next to leading order or up to 4 partons at leading order. And we can see that in the ratio, the best agreement is achieved in the case of up to 2 partons at next to leading order, although there is although the agreement is within uncertainties, but there is some disagreement at very low values of delta R. Okay, now moving to the test of the lepton flavor universality. Here I present a measurement of the ratio of the branching ratio of the W boson decaying to tau nu over the branching ratio of the W boson decaying to mu nu. This is to probe the universality of the W coupling to charge leptons. For this measurement, we use dileptonic TT bar events as a probe of as a sample of probe W bosons. Here we tag the events that contain an electron or a muon decaying from a W, and then we probe muons that are from muons from the W decay or muons from the W decay with an intermediate tau lepton. We can see in the plot on the right hand side on the top the D0 distribution for prompt muons from the W decay in light green and for muons with an intermediate tau lepton that is the dark green. As we can see in the plot on the bottom right corner, the measure ratio is in very good agreement with the standard model expectation of 1. This measurement was motivated by the flavor anomalies that have been seen at LECB for some time, and also motivated by the long-standing deviation from LEP of 2.7 sigma that is seen also is shown in the plot on the right bottom corner. Just to remark that this measurement provides a factor 2 in precision compared to LEP and has the best precision achieved up to now. Okay, now moving to the first LEC search of the rare exclusive hadronic decay of the W boson going to a pion and a photon. Here the final state consists of an isolated photon plus an isolated track compatible with a pion. And in this analysis, a dedicated variable has been developed, which is the pion isolation variable that can be seen in the plot on the left-hand side, where we see the discrimination power between the signal and all the backgrounds. Here we select TT bar events where AW decays leptonically, and then the signal is discriminated, developing a boosted decision tree. In this boosted decision tree, BDT, we use as input variables for the training observables such as the lepton PT, the missing transverse energy of this pion isolation variable. You can see the BDT score in the case of the electron channel in the middle, and then the invariant mass distribution of the reconstructed pion and photon is fitted. Upper limits are extracted from this fit, and the limits are of the order of 10 to the minus 5, while the theoretical calculations are in the range between 10 to the minus 9 and 10 to the minus 6. Okay, now moving to photon-induced processes, we had the observation of the photon-induced W boson pair production. This is a test of the electroweak sector of the standard model, and we have direct access to the triple and quartic interactions, as we can see here in the Feynman diagrams. In this analysis, The protons radiate ISR photons and then stay intact or dissociate, as we can see in the diagrams with the corresponding percentages. Just to remark that we already had a run-1 evidence from both experiments, ATLAS and CMS, and this run-1 evidence of this process has turned into observation, now analyzing the run-2 dataset. So let me show you a nice event display. This is a candidate event of the photon-induced process of the W boson pair production, where the W's decay leptonically, one to a muon neutrino and the other to electron neutrino. This corresponds to an event recorded in the proton-proton collisions acquired in 2018. You can see in the event display the vertex that has been reconstructed, where there is the muon track in red and the electron track in yellow, and no more tracks from this vertex. Okay, so we can see in this table the observed events in data of the photon-induced W boson pair production and the different backgrounds, where you can see that the dominant background is coming from the quark-induced W boson pair production. In this analysis, the set position of the interaction vertex is obtained according to this equation. And then the number of tracks, which is used to separate the signal from the backgrounds, is defined as the number of tracks in a window in the set axis within 1 millimeter around the set position of the interaction vertex. These are the number of tracks, excluding the tracks from that are used to reconstruct the leptons, the two leptons. And we can see in the plots on the bottom the transverse momentum of the electron and muon system, where we require to be above 30 GeV, where the signal is enhanced, and this observable, the number of reconstructed tracks, which for the signal region, as we see in the table, we require that the number of tracks is equal to 0. And then the other beams are used as control regions. Here we achieve an observation of 8.4 sigma. We had also the observation of the photon-induced dilepton production. In this case, we used the 2017 data set with the ATLAS forward proton AFP detector inserted. This corresponds to a total integrity luminosity of 15 inverse femtobarr. In this case, the observation is with a significance of 9.7 sigma for the electron channel and 13 sigma for the muon channel. And just to remark that this is the first cross-section measurement using proton tagging at the LEC. We can see on the right-hand side the experimental setup with the ATLAS detector and the AFP detectors at both sides, side A and side C. And in this analysis, we define the fractional proton energy loss of the scattered proton and the fractional proton energy loss from the lepton kinematics. In the plots on the right-hand side, we can see the difference between these two variables where the signal peaks at 0. We can see the comparison of the events observed in data and the predicted yields from signal and the combinatorial backgrounds. This is obtained in both sides, A and C. Okay, now moving to the electroweak production of a set boson plus 2 jets, we have here measured the differential cross-sections. This is sensitive to the vector boson fusion production mechanism. We can see on the bottom the typical diagrams corresponding to the electroweak set plus jets signal and the QCD production on the bottom. Here, I would like to highlight that the measured data are sufficiently precise to be able to distinguish between the different state-of-the-art theoretical predictions that have been computed with PauHEC plus Pythia, Herwig plus BBF NLO, and Sherpa version 2.2. In slide number 16, just to show the typical event selection criteria for these BBF topologies, where we require that the high Diejet invariant mass to be above 1 TeV, as we can see in the plot on the bottom right corner. We see that the electroweak signal is enhanced in the Diejet invariant mass tail, and also an important cut is that the Diejet rapidity separation is above 2. Then we define an observable, which is the set centrality, which is used to define the signal region, together with the number of jets in the gap. In this way, we have the signal region where the number of jets in the gap is equal to 0, and the set centrality is smaller than 0.5. The other cuts are used to define control regions. So in this paper, we have measured the differential cross-sections as a function of 4 observables: the Diejet invariant mass, Diejet rapidity separation, the dilepton PT, and the Diejet azimuthal separation. We can see in the plot on the left-hand side the differential cross-section as a function of the Diejet invariant mass for the inclusive set plus jets production, which is compared to the predictions provided by Sherpa and MathGraph plus Pythia 8, where there is some overestimation of the distribution by Sherpa in the tail. We can see on the right-hand side the differential cross-section as a function also of the Diejet invariant mass, but this case for the extracted electroweak signal. And here the measured data is compared to the generators Sherpa and Herwig plus BBF NLO, and also PauHEC plus Pythia 8, where we see some overestimation also from PauHEC and Herwig. And then on the plots on the bottom, we can see the fractional uncertainties, which in the case of the inclusive production, the dominant is coming from the jet uncertainties, while in the electroweak signal, together with the jet uncertainties, we have large uncertainties coming from the strong set plus jets modeling. Okay, now moving to the electroweak production of a W and Z boson in association with jets, and the same sign W boson per production in association with jets. Here, the vector boson scattering is contributing to the electroweak induced production, as we can see in the diagrams on the top, and we can see also the Feynman diagrams corresponding to the QCD production. Here we have achieved also an observation of the WZ electroweak production at 6.8 sigma significance, and the differential cross-sections have been obtained as a function of different observables. Constrained on anomalous quartic gauge couplings have been obtained in the effective field theory framework. So let me show you here the normalized differential cross-sections as a function of the Diejet invariant mass, on the left for the same sign W boson per production, and on the right-hand side for the WZ production, which is compared to MathGraph plus Pythia 8. And on the bottom, we can see the observed events in data compared to the predicted yields from the different processes. And here we can see also some signals for anomalous quartic gauge couplings. These are for the transverse mass of the W boson per production on the left and the WZ bosons on the right-hand side. Okay, so now moving to the polarization in electroweak, same sign W boson per production in association with jets. Here, deviations in the BBS production of longitudinally polarized gauge bosons have been predicted in different BSM models. And this is the first measurement of the production cross-section for polarized same-sign W boson pairs. Here, two different BETs have been developed to separate the different polarized final states. The W can be polarized longitudinally and transversely. But here the data set is still quite limited. And in this analysis, the electroweak same-sign W boson pair production with at least one longitudinally polarized W boson has been measured with a 2.3 sigma significance. We can see here the comparison of the event yields from data and the predicted yields from the different processes for different polarizations. Here, kinematic distributions, depending on if the W boson is longitudinally or transverse polarized, are different. For instance, the W boson for longitudinally polarized W bosons, the PT distribution is softer. Okay, now moving to the observation of the electroweak production of the set boson pairs in association with jets. We can see here the typical diagrams of this process for the electroweak BBS diagrams on the top and for the QCD production on the bottom. Here, this analysis has been performed by both ATLAS and CMS experiments, and this has been performed exploiting the leptonic decays. In the case of ATLAS, the 4 lepton and 2 lepton channels have been used, while CMS has explored only the 4 lepton channel. With this analysis, all the diboson plus 2 jets channels have been observed now. With ATLAS, we achieved an observation of 5.5 sigma, while CMS has evidence of this process with 4 sigma. We can see on the bottom the multivariate discriminant that has been used in ATLAS for the 4 lepton channel on the left and the 2 lepton channel in the middle, where the data are compared to the predicted yields. And in CMS, for the 4 lepton channel, we see the matrix element discriminant that has been used. Now, moving to another process that has been also observed, the electroweak production of W photon plus 2 jets. Here, the BBS processes comprise an independent and complementary method to study electroweak symmetry breaking. We see here the different Feynman diagrams corresponding to the BBS contribution, the electroweak contribution with triple gauge couplings, with quartic gauge couplings, and on the right-hand side, the QCD production. And on the plot, we can see the results and even observed events from data compared to the predicted yields from the different processes. Here we have observed a significance of 4.9 sigma, almost observation, but just to remark that when this is combined with ATV data, an observation of 5.3 sigma has been obtained. And I just presented the W photon plus 2 jets. Now moving to the set photon plus 2 jets, we have evidence in this case. This has been obtained with the early RAM2 data set from 2015 plus 2016 with a total integrated luminosity of 36 inverse femtobar, and with this 3.9 sigma significance has been achieved. That is very close to observation with 4.7 sigma if this is combined with ATV data. Here the signal is extracted using a 2-dimensional fit of the dijet invariant mass and dijet pseudo-rapidity separation.
I'm very sorry, Ruiz Martinez. 5 minutes are left.
Okay, thanks.
Uh-huh.
I'm finishing. And then the fiducial cross-section is measured and is in agreement with the standard model expectation. Also, constraints on the anomalous quartic-gauge couplings have been obtained. We can see in the plots on the bottom the event yields from data and the predicted yields for the dijet invariant mass and in bins of the dijet pseudo-rapidity separation. This is for the electron channel, set going to electrons on the right-hand side, and the muon channel on in the middle. And then we can see in the right-hand side the invariant mass of the set and photon system with the data, the events coming from data and the predicted yields. Okay, and now moving to the observation of the production of 3 massive gauge bosons. This is the first observation of the combined production of 3 massive gauge bosons for triboson for W and Z. We have performed searches for the individual processes in final stage with 3, 4, 5 and 6 leptons, considering only electrons or muons. We can see in the plot on the right-hand side the signal strength, which is defined as the measured cross-section times branching ratio over the standard model expectation. And here the results from using BDT or sequential cuts are compared. And on the bottom, we can see the observed events from data and the predicted yields in the case of the same sign dielectron final state, and then 3, 4, 5, and 6 leptons. We have observed a significance of the combined triboson production of 5.7 sigma with this analysis using the full run2 dataset. Okay, and this is the last analysis, the inclusive 4-lepton differential cross-section. Here, as you know, the 4-lepton final state has contributions from many interesting standard model processes, such as the single set boson production and the Higgs boson production, or on shell diboson set production. We can see here the different diagrams that are contributing to this 4-lepton final state, and this is sensitive to new physics or BSM contributions, like the modifications to the couplings of the Higgs or gauge bosons, or possible for fermion interactions. I would like to show you here on in the plot on the left-hand side the comparison between data and the predicted yields from the different processes. We can see also in the ratio that there is a reasonable agreement. And on the right-hand side, the differential cross-section as a function of the invariant mass, the 4-lepton invariant mass, where the measured data are compared to the predictions from Pauhek and Sherpa. And we can see on in the x-axis where each process is the dominant one. Okay, so this brings me to my conclusions. We have many new results with the latest and greatest run2 dataset by the Atlas and CMS experiments, and the legacy run2 measurements are being finalized. We have performed comprehensive tests of the standard model over 15 orders of magnitude in cross-section. We are going now with a large data set, more differential, and the results are being compared to the most accurate theoretical predictions, state-of-the-art Monte Carlo generators, and fixed order calculations. I have presented a test of the lepton flavor universality, which is in very good agreement with the standard model expectation and has the best precision achieved up to now. The first LHC search of the rare exclusive hadronic decay, W going to pion and a photon, and also first measurements of the production cross-sections of polarized same sign W boson pairs. And also we have first evidence of observation of rare processes such as photon-induced processings, or yeah, we have observed now all the diboson plus 2-jet channels. And we have also observation of triboson. You can find more information in the public material in these links. Thank you very much.
Thank you. There is one question in chat. So let me just read this question. What is the reason for getting two different values for the observed and expected significances?
Yeah, well, this is normal as for the expected. This is often used with the expected is with the predictions that we have, and then once this is unblinded that is observed, there are always can be some fluctuations and uncertainties. So
I see. Okay, thank you very much.
thanks a lot.
Yeah, one more time for very impressive and very informative report. We have to move further. So the next speaker is Amandeep Kaur, and the title is Exotic Searches by Atlas and CMS. Please, 30 minutes.
Hello, everyone. Can you hear me well?
Yeah, very, very well.
Okay, so I hope you can see the slides. I'm not sure actually. Do you see the slides?
Yeah.
Okay, so due to the bandwidth issues, I have to keep my video off. First of all, good afternoon, everyone. So this is Amandeep Kaur, and I will talk about the exotic searches that has been performed by Atlas and CMS. Thanks to the organizers for having me here to present the results for Atlas and CMS. So first, I will just give a brief introduction about these two detectors, which are actually situated at the LSE ring and almost in opposite direction to each other. And these detectors actually led to the discovery of Higgs boson in 2012. So with successful data taking during run 2, which ended in 2018, these detectors have recorded luminosity, integrated luminosity of about 139 fem to 1 inverse of data at 13 TeV. And so with this large center of mass energy and luminosity, it gives a unique opportunity to investigate different extensions of standard model and to search for rare decays. But we have a challenge ahead of us, which is because of the occurrence of a number of interactions, simultaneous interactions in each bunch crossing. So like in the 2018, we have the mean number of interactions occurring around 37. So next, the question that we would like to ask to search for the beyond standard model is why actually we need to look for a beyond standard model. So we know that the standard model successfully, it explains very beautifully and very nicely the interaction, the structure of matter and the interactions between them, but still it fails to answer many important questions like the inclusion of fourth fundamental force, that is gravitational force, why we have only 5% of matter made up of ordinary standard model particles in the universe, and actually what is actually a dark matter. So another set of questions like why there are only 3 families of quarks and leptons, and if there is a more fundamental theory of which this standard model theory is just a low energy approximation. So to answer these questions, new models beyond standard model, they have evolved with time and they predict new phenomena and new particles at TeV scale. So it would be interesting to look for beyond standard model to answer these questions. So now the question is, what do we actually expect beyond standard model? So we look for new resonances, which are actually one of the easy way to look, because of we search for a bump or we search for an excess over the smoothly falling standard model predictions or backgrounds. and we look for actually dark matter to answer the questions of what is dark matter and what is the interaction of dark matter with standard model particles. We look for long-lived particles which can actually answer the questions for matter and antimatter asymmetry, and then we look for these new quarks which can answer questions for a lepton, why they are same number of leptons in quark generations. So moving to the first talking about the resonances. So as I mentioned that resonances are quite easy signatures if we tackle issues like backgrounds and other issues, technical issues. So but what we do in resonances is we search for a bump over a smoothly falling standard model background. So these resonances actually can decay to dilepton pairs or to top quark pairs or dijets, which and also to the dibosons. So there are extensive search program by CMS and Atlas in this sector, but we will just focus on very brand new and recent results by CMS and Atlas in this sector. So first of all, I would like to highlight this dijet resonance search that has been performed by CMS, and in this particular search, this search is actually performed for masses greater than 1.8 TeV for the search of both narrow and broad resonances. So in this particular search, there is to reduce the analysis sensitivity towards the final state radiations. These close by jets, which are of delta at 0.4, they are combined to form a wide jet, and this actually enhances the analysis sensitivity. And one of the another thing which has been done is apart from the traditional fit method that we utilize to predict, to estimate the background, a new method called ratio method has been used for dijet invariant mass greater than 2.4 TeV, which actually derives the estimation of the background from the control region, unlike fit method, which actually drives the background from the signal region. So in this, using this ratio method along with the fit method for the broad resonances, the sensitivity has improved significantly. So with this, we can see here the divergent invariance mass distribution, and we can see that the data agrees well with the standard model predictions, and no excess has been found. And we can set then limits to the cross-section times branching ratio to and times acceptant as a function of resonance mass for different resonances like W prime, Z prime, or dark matter or graviton. Then moving to this another very interesting search by CMS. So in this particular search, this search is performed for at low masses. So I would like to point out that to search for a resonance, basically a digent resonance at low masses is a challenge because of the multi-jet background or a QCD background, its cross section is very large at low masses. So for that, actually, this very different technique has been used, which is called data scouting, and which is used to collect the data and further analysis. So in this data scouting technique, the data is recorded using only the calorimeter based information with the lower PT thresholds and backgrounds, and in this the background is estimated using giving parametric fit to the data, as you can see on the left hand side plot. So we can see here that the figure here shows expected digest mass distribution of resonance signals for masses 700 GeV, 550 GeV, and 400 GeV. And we can see that the data and the standard model predictions agrees well, and no excess has been found in this. So we can then set limits to the cross-section times branching ratio, and as a function of resonance mass, that have been considered in this analysis. So moving to the another important search by Atlas. So this in this particular search, the resonant decays to pair of top quarks, which further decays hadronically. So also in this particular search, new techniques have been used to increase to have improvement to increase the sensitivity towards final state. So as I've mentioned, the jets are actually very challenging to tackle. So because of the QCD background, so in this analysis, a deep neural network technique has been utilized in which the substructure of the jets of large radius jets of R1 1.0 have been looked, and they have been in this way the jets are distinguished like if they are whether from W decay or Z decay or even from QCD. Also for the B tagging, in this case scenario, the variable radius track jet method has been used for highly boosted top quarks, and based on this, the two signal regions have been explored, which is one is with 1B and there is 2B jets in the final state. And we can see here the reconstructed mass of the TT bar system, and in the 1B final state and in the 2B final state, and we can see that data agrees well with the standard model predictions, and no significant deviation has been observed. So with this, the limits has been set to the cross section as a function of masses of Z prime and we can see that because of improved analysis technique, this limit has lead to 65% improvement in the expected limit at 4 TeV. So next, our another search is the resonance search for the diboson, in which the resonance decays to the pair of diboson. This search actually targets the resonances in from 100 GeV to multi-TeV, ranging from 100 TeV to multi-TeV, and in different BSM scenarios. And in this, we can either have a standard production of resonance, which can further decay to two bosons, vector bosons, and also we can have a VBF production of this resonance, which further decays to dibosons. So if the mass of this resonance is very high, then we can expect that the vector bosons, the decay product of these dibosons will be highly collimated, and then we need special or new techniques for identification, reconstruction of the objects which are coming from the decay of these vector bosons. So in such dense environment, it is very critical to combine the calorimeter and tracker information. So with for these kind of searches, CMS and Atlas has improvised their reconstruction techniques very well, and also the background estimation techniques. So I would like to point out this very beautiful event display in which this is related to the ZH resonance, in which Z decays to two muons that can be seen in red, and at the Higgs decays hadronically. So I will talk about the results of these resonance in upcoming slides. So here on slide number 10, I will first I would like to highlight the results by Atlas, in which Atlas looked at resonance decay to VH, in which he as I've mentioned previously also, to tag the W or Z jets from W or Z, which is our signal here. We need the algorithm. Atlas has used this new technique called track callo cluster, in which the information of the tracker and the calorimeter is used to tag the jets from W and Z decay, and to distinguish them from the decays of QCD. And also for the identification of B jets, new variable radius track jet B tagging is used, in which the radius of this this large jet is dependent on the PT of these jets. So as obvious, in the hadronic decay, the multi-jet background or the QCD background is a dominated one, and it is estimated from using BDT, and it is estimated in the zero tag region, and then it is using extrapolations, it is estimated in a signal region, which is either one B jet or two B jet. So various this search has various signal region, like this V could be Z or this V could be W. So we have ZH1B, ZH2B, or WH1B or WH2B. So here I have shown the one of the digit invariance mass distribution for uh, this signal region, which is VH2B, and we can see that the data agrees well with the standard model predictions, and correspondingly the limits has been set to the cross section of Z prime going to this ZH resonance and WH resonance, as shown here. Similarly, for the another channel in which we have the semi-leptonic final state, or in which Z goes to 2 nu and we have a Z goes to 2L when at the Higgs goes to decays hadronically. In that we have, as I mentioned, the track color cluster algorithm is are used in that scenario, and we can see that here the transverse mass distribution of the VH system, in which because we cannot actually have the reconstruct the full mass in the zero lepton final state. So this is the signal region of zero lepton final state, and the transfer mass distribution of the VH system is plotted, and this red color, red line is dotted line is the signal, and we can see that no excess has been found over the standard model predictions, and data agrees well with the standard model predictions, and correspondingly the limits has been set for the Z prime going to GH in both zero lepton and two lepton final states has been set as a function of masses of Z prime. So next, one of the search which is very important by CMS. So CMS actually looked for spin 1 resonances in the boosted regime. So that is the search has been performed for resonances greater than 800 GeV, and this is a similar search which is performed by Atlas, that I have explained on the previous slide, in which Z goes either to 2 nus or Z decays to 2 leptons. In this search also, with the standard production of the ZH resonance, a VBF production of the ZH resonance is also considered, and limits has been set for both the production modes. So in this, the major background is V plus Z, or TT bar or diboson, and we can see that this is a digit mass distribution, and it is divided into signal region, validation region, and sidebands for to have signal depleted region and signal rich region. So we can see that here we have from the BDT training, we have this standard model, the predictions from the data, for the background and the standard data, and this red color is our signal for mass of Z prime to be 2 TeV. And we can see that no excess has been found in this final state, and we can set limits to the cross section of Z prime going to ZH in the non-VBF signal and also in the VBF signal as a function of masses of Z prime. So anything below 3.1 T, 3.5 TeV in the non-VBF signal, and 3.7 TeV for HV, for this model A and B, the Z prime below these masses is excluded, and similarly the limits has been set for the VBF signal also. So next is one of the questions that I have raised in the introduction slides is why we have same number of generations of lepton and quarks. So to answer this question, it is very to answer this question, many models beyond standard model have predicted these new particles called leptoquarks, which carry both lepton and baryon number, and they have fractional charges. These vector quarks can be singly produced or can produce in pairs, and they decay to lepton and a jet. So as we can see in this event display. So these searches are actually highly motivated by the B meson anomalies, and here we have this the ratios of branching fraction of D star and D, and this in various experiments have provided these ratios, and we can see this black point is the standard model predictions, and we can see that with the recent results, the 3.1 sigma discrepancy has been observed with the standard model predictions. So moving to the one of the searches performed by Atlas for the leptoquarks. So in this here Atlas has new results on where they look for pair production of leptoquarks that decay to top and tau. So this is the first analysis which looked for this top and tau decays. So depending upon the top decays, either we can have, and also depending upon the lepton flavor, we can have several final states in with at least one light lepton and at least one hadronic tau. So for the tagging of hadronic tau, new neural network techniques have been developed, and is here we can see the events in the different final states, as I mentioned, in which have been considered in this analysis in the signal region. So we can see that the data agrees well with the standard model predictions, and correspondingly limits has been set on the cross section of these leptoquarks decaying to top tau pairs, and as a function of masses of leptoquark. Also, Atlas also looked for a top quark lepton, which is in the fully hadronic final state, in which the top decays hadronically, and we have in this lepton search, we have for different control region, and signal region is looked for with the BDT. And for in this final state we have TT bar as a TT bar and the Z plus Z as a major backgrounds, and we can see that in these control regions data and standard model predictions agrees well with the data, and we can set limits on the cross section of these top quad going to either electron top or mu top, and limits are set at 1.4 TeV for the electron channel and 1.47 TeV for the muon channel. So another search which is performed by CMS. So CMS also has new results for singly and pair production of leptoquarks, and we can see here the Feynman diagrams of the pair production and the singly produced leptoquarks. Depending upon the coupling of these decay products, that is either the top quark plus a tau lepton or bottom quark plus neutrino, we can have different final states like top tau nu b or top tau mu. So with this we have different we have from neutrinos we have high PT miss, we have high HT and one hadronic top candidate and one hadronic tau, and we can look for the scalar transfer sum of all these objects, and here we have the number of events as a function of a scalar sum of all these products. And we can see, depending upon the masses of the leptoquark, this top quark which is produced, it can either be merged or either be resolved. So we can see that here we can see that the data agrees valid with the standard model predictions, and limits are extracted and are depending upon and they have been here the limits have been plotted as a function of this coupling as a function of this masses of leptoquark. So anything, so this actually this gray region is actually the regions which is preferred by the B-meson anomalies, and these lines are actually corresponding to the singly or pair production of leptoquarks, and anything which is left in the left of these lines which is excluded. So moving to the search for the dark matter. So as I mentioned now that we keep asking ourselves question that why only the 5% of the matter in the universe is made up of standard model particles, and what is actually a dark matter. So if dark matter exists, and if it couples to the standard model particles like we think, then we will have the pair production of these dark matter particles in the at the collider experiments or at the LSC, and these dark matter candidates actually escape the detector because of their weakly interacting nature, and we can have the signal as a large missing transverse energy which can be observed with the standard model particle. So several models have predicted this dark matter, and we have like a simplified S channel model in which this mediator that couples to standard model particles and dark sector particles. Also we can look for more complete models like 2 Higgs doublet model, in which this A is the pseudoscalar, which decays to dark matter particles. So here is a very interesting event display in which the event has this jet which is recoiling against this large missing transverse energy. So we will go through the results of this analysis in the upcoming slide. So here we have the very interesting search which is performed by Atlas for the dark matter. In this search, different TW channel and T channel has been explored for the production of dark matter. And in this particular search, the Atlas targeted actually the 2 Higgs doublet model, where we have dark matter decaying to single top and dark matter. So we can see here. And in this several final state, depending upon the decays of top, either we can have 1 lepton or 2 lepton in the final state and is explored. And then here we have the number of events in different control region for the prediction of these backgrounds. And we can see that the data is no significant excess is found in with respect to the standard model predictions. And 2D limits actually are set for the masses of charged Higgs and masses of this pseudoscalar A. And again, in anything which is inside these, which is left to the these contours is actually excluded. So another search, which is very interesting search, has been performed by Atlas, and in which we have this is that I was mentioning, that this single jet which recoils against this large missing transverse energy. So we look for events that have jet and large missing transverse energy, and actually this search this is a model independent search, or this search actually has considered many models like axial vector mediated model, or SUSY, or large extra spatial dimension models. Various models have been considered by this search. And here we have basically we look for an excess in the PT recoil because we have signal large missing transfer energy as our signal. So we can see that the no excess has been found in this and the data agrees well with the standard model predictions. So for this we have the limits set to the cross section for different missing transverse energies bins, and also these limits are set in the plane of this dark matter candidate and masses of this axial vector mediator. And we can see this blue line, which was the result for 36 5-to-1 inverse of data, and we can see that with the increased luminosity, our limits have improved very much.
Dear
So next,
Amandeep, I'm very sorry. Just 4 minutes left.
okay, thank you. Yeah,
Sure.
So next search has been performed by Atlas. This is actually the first result at the LSC that has been recorded. So in this search, the search for this dark matter is produced in association with this dark Higgs, which is represented by this S in this Feynman diagram, which decays to diboson pairs and which decay further hadronically. So to better estimate this dark Higgs resonance, which is decaying to this hadronically, this track assisted reclustered jets technique is used, in which the jets are reclustered with the cone radius of 0.8 based on this R.4 calorimeter jets and tracking information. So with this, we have the signal region, and also the signal region is merged in various ranges of missing transverse energy, and data is overlaid in the signal region, in this control region of 1 mu and this control region of 2 mu. So we can see that in the plot below that this is we have invariant mass of the dark Higgs, and we can see that no significant success has been found, and we can set limits to the cross section as a function of masses of this dark Higgs, and anything greater than this 160 GeV is actually excluded. So next we have this search for dark matter from the CMS, and in this particular search, CMS has a search for the production of dark matter with the VBF topology, and in which this is actually the Higgs actually decays to isolated photon, which is a standard model particle, and this dark photon, which is the predicted which we need to look for. So in this also, we have this the fit is for this search, the fit is done to the distribution of transverse mass of this photon plus ET miss, and the cross limits have been set to the branching ratio of Higgs to invisible, that is 2.9%, and combining with the CMS ZH resonance search. Also, we can either scan the masses of Higgs, that is if there is any other Higgs of different mass, and we can set limits to the cross section on based on that. So then another unconventional signatures that are interesting to look for are the long-lived particles, which can provide the physics, which can give hint for the physics beyond standard model. And these searches are actually very challenging as experimental point of view because of their non-standard reconstruction, because of their non-standard signatures, we need dedicated triggers and dedicated techniques for background estimation. So here we have we have this analysis for the search for long-lived particles, in which by CMS, in which the distinctive topology has been utilized, in which the pair of jets are originating from the secondary vertex, they have been looked for. So this search is actually targeted many models like split SUSY and RPV SUSY models, and this is exotic Higgs model in which the Higgs decays to two scalars, which are actually, of course, these scalars are long lived and which decay hadronically. So a dedicated secondary vertex reconstruction is performed, and this gradient boost decision tree method is used, which utilized actually variables like track multiplicity and impact parameter, and the distance between this primary and secondary vertex as input parameter. So our signal region would be in the high, where we have the high GBDT score, that is score is greater than 0.988, and we can see that in this particular signal region there is no excess has been found, and similarly the limits has been set to the branching ratio of Higgs going to two scalars at 1% for C tau for the decay lengths of 1 millimeter to 1000 millimeter. So the one of the very interesting and the latest results are from Atlas on this question that we keep asking, if why we have same number of families, same number of this lepton and fermion families. So we have actually these neutrino oscillation experiments, which have demonstrated that the lepton flavor conservation is actually violated in nature, because also in the standard model there is no fundamental theoretical motivation behind this lepton flavor universality in the fandom, which is actually added in the standard model. So we need to look for the lepton flavor violation. So this search has used Z boson decaying to tau lepton, and another lepton must decay to either electron or muon with opposite charge. So here we have the transfer mass distribution for the signal. Here we have the transfer mass distribution for the background, in which the background is basically where the jets are faking the tau hadron. And using the neural network technique, this search use the combined neural network distribution is plotted in the signal region for the mu tau final state. Similarly, we considered E tau final state, and we can see that no excess has been found beyond above these standard model prediction backgrounds. So the very stringent limits has been set on the branching ratio of this Z to E tau and Z to mu tau final state, and these actually searches have superseded the otherwise best limits which was provided decade ago by the LAP experiment. So this is very interesting search that has been performed by Atlas. So concluding my talk, so as I mentioned that searching for exotic is both challenging and exciting with the development of new techniques and considering many possible final state, many stringent in many models, for many models and many sectors, these stringent limits have been put. And with increasing efficiency with using different analysis techniques and improved object performance, sensitivity is actually increased, leading to improved units. Several full run to results are still yet to come, so stay tuned, and thanks for listening.
Oh, thank you very much.
Thank
So we don't have any questions in chat. So do I understand correctly that up until now, nothing beyond the standard model predictions has been observed with statistical significance, right?
Yeah, but several like for the LFV, this leptin flavor violation, these result gave a very nice. This result was very interesting to look for because of very stringent limits on the branching ratio of this Z2L tau. Yeah, but yeah, that's true. We still
Okay.
have a lot to cover.
Okay, so thank you very much for your very interesting, informative, impressive report. So the next speaker is Anna Cueta, and the title is Experimental Results on the EFT, Effective Field Theory, I understand, in interpretations of standard model and Higgs boson measurements. Please, 30 minutes.
Hi, can you hear me and see the slides?
Yeah, we hear you very well.
Okay, thank you. So I'm pleased to present you the experimental results on effective field theory interpretations for a standard model and Higgs boson measurements on behalf of the ATLAS and CMS collaboration. So as you have heard from the previous talk at the LHC, there has been no clear hints from BSN physics from the direct searches that has been performed. However, we have tested the standard model with a wide variety of analysis covering an impressive range in cross-sections. And this analysis can not only be used to test the standard model, but also to look for new hints of new physics if any deviations are found. So the standard model effective field theory provides us with a framework for a systematic interpretation of the large data sets in terms of new physics. And an advantage of this framework is that it does not assume that the theory is valid at arbitrarily high energies. So how it works is that it extends the standard model Lagrangian by adding new operators of dimension larger than 4, suppressed by the new physics energy scale, lambda, so in powers of 1 over lambda, it's this suppression. And this new physics energy scale is assumed to be much larger than the electroweak scale that we prove with the standard model, so much larger than the vacuum expectation value of the Higgs field. So for this extension of the Lagrangian of each possible dimension, what we do is to write all set of operators that form a non-redundant basis of them, and they keep the same fields and symmetries as in the standard model. Here only the even dimensions are shown because the violate lepton and baryon number conservation. So just to mention that in measurements, only the ratio of the CI, which are the so-called Wilson coefficients, appearing in front of each operators over lambda, is measurable. And at each dimension, several operator bases can be worked out. And in general, you will see that different conventions are used from the experimental side. So any constraint on an EFT coefficients will set a constraint on a large classes of UV theory. And the other way around, if we see any deviation from the standard model value of these coefficients, which is 0, we will not be sure of what is the UV theory that describes the work, but we will have some hints on its properties and how it behaves. So now I just want to give you some concepts about this SMEF and talk about the higher orders in SMEF. So when we start building our cross sections, we start the first time that it's not a pure standard model, is the interference of a standard model amplitude with an amplitude in which we have one EFT insertion from the diagram that you can see on the slide. This gives us the interference term, which is also known as the linear term. And then we can have two of these amplitudes and have the quadratic terms and start complicating the series by adding more insertions or going to higher dimensional operators, but also we can have add more terms in QCD, so adding more loops. So the naive expectation is that this dimension 6 interference term is the leading one and is much larger than the quadratic term and of the same order of the interference of the dimension 8 operators with the standard model. However, this is not always true. We can have the interference to be suppressed. And the study of the quadratic terms can be show some light on the convergence of the EFT series. So typically for these predictions, a leading order SMEFT is used, but this is just because SMEFT is complicated. However, it is compatible with next to leading order corrections, unlike the kappa framework or anomalous couplings interpretations. And there are already available tools that allows to compute these SMEFT effects as next to leading order. One of the caveats is that there are no clear recommendations on which are the real uncertainties on this CFT prediction. So apart from the common theory uncertainties that we apply to the standard model, there can be some other uncertainties coming from the truncation of the series, the terms that we consider, or even the input parameter scheme that we are using. And in general, these are not tested by any of the interpretations in the analysis. So the effects of the EFT in differential measurements are usually shown in the tails of the distributions, since they grow with the energy over lambda. However, this growth of amplitude with the energy can lead at some point to an unitarity violation, and will enter in a regime in which the EFT is no longer valid. So this EFT approach has not always been used. So for example, at LEP, it was more common to have in the vector boson side to have interpretations in terms of anomalous triple gauge couplings. So where we look for deviations in the couplings of 3 vector bosons. And this was controlled by 3 CP conserving parameters, that the one that you can see on the slide. And the way they parameterize everything is just adding the terms in the Lagrangian that will give rise to an anomalous couplings as the one that they were looking for. In general, we could always have more terms adding derivatives by adding additional 1 over MW scaling. And here there were not as many rules as in the EFT, but we need to keep all the invariances and symmetries of the standard model, since the terms could be gauge invariant. And of course, this case of interactions leads also to unitarity violation and would need some unitarization scheme to recover this. However, there is a mapping or a way to go from this Lagrangian expansion to a proper EFT basis in which you care about the gauge invariance and so on. And here I have just shown some of these, how this mapping will go, and the other parameters are in the backup. However, when we consider the full EFT basis, there will be many operators affecting these vector boson measurements, which are usually not considered, apart from the ones that I'm showing in the slide, with the argument that they were constrained at LEP. However, this can be a bit basis dependent. So now I start with the measurements. The first one is the WW and WZ measurement. That is a dedicated measurement to constrained anomalous couplings from in WW gamma and WWZ. Here, the semi-leptonic channel was chosen because it offers a good balance between the purity and efficiency, and the Z or the W that decays hadronically does it inside a Fatjet. Then the limits to the anomalous triple gauge couplings are obtained from 2D and bin fits, likelihood fits, to the soft drop mass of the Fatjet and the invariant mass of the W and the Boson system. And here in the plot, we have just an example distribution of this invariant mass with the data points, the standard model with its uncertainties, and also one of these injected signals from one of the operators considered, this CWWW. So what they did for this analysis is that they did not only set limits using the LEP parameterization, but they also converted them into EFT limits, as you can see from the table, and compared them with the ATV1, and they have been nicely improved from the ATV ones. So the next measurement is an atlas measurement of WW, but this time in the full leptonic final state. This WW measurement has more background than the WZ and needs to control more the background from TT bar, and this is done by imposing a jet veto, so this is WW plus 0 jet. And the limits are extracted from the unfolded measurements of the leading lepton PT, as the one as you can see from the plots. And one check that they did in the analysis is that in principle in the unfolding we can have different corrections from the standard model or the EFT, and they checked that in this case they were not sensitive, so they were similar corrections for the standard model and the EFT. So this analysis is a bit less sensitive to the OW on OWWW than the WZ analysis. But there is some relevant checks. It's the study of the quadratic terms. So in this table, what you can see is the comparison of the limits that you could set on these parameters from the linear and quadratic terms or the linear only. And you can see how they are very relevant for the CWWW constraints. And from this linear plus quadratic, they also show the same constraints, but also adding the CPO operators that will only appear in the quadratic terms, since they are selecting a CP even variable to extract these limits. So the next one is also a WW analysis in the same final state from CMS. However, they introduced a key point in the analysis, which was the addition of the one jet category. So as I mentioned before, this has more difficulties in the way that they control the background, and they even studied two different methodologies, yielding very similar results. So then the limits for ATGCs were extracted from MEW template. So they chose this variable, and here you have an example, just because it's less sensitive to higher order QCD effects, and also a bit less sensitive to some systematic uncertainties like the jet energy scale. And they exactly did the same checks as in the previous analysis from the effects of in the unfolding. So for the extraction of the limits, they just used the different flavor event sample, so an electron and a muon, just because it has much smaller contamination from the region. And they started the distributions at 100 GeV just to reduce the Higgs contribution. So the addition of this one jet measurement made that the analysis could improve the factors, and also the limits that I have shown in the previous analysis from Atlas by a factor of 2, as you can see if you compare these slides and the previous one. However, still, at least from most of the operators on CV, the constraints are always stringent from the semi-leptonic channels, the first one that I showed before. So the following analysis is a bit different in many senses. So this is an analysis of the differential cross-sections for electroweak set production in association with two jets. Here the set decays leptonically in electrons or muons, and it was the first time that this final state has been measured, and you have heard from Arantxa. It's using the full run-to data, and they look at the typical topologies of this BBF topology. So two high PT jets with a wide separation in rapidity. So they use a bit different bases that I have been showing before. They use the Varsaw basis that you can see in the backup of the slides, as implemented in the SMEFTSIM package, which is linked here. And they did not obtain the limits just looking at one of the observables, but looking at 4 of them. And they introduced parity opt observables like the sign delta phi jet, in which the jets are ordered in rapidity. Since this variable is can be show sensitivity to CPO observables already at interference level, but also it's the most sensitive variables also for the CP even ones. So they checked for the analysis the importance of the quadratic terms. And what they saw is that the constraints were mainly coming from the interference. So in this case, the EFT was converging properly, and there were not, at least a priori, not many surprises appearing from the higher orders. So this small difference between the quadratic and interference terms can be seen on the table. So first you have the linear only constraints and then the linear plus quadratic, but also can be seen from the distributions in which the purple line, which is the interference plus quadratic terms, are not adding very much information in most of the cases to the interference ones. So now we switch to neutral triple gauge couplings and anomalous quartic gauge couplings. So starting from the NTGCs, these neutral gauge couplings are not allowed in the standard model and also do not appear at dimension 6 in 3 level. So they first appear in dimension 8 EFT with the operators that you can see on the slide. However, in many analyses, what you will see is some parameters corresponding to a vertex approach, so similar to the Lagrangian one that I have mentioned before, that you can see also in the backup. For the anomalous quartic gauge coupling, the situation is more or less similar. If they appear first at dimension 8, and it's assumed that when you test the full EFT, there will be other operators from dimension 6 affecting these measurements. However, what is assumed is that this contribution of these operators is negligible, since they have been already constrained by other measurements. So usually the Evoli basis is used, and also you can find it in the backup. And the Lagrangian terms are separated into these 3 categories. So the first 2, just looking at the kinematic fields of the Higgs. The second one is mixing derivatives of the Higgs fields and 2 field strengths, and the last one's mixing 4 different field strengths. So we start with an atlas analysis of set with 2 leptons and 2 neutrinos, looking for neutral triple gauge couplings. This final state has larger branching fractions than for lepton, but also larger backgrounds. And the NTGC limits are obtained from the unfolding PT of the 2 lepton system distribution, as you can see in the plot. But they set the lower limit to 150 because the EFT or the anomalous, the neutral triple gauge couplings will only appear at high values of the PTLL distribution. So in general, the sensitivity range of this analysis was found to be within the unitarity bounds, so no unitarization scheme was applied. And this measurement is still limited by statistical uncertainty from the data, so it has around a 40% of uncertainty. And the limits were extracted using a log likelihood ratio, relying on the Gaussian approximation, so they only used beams with at least 10 events. So these are the limits that they could set on each of these parameters. However, these limits were already improved by this CMS measurement of set to 4 lepton. This measurement was performed in 3 different channels. The 4 electrons, 2 electrons, 2 muons, and 4 muons, and here both set bosons were considered to be on-shell. So for the interpretation, the 3 channels were combined, and the limits were extracted using the 4 lepton mass. And this is just an example distribution of the MZZ mass with some of these parameters, well, a combination of these parameters shown. For this analysis, what they did is also to check the effects of including the electroweak corrections, and this improved the limits by 4 and 6%. And they showed the limits not only for this vertex approach that I mentioned before, but also for the EFT parameters that were shown previously in the slides. This measurement has the most stringent limits on ZZZ and ZZ gamma and anomalous couplings. And just to mention that the Z gamma gamma anomalous couplings are still better constrained at this atlas measurement of Z2 neutrinos plus gamma. And also a similar strategy was followed by the atlas ZZ to 4 lepton analysis, however, going to having looser constraints because they were using a restricted data set with only 36 inverse femtogons. So now we switch to topologies, to BBS topologies. So they will be looking for jets with high invariant mass and a large rapidity separation. And this is the W gamma analysis from CMS, on which W decays leptonically into an electrons or muon. And the anomalous quartic gauge couplings are obtained from limits to, from fits to the invariant mass of the W and the photon system. And this is the distribution that you can, from which the limits were extracted. Here they use the Evoli basis because they will be constrained in anomalous quartic gauge couplings, and the limits were set from profile likelihood test statistics. And this measurement sets the most stringent limits on these parameters, which are the ones in which the operators are mixing the B field, or 2B fields, or 1W and 1B field. So the next one is a W set and same sign WW analysis, also in these BBS topologies. In this case, the same sign WW was chosen because it's the cleanest channel in terms of electroweak and to QCD background ratio. So the uncertainties arising from the background estimation are better under control. The APGC limits were obtained from fits to the transfer mass of the boson system distribution, as you can see from this plot in this slide. And the anomalous quartic gauge couplings was performed with the Evoli basis. In this case, they needed a kind of unitarization scheme, and what they did is just to cut the EFT integration at the unitarity limit. So apart from this limit onwards, what they did is to set the EFT prediction to the standard model value. So these are the limits that they could set. In general, they represent an improvement with respect to other leptonic measurements of WZ and WW. However, as in the case of the ATGCs, the semi-leptonic final states are usually more restrictive and put in more stringent constraints. So the last one from this anomalous quartic gauge couplings is the set BBS analysis from CMS. They were looking at the 4-lepton final state with 2 high invariant mass diet system. This analysis is statistically limited, and only evidence of this process is achieved. However, it's sensitive to the charge and neutral current operators, and it could set the most stringent test to the neutral current operator, so the last 2 ones that you can see from the table. And what they did is just to consider this fit up to the unitarity bound that was estimated from this theoretical paper. So now we switch to the Higgs sector. So in the Higgs sector, we also have anomalous H2BB couplings following a similar strategy, extending the Lagrangian or the vertex function with the terms that you are interested in. However, moving to an EFT, there are several bases that are or have been in use for the interpretation of the results. In general, when we have 2 complete bases, we always can find a mapping between them. However, this is not always the case, since some of the bases are just restricted to Higgs interactions as the Higgs bases, but the other ones that are in use are the Barzel bases or the strong interacting light Higgs bases. So I start with an atlas measurements from Higgs to BB, in which the Bs are resolved. This is a measurement of simplified template cross sections using the full run-2 datasets, and for the interpretations they use the Barzel basis, again as implemented in the SMETSIN package that I mentioned before, and they assume the flavor universality model. And one interesting thing of this analysis is that they did not choose a priori which was the set of EFT parameters that they were going to constrain. However, they retain those to which the measurement has more sensitivity for the 1D fits, so neglecting the correlations with others. But they also try to perform non-simultaneous fits, and since they have 5 pins in the measurement, they choose the 5 directions to which the fit was most sensitive. And to find this direction, what they did is to diagonalize the EFT matrix. However, since the EFT complete fit will not converge because of a strong correlations between the parameters, what they did is just start from the Fisher information matrix of the measurement, which is just invariance of the covariance matrix, and propagate the EFT parameterization and diagonalize it. So this methodology was explained in this pub note, and what they showed in the plots in the right-hand side one is just the limits with the linear and linear plus quadratic terms, which are somehow relative in some of some important in some of the constraints, but not changing a lot the constraints themselves. And also in the left-hand side, the plots showing the impact of this eigenvector decomposition within its uncertainties coming from the fits. So the next analysis is the BP, but in this case, the BP system is boosted. So the strategy was very similar as in the result analysis. And in general, better sensitivity to EFT was expected at higher transfer momentum. However, the constraints were there not as much improved with respect to the result analysis, most likely because the uncertainties also in the low PT regions weren't so much higher.
Anna,
So now
I'm very sorry to interrupt you. 5 minutes left.
Okay, thanks a lot.
Mm-hmm.
So this one is Higgs 2,4 lepton analysis from Atlas. It's also measurements of simplified template cross sections, and here they are not restricted only to VH measurements, but also to other production modes like GGH or TTH and BBF. For this interpretation, they really chose which were the main operators that will affect the measurements and the ones that they wanted to constrain. But there were several nice studies in these measurements. First, it was the checks of the linear and quadratic terms, and also inserting CP even and CP odd operators. So in the table, you can see all the operators that they consider together with the structure of each of them, and whether they appear in the decay or not, and in which production mode do they have an impact. So in general, as the STXs are just defined by setting cuts on CP when observable, the CP odd constraints will only come from the quadratic terms. And in this case, the quadratic terms were a bit were shown to be more relevant than in the Higgs 2BB analysis. Apart from this, they did also a nice study on the acceptance effect. So the 4 lepton selection that is done at the analysis level can be affected by the EFT operators. And this was considered in this analysis, and what you can see in the left-hand side plot is just the effect of the acceptance from CP even and CP odd operators, or CHWB even and odd, and without a large difference in the acceptance. However, when we see these top right-hand side plots and check the difference in the yields with and without the acceptance, we see that the impact is quite large. Then the limits were extracted using 1D fits. And then the correlations were studied through 2D fits. And what they showed in the 2D fits is that there are non-trivial correlations between most of the parameters. And this is just because these acceptance effects were estimated in a quite complicated way, and they are not linear. The next one is also a CMS measurement in the Higgs 2,4 lepton final state, but this is a dedicated measurement we're looking for anomalous couplings, and it's quite complete in this sense and a bit different to the previous ones. So they look for CPA violations in the TTH and GGH couplings. They also looked for 5 anomalous couplings in HPV, considering some simplifications to conserve custodial symmetry. And on top of that, they also could do an EFT interpretation using the Higgs basis. So I did not show here any results regarding the 3 first points, and only the EFT interpretation. which was performed with the Higgs basis, and these are the constraints that it could get. So the next one is Higgs to the photon analysis. This is a measurement of differential cross sections. And the interpretation was done in two different phases, the Varsa phases and the Silge phases. And as in the case of the set electroweak production, they introduced CPO observables to constrain these CPO operators already at interference level with this sign delta phi yet. And here the operators are studied. So the operators that are studied are the ones that are modifying mainly GGH, so this CHG, and the Higgs to gamma gamma decay, so CHB, CHWB, and CHW. Then the limits were extracted from 1D fits using just a chi-square approximation. So the results I showed before were using the Varsa basis. Here are the results using the Silge basis together with some correlation plots. And in some cases, you could see some of these banana-shaped correlations, and this is just because the interference for this operator is destructive. So it's negative, making the yields to be negative, so not allowed. So the last analysis is the CMX Higgs combination. This is a combined measurements of the productions and decay rates of the Higgs boson and its couplings to vector bosons and fermions. The interpretation was done with the Lagrangian, so this is the same as the Silge basis with flavor universality. And what they did is, as in the previous analysis, is to reparameterize the signal strength in terms of the EFT coefficients. So here only the interference terms were considered, and they chose only those operators that are not tightly constrained by other data. The acceptance effects just from the cuts that are applied to the decay channels were not considered for this analysis. However, they did an interesting study by comparing the limits extracted from simultaneous fit, likelihood fits, in which all other parameters are profiled, and 1D fits in which all others are fixed to the standard model, as you can see from the table. And of course, these 1D fits are always more constraining, but probably showing less the reality. So this brings me already to my summary. So in general, many different precision measurements have been used in the electroweak and Higgs sector to constrain BSM effects in terms of EFT or anomalous couplings interpretations. In general, there is a bit of difference in the methodology, but all of them are tending to include an EFT interpretation, taking into account dimension 6 operators. Of course, this cannot be the case for the anomalous quartet gauge couplings or neutron triple gauge couplings. Unfortunately, no deviations from the standard model has been found in any of the analysis, and in general, the tendency is that the constraints of parameters has improved significantly with respect to previous measurements. This applies mostly to the electroweak measurements. In the case of the Higgs, it's a bit more difficult to compare since there are different conventions and ways to do these interpretations in use. In general, all the operators or effects to constrain are typically chosen a priori based on symmetries or previous constraints. But when we move to an EFT, the parameter space shows large correlations in general because we have many operators contributing mostly everywhere because they come to shift to input parameters or the redefinition of the fields. And in general, there are different assumptions considered between different analyses and experiments. And just to finalize that, it would be nice that in the future we can converge to a more easy to compare strategy so that it would ease the way to global fits also from the experimental collaborations. And that's all from my side.
Thank you very much. There is a question from Kaimuddin Hank. The question is, what is ultra-relativistic heavy ion collision? And what is ultra-peripheral collision? What can you say?
Is this from my talk? Because I think I didn't talk about ultra-peripheral collisions.
I also was surprised, but maybe I decided maybe I missed something. Okay, so that's not appropriate to your talk. Thank you very much again.
Yes, can I ask a question?
Sure.
Yes.
I have a question for slide 12. Is it possible? Yes, and
It's taking a bit of time to check. Okay.
yeah, this plot on the left, you have you have QQ to ZZ and Z gamma. Is it the combination of ZZ and Z gamma or not?
I think it's just that it's set. You cannot see it, but it's set gamma star, so you cannot
the
really
virtual
see.
one.
Yes. So that's why I think in general they said that they require them to be on shell. So I'm not exactly sure which is the requirements in the analysis for this second set, but I think it's just the virtual contribution that you cannot separate.
Okay, so this table is not for combination. It is for
No.
Mhm.
Yeah, it's
Because
separate.
it can be combined actually in the future, because ZZ and Z gamma use the same EFT parameters. So
Yes, sure, and it would be quite interesting.
thank you.
Okay. So
Sorry,
Anna
can I also ask a question?
Okay.
Sorry. Yeah, I have a question about Atlas for lepton analysis. So if we can just go back to the limits, actually.
For the Higgs-2 for lepton of Atlas?
Yes. Yeah. Okay, so according to this EFT coupling, so almost all of them can be varied independently without problem, but the question is about CHWB. As is shown in the ZJJ analysis, so these couplings affects also some electroweak processes, and what is the most important, it affects the background of this particular channel. So by varying this parameter in such a wide range, it also contributes to the background of this channel. So do you by chance know what is the logic to include this parameter to the scan in this oversimplified way? Because if we take into account the modification of the background, the limits will be different from the one which you obtained.
Yeah, so the logic, I think in the end, they decided just to constrain the ones that they were sensitive to. They are so far, in general, in none of the analysis that I have shown, they take into account the EFT and from the background. That will be another interesting thing to see. And I think we know that from electroweak measurements, this parameter is much better constrained than this. But there was there are like many different things that could be taken into account. That at the moment, I think we are in a very early stage of this CFT, because in general it's quite complicated to have all the computations and so on.
Okay, thanks.
Are there any questions? No. Okay. So Anna Kuyeta, thank you very much for your excellent talk, which caused such a big interest in the audience, as you see.
Thank you.
Okay, so let's move further. We have the last speaker, the last but not the least. That's a trivial expression. That's the time to say it. So it's Pavel Pakhlov, and the title is Recent Experimental Results in B Physics. Please, 30 minutes.
Okay, can you hear me?
Yeah, very well.
Okay, and let me now show you my screen. Just a moment. I will take. Okay, can you see? Can you see the slides?
Yeah.
Okay, that's nice. Okay, my talk is about the flavor of physics, the recent result in particular in B physics, because I think B mesons are the most interesting part of the flavor part of the standard model. And I would like to say from the very beginning that this year is not very rich of new results in flavor of physics. And this is because the dedicated experiment BEL2 at Super B Factory has just started to take data. They already achieved quite high luminosity, so they beat already the previous record in plus and minus luminosity, which was done at the Bell experiment with KKB accelerator, and they take a lot of new data, but still, of course, a few months of data taking in this year cannot be competitive with the previous 10 years operation of 2B factories. Therefore, new results in B physics, and in the same time, LHCb, which is the main competitor to Bell 2, because Bell 2 just started and there is no big competition, they also relax still. Therefore, we don't expect many results this year, but I hope very much that in the very nearest future, we will have a lot of new results in B physics. Okay, let me start with motivation for study of B mesons. Let me remind you that standard model is really very successful theory because, of course, it can be proud of many predictions that was confirmed by the experiment. Now all particles predicted by standard model have been observed, and all symmetries, which are basic symmetries of the standard model, are confirmed, and the mechanism of symmetry breaking is established after observation of the Higgs boson, and this confirmed really that the ideas of standard model, which arose 50 years ago, are really confirmed now with experiment. But in the same time, the standard model is certainly not the final theory in physics, and it has a lot of intrinsic problems. It has a lot of some problems with experiment because it cannot explain dark matter, dark energy, and baryogenesis. Therefore, we expect that new physics will appear soon because the problems of the standard model are arise already at the level of 1 TeV scale, which is already close to possibility of experimentalists to test the scale. And flavor physics is important part of the standard model because it's very rich of some phenomena which are not explained by the standard model because it's a lot of free parameters here, a strange hierarchy of the lepton masses and fermion masses and fermion mixing are not explained, and standard model cannot answer many questions which are very it's obvious to ask why we have only 3 generation, why these certain free parameters are really such as they are, and of course it cannot explain the hierarchy of and smallness structures in the of these parameters. And flavor physics, of course, provides an important part to study new physics at very high energy scale because of loop and box diagrams which are govern some decays of B mesons. And important part of the standard model of the flavor physics is the study of CP violation, because CP violation is really related to box and loop diagrams where the new particles can contribute, and the key importance for testing of new physics are B mesons, where these diagrams are increased. At least they're not suppressed like in charm physics, for example. So the CP violation studies, it's already 40 years history of the ideas of Carter and Sander, who suggested that CP violation in B mesons should be large and can be measured and can be used for study of the standard model parameters. So they observed that B mesons, B cores, which corresponds to the third generation, should decay to the light quarks via some intermediate states. It requires 2 W emissions, and in result, the final states with light quarks for B meson and B0 bar are the same. They found that why B and B bar decays result in the same final states, and there is a possibility for BB bar mixing, like in case of kaons, they can generate CPI symmetry, which was estimated by Carter and Sander to be as large as 10%. And now we know that it was too pessimistic estimates, because the CPI symmetry in B meson sometimes reach 100%. And of course, CPI violation is not only an enigmatic phenomenon that should be studied, but it's also effective tool to search for new physics. And you can see these two plots, which was prepared by CKM FITER collaboration, showing the possible contribution to BB bar mixing diagram from new physics. You see delta MD corresponding to mass difference between two CPI eigenstates in B mesons is a result of these box diagrams, and it's consists of standard model part, and maybe some new contributions from for example, supersymmetry can result in some deviation of this delta MD from the standard model prediction. And this contribution of new physics 20 years ago, can be as large as it can be much larger than the standard model from experimental constraint. But now, after work of two B factories, Babar and Bell, it was constrained to be at least smaller than standard model contribution. But you can see the ratio. So the contribution of new physics can be as large still as 30% of the standard model contribution. So the B physics remains to be very interesting, and new constraints are important to constrain the new physics. And when we're searching for new physics, we should require that the luminosity should be as high as possible, because here there is some citation from, sorry, it's in Russian, from the great Russian physicist Lev Okunin, who told that 50 years ago, he was insisting for continuing an experiment in Dubna with K long, searching for decay of K long to pi plus, pi minus. This was before the observation of CPI violation by Cronin, Fitch, and company in the United States. And the competitive experiment in Dubna already reached the upper limit corresponding to the effect that was observed 1 year later by American physicists. But unfortunately, this experiment was closed because the director of Dubna that time decided that it's not has no big chance to observe something new, and it was closed just before they probably could observe CP violation. And now we are in a very similar situation. We work with B mesons that probably can be sensitive to new physics at 1 TeV scale, and we should study as perfectly as possible. And for this, the B factory, super B factory, was built at KK Center in Japan. So the idea was to increase the luminosity by at least a factor of 50 in comparison with the previously achieved by experiment Bell. And the idea how to increase this statistics to increase the luminosity was there was a simple method to increase currents, but it was calculated that to increase currents, KK needs a special power station, which will be probably one of the most powerful in Japan. And the better idea was to reduce the size of the beams. So they use the nanobeam scheme for colliding that allowed to increase the luminosity by a factor of 40 in comparison with Bell experiment. And the new Bell detector, which is use the new subsystems, almost all inner detectors were replaced with new one to cope with higher background level, higher radiation level. and to have better performance. We have much better now the tracking with the new vertex detector with much larger drift chambers and much better system for identification of charged hadrons. And of course, B-physics remains an important part of the scientific program at LHC. So the LHCb detector is a dedicated detector, especially designed to study B-mesons, and for CMS and ATLAS, the B-physics remains an important part of the scientific program, and we will see this in some examples of the last year. And if we talk about searching for new physics using CPU evaluation as a tool to probe the scale of new physics at 1 TeV and higher. One of the most illustrative part how to search for new physics is a study of unitarity of the CKM matrix, which is represented by several unitarity triangles, and this is one of them, which is related to B-meson decays. And we can measure, in B-physics, we can measure sides of this triangle, we can measure angles, and if we see some deviations of the triangle from some deviations between the measurements of the angles and sides, or by sides only, or by angles only, we can conclude that there is some contributions which is not controlled by the standard model. For example, the new physics can contribute to the box diagram. In this case, the angles can be different from those expected from the standard model CKM matrix production. And in this case, the sides, which are mostly measured from three diagrams, except for VTD, which is just impossible to measure from three diagrams, all other sides are measured using 3 decays, and angles are measured with, almost all of them are mostly measured with box diagrams. Therefore, the contributions which comes only to box and not coming to tree will result in some deviations. So the task is to measure this triangle as much as accurate as possible, and we will see how it's done. So the measurement of angle beta, which is one of the most precisely measured parameter of the standard model, you can see the result from Bell, and you can see comparison between the 3 most accurate experiments, which include Babar, Bell, and LHCb. And LHCb also produce some good results, but still they could not beat the Bell and Babar. And this is actually quite surprising for me, because the statistics at LHCb is quite high, and probably they just need to update this result to have accuracy better than Bell and Babar. I hope this will be in nearest future. And if we talk about the measurement of another angle alpha, it requires much more complicated analysis because of penguin pollution of the measurement, because in addition to the tree diagram being to pi plus pi minus, there is a penguin contribution which can result in the same final state, and the phase from penguin contribution is different, and the ratio of penguin to tree diagram is not known. It cannot be predicted theoretically. This results in some this results in situation when we measure some angle, but we don't know how it's related to alpha. The idea was suggested by theorists Granau in London. They proposed to use isospin conservation in strong decays, and using isospin relation, it's possible to extract alpha almost without model dependence. Of course, there is some systematics from the isospin assumption, but if we measure 6 final states, including pi plus pi minus, pi plus pi 0, and pi 0 pi 0, we can extract alpha without model dependence, and this is really done during 10 years of operation on B factories, and in future LHCb can contribute to measurement only of the charged final states, improving this accuracy, but BEL2 will contribute to all possible final states, including neutrals, which are important for measure of angle alpha. Therefore, now the accuracy, as you can see, is about 2 or 3 degrees. And in future, in 5 years, it's expected to be smaller than 1 degree. Okay, BEL2 has shown this year the first results using very small data sample in comparison to BEL. You can see this is just 3% of the data that was achieved, that was taken by BEL. But already with this data, the first results are available. So BEL2 measured the parameter sine of 2 beta in CP violation parameter in B integer psi 0 KK0. Of course, the accuracy is still much worse because statistics is just taken during a few months. And the first results of reobservation of B into pi plus pi minus and pi plus pi 0. It's also shown at the last ICPPA conference. And now I will talk about angle gamma, which is measured in the decay of B into dk, using the fact that sometimes we can distinguish between D0 and D0 bar. If, for example, D0 decays into CP eigenstate like K plus K minus. In this case, we don't know which 3 diagrams, the first or the second one, contribute to this final state, and the interference, because there is a relative phase, weak phase between them corresponding to gamma. This resulted in CP violation. So we will see, for example, for B plus and B minus, different probabilities of the decay into dk when D0 is not distinguished from D0 bar. The new method was proposed by theoreticians, and it was actually used by BEL before it was suggested by theoreticians, is to use the final state K short pi plus pi minus, which has a very high branching fraction, and this is even more interesting results because you can see the relative phase between different parts of the Dalitz plot, which is okay. The Dalitz plot for D0, tagged as D0, is shown at this this picture. You can see very nice interference pattern here when K star and rho meson interfere, and even K star bar, which from WKB suppressed decays is seen here as a band, horizontal band here. And the accuracy, present accuracy is limited by statistics. You can see that angle gamma is measured already with relatively good accuracy. And if we compare with alpha and beta, it is still the worst measured angle. Therefore, improvement here is very much important. And it was done by LHCb just recently using 3 methods. The first one is to repeat those used at B factories, that is to have B meson into dk with Dalitz analysis of D0 decaying into K short pi plus pi minus. And they measured the angle gamma, which is consistent with the previous result from Bell and Babar. Accuracy, you can see, is 5%. But they also can use another method, is to use the decay of B0 to D plus pi minus. Again, there is a possibility of interference due to BB bar mixing and due to the fact that D meson can be produced from W decays to D plus or from the B part of the B mesons. It means that B0 can decay into D minus pi plus and D plus pi minus with different amplitudes, but it's not so much important. Important thing that the relative phase between these 2 diagrams is related to gamma, and we need to study indirect CP violation to measure gamma, and you can see the result. There are 2 regions which are allowed by this study at LHCb, and it's quite typical situation when there is a big ambiguity in the results, because here again we have we measure some trigonometrical function from the parameter which we are interested, and therefore there are some twofold or fourfold ambiguities in the results. Important thing that LHCb is also used the third method. They use B sub s decay into D sub s k plus or D sub s chi minus. Again, there is a possibility for interference between them because of B sub s mixing. The study is more complicated in comparison with direct CP violation, because you need to study time-dependent CP violation with tagging and with a perfect resolution of vertices. But for HCB, it's possible to do. And they measured angle gamma, which is more than 2 sigma different from B sub s from those measured in B plus and B0. You can see the picture in the right bottom part of the slides. The red one is probability to measure angle gamma in different modes, and there is a more than 2 sigma disagreement between these two measurements, which can be quite intriguing because this probably can indicate that in B sub s we have some extra phase which appears from the B sub s mixing. But of course, this is just 2 sigma. We need to wait for new data from LHCb, which hopefully appears next years. And if we can see now the situation, the history, the situation with the unitary triangle measurements during the last more than 20 years, we can see that before B factories, the allowed area for the upper apex of the triangle was extremely big. So then in this year, 2B factories started to work, and they improve accuracy. Finally, before the start of L2 and new measurement of LHCb, the situation was quite perfect. We can see that all measurements are consistent, but the consistency is still at the level of 10%, which allow to the contribution of new physics at this level. Therefore, the improvement in accuracy is important. And now I will talk about some new results from 3 LHC experiments, LHCb, Atlas, and CMS. And first one is a study of CP violation in B sub s decay. B sub s decaying into GPSI 5 is important channel. It's a golden mode for B sub s because according to standard model, the CP violation in this decay should be perfectly consistent with 0. The prediction of the standard model is less than, sorry, I haven't shown this. This is milliradians. So it should be almost 0. And the predictions are 0, and the experiment this year it was done at CMS. You can see the huge number of events of B sub s meson candidates at the left plot, and their time evolution fitted with possible CP contribution is shown at the right plot. And the result that if we combined, CMS combined the first data and the last data, this red ellipse corresponds to the allowed area for delta gamma, and B sub s measurement is consistent with 0. And here the results from other experiments, all of them are consistent with 0.
Pavel, I'm sorry, 5 minutes left.
Okay, okay, I will finish in 5 minutes because I'm already close to conclusion. The new measurement, another interesting channel is B sub s decaying to mu plus mu minus. It's a benchmark final states because in addition to standard model, which is extremely suppressed for this final state, the new physics, for example, supersymmetric particles can increase this final state significantly, because for B mesons, it's suppressed by chirality of muons in the final states, but new physics can just be not left-handed and increases final states significantly. And now Atlas is measured this final states. It's also see the signal with a high significance. CMS is updated their results, and you can see the table. You can see that for B sub S 2 mu plus mu minus, all three experiments see the signal, and all of them has the measured branching fraction exactly 1 sigma below the standard model expectation. It can be intriguing. Of course, the significance is still very low. For B0, this branching fraction is tiny and is still not seen. You see the upper limits from CMS and Atlas, as well as also consistent with zero result from LHCb. Interesting result from LHCb for lepton flavor violation in B decays. So they improve the upper limits, for example, for the decay of B plus into K, mu plus E minus. You can see there is no even background events in their contribution, in their distributions for these final states, and their upper limit is almost 2 orders of magnitude, okay, 1 order of magnitude better than previously achieved by Babar. Interesting results in the that LHCb can reconstruct the final state K plus mu tau. It's difficult because tauonic decays are always with neutrino, but they use the special trick. They use B sub 2 tagging, so they try to reconstruct B plus decaying, which is the product of the B sub 2 decaying to B plus K minus, and they see no signal here, and the upper limit is better than Babar, already moderately improvement compared with Babar, and also B0 and B sub, B0 and B sub S0 decaying to mu tau. It was also for B0 done by Babar, and LHCb improved it by a factor of 2, and for the first time measured the upper limit for BS into mu tau. Finally, my last physical slide is the steps for studying of the photon polarization in penguin decays. Again, important contribution, important task for LHCb and Super B factories is to measure the photon polarization, because in the standard model, the photon from this decays is always left-handed, but any new physics can change the situation, and right-handed contribution can be also contribute to the final states with photons from B hadrons decays. Important thing, LHCb for the first time observed the radiative decay of lambda B to lambda gamma. It's very nice channel because the photon polarization is difficult to measure. Yeah, you need, for example, to use photon converted into plus and minus, which is very difficult to measure because you need to measure the plane of conversion. But for lambda B to lambda gamma, you don't need to touch photon. You can measure the polarization of photon using lambda, because lambda is fermion and lambda B is fermion, and the photon polarization is correlated with lambda polarization. But lambda polarization can be measured because of p violation in the decay of lambda to proton pi. Therefore, potentially this is a very nice channel to measure the polarization of photon. Unfortunately, now the statistics is too low. It's only 65 events observed by LHCb. But when the statistics will be, say, 100 events, they can really make important measurement of polarization. Another possibility to measure polarization is to study the decay of B sub S to phi gamma. And here you need the time-dependent analysis, because there are three contributions which are related to chirality of photon. S and R delta and C can be used to search for both new physics and measure of polarization of the photon. LHCb made these results and shown last year. You can see the numerical results here, and I would like to say that all of them are consistent with the standard model still. So my summary, there are a few slides of summary. First of all, the present situation with contribution of new physics to box diagrams are shown at the left plot. And already in 5 or 2 years, we improve the upper limit for the new physics and constrain the new physics contributions already at several TV scale by upper diagram. Or alternatively, we observe some new physics if we found that the contributions in the box diagrams are different from zero. I would like to say about Bell-2 experiment, which has just started to operate, just started the data taking. And in 5 or 7 years, the accuracy in measurement of all angles will be improved by a factor of 5 or so. And after that, we can hope that we can observe the new physics by discrepancy in the measurement of the unitary triangle parameters. And finally, I would like to show that Bell 2 has already achieved the luminosity higher that okay, it's a factor of 3 higher than previously achieved by Bell, and it's still improving from month to month, from day to day. And in Bell 2, after summer shutdown, will start in few days to take the new data. Okay, thank you very much. That's all what I'd like to say to you.
Thank you very much, Pavel. There are a few questions in chat. Anyway, the first one, why CP violation is seen worse in D mesons? Is it due to CKM matrix?
It's mostly due to G mechanism, because the contributions from box diagrams, from loop diagrams in charm mesons is suppressed by G mechanism. Yeah, because of course, in case of B mesons, the contribution of box is cutted by T quark mass, which is much higher. In case of D mesons, it will be cutted by B mesons. It means already by a factor of 20 squared smaller. And also, in case of beam mesons, CKM box diagrams are not CKM suppressed.
And another question, which is not appropriate to your talk, but I cannot skip it. Any recent results in glue ball searches? Yeah. Looks
Yes,
like the guy just
there are new results from LHCb. I haven't mentioned this here. It's I'm not sure that they're related to glue balls, but they observed some new resonance in GPSI, which probably means tetraquark. But I think in the question, glue balls means all exotics. Yeah.
Yeah. Okay.
So, but okay, this is not a topic of my.
Yeah. Okay, so no more questions. So Pavel, again, thank you very much for your excellent talk. Yeah, very informative. And ladies and gentlemen, it was the last report of our first plenary session. So plenary session is over. Thanks, many thanks to everybody in the audience, and good luck with the conference further. Goodbye.
Next plenary session will be at 3:30.
Okay. Okay, bye-bye.
Thank you very much. Bye. two other presenters, Mike Murray and Paul Grenis, presented between us. So I will start my presentation. Okay, my talk devoted to review of two-phase emission detectors, research and development, which actually have 50 years of history this year. And this talk devoted to the memory of great scientist Boris Anatolyevich Dolgoshein. In his laboratory, I started my career also about 50 years ago. And at this first slide, I show his forward to first book devoted to technology of emission two-phase detectors, which he signed in 2009. And he said at that time that 40 years ago, at that time it was really 40, now 50, a group of Russian physicists investigating electron emission from liquid argon were able to formulate the unique properties of a new detector technology that could be developed employing this effect. They call these detectors emission detectors. Emission detectors seem to have found their niche in low background experiment search for cold dark matter and low energy neutrino interaction. The further development of this interesting class of radiation detectors may enhance the arsenal of modern physical methods and other exciting fields like the neutrino-less double beta decay search, solar neutrino physics, and possibly in many new areas that cannot be satisfactorily served with existing detector technology. And this year also we celebrate 90 years of this great physicist. And I'm happy that I have a chance to mention about this event in my presentation. Back to 50 years ago, in laboratory headed by Boris Anatolyevich Dolgoshein, his PhD student Boris Rodionov and graduating student Vadim Lebedenko investigated liquid argon like a possible medium for streamer chamber. I would like to actually note that by that time, laboratory headed by Boris Dolgoshein developed and built biggest streamer chamber in the world. It was 8 meters long streamer chamber. It was designed and constructed at MIFI, Moscow Engineering Physics Institute, and with particular goal to find out W boson. And detector was installed at later at in 60s, I would like to say, at Serpukhov accelerator. At that moment, it was biggest accelerator in the world. And with hopes that they, using this streamer chamber, discover the W boson. Unfortunately, it's not happened just because, as we know, that mass of this particle was slightly larger than energy of proton accelerator built in Serpukhov. Anyways, streamer chamber had a great history. They investigated, they measured the polarization of muons and investigated more other physics And at that time, they start to think about development of this technology in direction to increase density of working medium with attempt to detect low ionizing particles and detect complicated events, including gamma rays and others. So on this reason, there are two ways to solve this problem. One way is try to build a streamer chamber with spark discharging along the tracks in very dense medium, like liquid noble gas, or another approach that to use low temperature with normal pressure, but because of low temperature, increased density. The second way was developed in ICPPA in the laboratory headed by Lyubimov, but Dolgoshein and his young colleagues developed the way to detect particles in liquid argon first. And they discovered unexpectedly, by the way, that ionization electrons can be extracted from liquid argon, like shown in this picture. For example, using a structure like that is cathode, anode, gate between them below the surface of the liquid. And if we have ionization here, like from sharp needle shown here, or alpha particle source, which produce ionization in liquid, and then we have applied electrical field between anode and cathode, and these electrons come to the gas. And in gas, we know how to detect electrons and how to detect tracks of the high energy particles. That was the idea. And they built the first device in this approach. Was built in 1973. It was liquid argon spark emission chamber. So the design of the detector shown in this left picture. So we have cathode with alpha particle installed in on this surface, and covered with liquid with cathode, which could be in the gas phase or could be even also in the liquid. You can measure ionization current, for example, and specify the effective ionization yield from tracks of alpha particles or whatever particles you use. So in this right picture, you may see the picture, actually distribution of alpha activity over the source installed in the center of the chamber, not like here shown on the side, but in the center of the cathode, like here. So, and you may see that there is a cathode which built from many wires, and each wire actually placed in cathode placed in the gas in this specific experiment. And when electrons extracted in the gas phase, they can generate spark discharge in nearby the wire. Many of these sparks actually form activity of alpha source. So the ring around, that is effect of shape of the cathode. Cathode has a kind of actually has curved inside position of alpha source, and this curve reflected the light of all the sparks and formulate this nimb around the alpha source. But it is actually just effect of configuration of detector. Most important that we can see the alpha particles like intensity of this light proportional to activity of ionization. So that is what first emission detector, which allow to visualize the distribution ionization particles on surface of the, in this case, alpha particle. So this first publication at Jet Letters in 1970. So we consider this publication like first publication related to two-phase emission detectors, like we call them now. So the next step in this direction was to follow idea to build a streamer chamber, but in this after this discovery that we can extract electrons much easier to extract electrons and or track of ionizing particles from condensed noble gas in gas, and in gas to have just mode of normal streamer chamber. So you have anode with high voltage pulse source, which applied when particles come through the layer of noble gas, condensed noble gas, with delay needed to extract electrons in gas phase. And this narrow gap above the condensed phase, we have generated the track of particles. It was very nice tracks, very dense, with very small sparks. Streamers. It formed a very like continuous track. Also, this device shows that we can detect interaction of particles, high energy particles. On the bottom picture, you see the particle. In fact, it comes from this side, interact inside the condensed noble gas, and then products of this interaction, like many tracks of particles, pass through the condensed noble gas medium and left the short tracks over here. So because the layer was pretty thin, about 5 millimeters, an experiment was established at ITEP, synchrotron accelerator, proton accelerator at secondary beam when the pions come through the detector and their position selected with scintillation counter. So that is normal configuration for high energy experiment. So when particle comes through the detector, trigger system generates the high voltage pulse, and we, after delay for drift electrons in their emission, we generate the track. So this idea was pretty good working. Unfortunately, it was understood, and actually later this principle was built big emission streamer emission chamber based on liquid krypton, because we didn't have xenon enough at that time. We call this detector HOP, or Nadezhda in Russian. So this picture of this device shown here. So the streamer chamber above the liquid tank is liquid, about 15 centimeter and about 50 centimeter diameter. High pressure generator, pulse generator, which applied high voltage pulse in this two-gap gas area. And when electrons come through the liquid, we can generate a streamer track. This device was pretty big for that time, and built it just before very difficult times for our science in Russia. But anyway, it was tested with laser. Streamer chamber was working, and it's shown this track from laser in neon gas with addition some low ionizing vapor. And also bottom part also was tested with thick layer of liquid krypton. It was measured efficiency. It actually was very big at that time device for to make electrons effectively drift and emit in the gas phase. Unfortunately, the device was not finished in testing at the beam because actually all scientific activity at that time stopped at ITEP. But anyway, it was shown that we can build like this chamber. In parallel with development of track detectors, was very big efforts to investigate possibility to detect electrons extracted from the noble gas and other condensed dielectrics media by electric field and effectively detect them. So not only in Russia, also in France, Lancier, Signer, and Moretti, they also investigated possibility to build a two-phase detector with extraction electron in gas phase and detection with photomultiplier electroluminescence flash in the gas phase. In Russia, in actually joint efforts, MIFI and ITEP was built very small chamber with working volume about 1 cubic centimeter, which can be filled with different liquids, solids, krypton, xenon, methane, their mixture, and others. With PMT, looking through the glass walls, what happened inside, and we can see first scintillation when alpha particles activated condensed working medium, and after drift time, electroluminescence flash when electrons drift through the gas. With this detector was investigated efficiency of electron emission and different media, like I said. Plus, it was shown that using in this work and in this work, we can use photomultipliers and detect two signals: scintillation, which happen in the moment of interaction radioactive particles with medium, working medium, and delayed, but also actually associated with this event, electroluminescence flash, which was much more intensive, will allow to exactly to measure a number of electrons we have extracted. Okay, so using this idea was built multi-channel detector, which called emission gamma chamber. And this device was built also in joint efforts, MIFI, ITEP, and VNIB, that is Institute of Medical Devices. So this device actually very nice example. That is actually prototype of all two-phase emission detectors based on xenon and argon, which is working right now. So we have, at that time, it was very thin layer of liquid or solid xenon on the top of bottom of the detector, and not gridded electrode above, an array of PMTs installed through the windows above this medium, and that allow to detect, for example, gamma rays. That is actually image of the lead mask with holes, which was placed in front of the detector with the gamma source, which was cobalt placed below the detector. So we can see that the device has position sensitivity and quite a large area. It was tested with solid and xenon and liquid xenon, and proposed to use for nuclear medicine for imaging of gamma ray sources inside the human body. And this actually idea about this time, first paper was published about possibility to search for dark matter using two-phase emission detectors. But at that time, because masses of particles which can be candidates for WIMPs considered in the range of 110 GeV, for working medium was proposed to use liquid isooctane, that is saturated hydrocarbon, which work at room temperature and provide pretty good gas gain for electrons extracted, about 10 to the 4. And so it was proposed to use for detection of dark matter. But soon after that, actually in 15 years, it was clear that dark matter should have more heavy particles, and this direction was forgotten. Instead of that, intention was return to xenon, and this example of using xenon, which utilize two signals: scintillation in moment of interaction, radiation with working medium, and electroluminescence flash after electrons extracted in the gas, with a position-sensitive array of PMTs installed above. So we can see that the distribution, that also image of lead mask with holes, regular holes, irradiated from the top with energy 122 keV. And you can build not only XY distribution, but also Z distribution. For every point you see, you can measure not only position in the area of the sensitive area of the photon multipliers, also position in the depth of the detector. So 3D positions detector. It was very exciting result. It shall allow for nuclear medicine speak about possibility to build Compton camera, Compton events shown over here. I will not time to discuss about this, but that is very interesting approach. Actually was protected by patent in the United States. And at that time, we understood that if you use liquid xenon in a large volume and use two signals, scintillation and electroluminescence, like I described, we can build device which can select event happen inside the detector. So we so-called wall-less configuration, so we can avoid background associated with radioactivity of surroundings, walls of the detector, surround the material around the detector. So we can select events in the central part because of 3D sensitivity with like this technology of detection. And it was proposed at 1995 to use this technology for detection with very high sensitivity to electrons, down to single electrons, with effect of cell screening from background to search for rare events and weakly interacting particles, starting from neutrino and dark matter also was mentioned in this work. And in fact, that was this development opens the way for development of high two-phase emission detectors for dark matter search. I will not stop very detail because of limited time on all this development. That one of the first detectors, this kind, Xenon 10, this first result, real result shown here with scintillation S1 and electroluminescence S2 signals with 3D position sensitivity. This allows to have a large enough detector, like about ton. We can very effective shielding from neutron background, like shown in this picture. So, and this was very exciting time. And actually, after that, a number of detectors of this kind was built over the world, starting from Xenon collaboration, Zeppelin collaboration in England, LUX in the United States, DuckSite in Italy, collaboration working in Gran Sasso, in China, Panda X device, and this device actually, all this direction now leading in best limits for possible mass of the dark matter particles in form of weakly ionizing particles, WIMPs. And the best actually device, which is close to actually start working now, that is LZ, joint collaboration LUX and Zeppelin, which already use 7 tons of liquid xenon. We probably know, will not talk about details. We know about this pretty well. Eventually, we have limits for existing of WIMPs in scale of cross-section and mass, which if that is limits given different experiments. And we see that the last prediction all given by two-phase emission detectors. And what is interesting, all this prediction approaching to point when this kind of detectors become sensitive to solar neutrino coherent scattering. So if we go with larger mass detector, so this will be irreducible background, and actually eventually this kind of detectors become not dark matter detectors, but solar neutrino detectors. Okay, and now we have already a couple of directions to use this technology for neutrino physics. One of this direction actually developing it MIFI in cooperation with Kurchatov Institute, Dubna, and others. And this now experiment, which actually use the detector RED 100, two-phase emission detector with liquid xenon, 200 kilogram of liquid xenon, going to be installed at the Kalinin nuclear power plant, unit 4, next year. So by end of this year, the installation should go to the Kalinin nuclear power plant, and that is configuration. Detector actually inside the passive shielding, water and copper, looking like that, installed under the nuclear reactor at Kalinin power station, 19 meters distance. And that will be experiment for neutrino relatively low energy, because all coherent scattering now actually observed with neutrino with energy about 50 MeV. And now we go to see effect at pure electron anti-neutrino beam at energy few MeV. Actually, a cost for high cross-section, which allow to use a relatively small detector to detect this kind of neutrino, is very small signal, which consists of few electrons, like 2-3 electrons per event when neutrino coherent scattering on nuclei of xenon. So this detector assembling in a clean room in MIFI. So, and another very interesting approach, which that actually experimented observation of high energy neutrino oscillation generated at Fermilab accelerator, passing the way 1,300 kilometers to Sanford underground research facility, detecting in here, there is a first particle detector at entrance beam in the Earth, and secondary detector on the ground located, which actually should be 10 kilotons two-phase emission, actually liquid argon TPC. One of them suggested to be two-phase emission with amplification of signal with GEM gas electron multiplier. So that is huge detector, which you can see the figure of people over here next to this device. And but that is actually planned. In reality, at CERN now we're already on the way to test 6x6 cubic meters, so 300 tons liquid argon two-phase emission detectors. That this picture with also figure of people to compare the dimension and how it looks inside now. So that is very exciting project, and actually gold not only observe neutrino oscillation, but also proton decay and probably detection of astroparticle astroneutrino. So at my conclusion, and so what we have in this story is that two-phase emission introduced in experimental practice 50 years ago in laboratory headed by Boris Anatolyevich Dolgoshein. Over 50 years development pass away from miniature detectors with working mass about 1 gram to multi-ton detectors for solving fundamental problems of modern physics. So I actually, when I calculated the number, I was in shock. So mass of the detector increased like in 10 million times, and we can work with them, and including experiment of the second generation to search for cold dark matter, which actually use about 10 tons of liquid xenon, and actually plan to have G3 generation of dark matter detectors of this kind of two-phase with mass up to 200 tons using liquid xenon or liquid argon like working medium. And example of proto-dune double-phase prototype is largest emission detector ever built. It's already impressed with mass, and actually at the next, if all technical problems will solve successfully, we're talking about building huge, very biggest detector ever built for particle physics. That is a story of two-phase emission detectors introduced at MIFI 50 years ago. Thank you very much for your attention. Please give me a question.
There is one question in chat.
Comment.
Yes. Yeah, we have a chat. We can write down the question.
Okay, so the comment is, it is necessary to stress that RET installed at Kalinin nuclear power plant could see in principle directly the plutonium accumulation in reactor core.
Yeah, that is very nice question. We believe, actually that is shown by Mikhailian and his group in Kurchatov Institute, like in past century, that if we effectively detect neutrino using the effective detector, we may control changing of isotope content of the active zone. So when plutonium-239 generated, neutrino flux changing. So if that is very important if from point of view international efforts on limitation of nuclear weapon distribution, because plutonium-239 very effective material to build compact small nuclear bomb, because critical mass very small, half kilogram. So but there is no actually effective way to control what happened inside the active zone if this nuclear plant actually under supervision of foreign state. With detector like this type, we can use distant monitoring of nuclear. For example, like detector like Red 100 or something like that could stay on track outside the nuclear plant and effectively detect flux of neutrino. If flux of neutrino change inappropriately, we may conclude that somebody exchanged the fuel inside the active zone, and plutonium-239 disappeared. So that is effective control. Very impressed, for example, vice president of MAGATE, actually IC International Agency of Atomic Energy, Tero Variarante, who visited our lab in a couple of years ago. He said that our approach very important for international community to test independently on anybody what happened in active zone of nuclear reactor. So that is a possible application of this technology. So, okay. So if
sorry, can I also ask a question?
Yes.
Yeah. Thank you very much. This was a really interesting talk. I wonder if you can comment on the recent studies, and not so recent also, studies of xenon plus argon usage. When you dope argon with xenon and use that for discrimination, well, it's kind of the solution will save PSD properties, but you won't need shifters, spectrum shifters. So if it is, if there is any pros or cons.
Well, there are many efforts in this direction. Argon, interesting medium, plus it has, it can be used effectively for charge gain of signal. So for multiplication of electrons and taking not electromagnetic signal like S2, but amplified signal. In xenon, in pure xenon, it is not effectively. Last gain you can have in pure xenon vapor like 200 or something like that, even less. So in this sense, mixture of argon and xenon is very interesting, except that argon can contain argon-40, which is radioactive, and it is not very nice. So we have used isotopic enriched or depleted argon. So that is a very possible way. I don't know, do anybody succeed with this, but in earlier stages of this development, we try to use different mixture, and that is really can work. The question is, can we build this for particular conditions needed for a real experiment, like use isotopically depleted argon, for example, and what real gain you can achieve. So I don't know that this the problem is effectively solved right now in metal. I mean.
Thank you.
Yeah, you're welcome. Yes. So if no question, let's go to the next talk. Next talk we have Michael Murray, precision quantum chromodynamics with electron-ion collider.
Hello. I will just try to share my screen now.
Okay, so you should push on demonstration of screen and select. Okay, yeah, okay.
Is that clear?
Yeah. Oh, okay, it's fine. Just you can make it wider. Okay, perfect.
Okay. First of all, I apologize. I haven't quite figured out how to upload my talk, but I will do that later.
It's fine.
I was very pleased to get the chance to give this talk. So Boris was very kind to me when I was a young student. We were on Helios together, where Boris was building the transition radiation detector, and I was building a liquid argon calorimeter to try to measure very low mass electrons. I wish he was with us on the EIC to help us do with the electron ID. Anyway, today I'd like to talk about precision QCD at the electron-ion collider. And essentially what the electron-ion collider is trying to do is to try to make a detailed picture tomography of the proton and of the heavy nuclei in the natural state, with not a destructive measurement, but a detailed measurement of how the emergent properties of the proton emerge from the Lagrangian of QCD. So, next slide. So Einstein once asked if the inertia of a body depends upon its energy content. He originally wrote that mass is equal to E over C squared. And yes, that's true. In fact, almost all the mass of the proton comes from the energy of the gluon fields, the color fields between the quarks and the gluons, which themselves are almost massless. And I find it amazing that this incredibly intricate, complex thing called a proton somehow self-consistently arises from this rather simple Lagrangian, but it remains stable for billions of years. So it's this tremendously complex, vibrant system which somehow stays stable. Not only is the mass very not only does the mass arise from the fields, but the actually angular momentum and spin of the proton arises from the fields. So in a simple valence quark model, we think of the proton as made of 3 valence quarks, which can contribute to make the spin. But in fact, we've known for 30 years that this is much more complex than this, and we have this very dynamic system of valence quarks, C quarks, and gluons, which carry spin and also orbital angular momentum, and somehow this all magically adds up to 1/2 unit of angular momentum. So that's another thing that we would like to understand. So the full correlations of where these quarks and gluons are with respect to each other, where they are in space and time. So in QCD, we have a Lagrangian. It's not a simple Lagrangian, but it can be written down on one line. And yet this produces tremendously complex systems. So here we have a lattice QCD simulation of gluon fluctuations inside a proton, just this very complex nature of the object. So the proton is continually interacting with the vacuum. The quarks and gluons are interacting with each other, and somehow the properties of the proton emerge from these self-consistent interactions. Okay, so what are the goals of the electron-ion collider? Principally, we want to understand how the mass and the spin arise from the underlying Lagrangian. Now, to do this requires very precise multi-dimensional tomography of the quarks and gluons that make it the proton and large nuclei. So essentially what we're trying to do is to film the partons moving inside the proton. And this will require very deep synergy between theoretical methods, which are proposing as new ways to look inside a complex quantum system. Great deal of experimental work, and of course the accelerator. So we have four main pillars of the EIC physics case. So what I'm showing here is a graph, a chart of the EIC physics reach. On the x-axis is the center of mass energy, which has a pretty wide range from about 120 to about 150 GeV. And on the y-axis will be the luminosity, which will essentially map onto running time. And so initially we'll be looking at parton distributions in nuclei, one-dimensional parton distributions in nuclei. As we move up to high root S, we'll see if we can get to a extreme state of parton density, essentially a saturated state of gluons. Then as we get to higher luminosity, we'll try to look for spin and flavor structure of the nucleons and nuclei. And then at the very highest luminosities, multidimensional transverse momentum distributions and a real spatial imaging of what the nucleus looks like. So it's a very rich physics program. The EIC maps a very wide range of scales. So here we're comparing the scale of the Q scale, which is kind of, you can think of as kind of the resolution scale, how the inverse size that you can look at of the EIC compared to other detectors, other colliders. And so we see we have already a very nice measurements of the non-perturbative regime going on at COMPASS and JLab, Hermes. We've already seen the Hera detector has already measured over a large range of Q squared, but the EIC will have very high luminosity, the flexible beam energy, and crucially, it will have the polarization of both the electrons and light ions. And this really lets it get at the spin structure, which was not possible for the Hera machine. So the machine, so it's recently been decided by the Department of Energy that the machine will be built at Brookhaven National Laboratory. So we'll use a lot of existing infrastructure already. We already have a polarized ion source, a booster, then the alternating gradient synchrotron, which will serve as then we will inject into the ring, and we have already the ion ring already existent. Then we'll need to build, at the top right, we'll need to build a polarized electron source. We'll need a cooler to keep up the luminosity of the beams. So far, the funding that the DOE has committed is to building the machine and one detector. And so now we are trying to, we need to raise about another 250 million to build a second detector. So that will have to come from non-DOE sources. So that's a big effort within our community at the moment to raise the extra funds for a second detector, which I think is essential for the good physics program. Now I want to compare the EIC to other machines. So both existent and proposed. So you see the EIC has a very high luminosity. And although it has a somewhat lower beam energy than Hera, it has a very wide range of the product of energy and luminosity is very large for the EIC. So it's about a factor of 500 above Hera, which is very helpful. It also has a huge kinematic reach. So here I'm looking at the kinematics of the detector. So Q squared is sort of scattering the momentum transfer of the electron proton collision, and X is the Feynman X, the fraction of the momentum held by the struck parton, and the dots and blue and green and purple areas represent existent data, and then these curves represent the range of the EIC at different beam energies, at different center of mass energies. And so we can see there's this great physics range above what's already existent. Okay, a challenge of the EIC is that we have a very wide range of different kinds of collisions that we're trying to measure. So we need to measure inclusive deep inelastic scattering, where the electron scatters. The proton produces a wide range of final states. Then we want to do that in a semi-inclusive mode, where we tag one of the hadrons in that final state, say a charm quark or a B quark coming off, or perhaps a jet. That gives us a much more complex geometry to disentangle. And then finally, we also want to look at deeply virtual Compton scattering, where one of the where the struck proton remains intact and is reconstructed in the Roman pots, and we get a variety of products coming off this. So trying to measure all these physics processes means we have to do lots of different things. We have to measure first electrons, and I guess I said I'm missing Boris on this. We certainly have to measure jets over a very wide range. We have to try to tag leading hadrons, the flavor, charm, strange charm, or bottom hadrons, and also look for diffracted protons, very forward hadrons, photons, and neutrons to try to tag diffracted processes. So let's take an overview of the detectors. So the one very striking feature of the EIC is the large crossing angle. So we need both a large crossing angle and the Crab crossing mechanism to achieve the required luminosity. And this also has a constraint in that the central region of the detectors is limited to about 10 meters. So we have to make very compact central detectors, but still we want to have very large acceptance with PID for jets and electrons. In the forward-going hadron region, we have to measure either diffracted protons or weakly scattered protons, which are almost a beam energy. We want to get neutrons and photons as well. The electron region, we have to measure very softly scattered electrons, but we also need to make a precise measurement of luminosity and polarization. Both the forward and backward regions are very deeply embedded inside the machine matrix, which poses its own challenges. So as I said, the forward and backward detectors, here we see the central detector, like a conceptual view of the central detector. And then we have these very complex forward and backward detectors from looking at both the scattered electron, trying to measure its polarizations of the beams, and also to reconstruct the forward scattered protons, or to see that the ions, whether the ions in ion mode are intact or not. So we need to measure neutrons and photons from the ions. So this is a very complex problem. But what's nice about the forward and backward regions is that we have a large amount of physical space. So that's helpful. So the detectors are really a great challenge. I'm sure Boris would love it. The central detectors are very compact. The Crab crossing and the strong crossing angle means that the forward regions are very complex. Another basic problem is it's not like the LHC where you're colliding things that are basically symmetric. It's a very asymmetric system, and you're trying to measure this over a very wide kinematic range. Sometimes we even want to look at the electrons coming backwards, for example. So we can't compromise electron ID or jet performance or particle ID anywhere in the detector. We think it'll be great fun, and we're currently looking for collaborators. So I'd just like to summarize. The electron ion collider will be built at Brookhaven. We hope sometime like the 2030s. The machine offers a great opportunities to study the emergent properties of QCD at a very wide range of scales, at a very high precision. The detectors will be a great challenge, but I think we can do it. And we would be very happy to have you join. Thank you very much.
Thank you very much, Michael. Any questions, please? In chat or just turn on their sound? Okay, thank you very much, Michael.
Thank you.
Very interesting program, and actually, I wish you good luck. We will think here in Russia what we can introduce in your project.
That would be wonderful. That would be wonderful.
Okay,
and I said, I wish I was in Moscow, guys. Thank you so much.
Okay, great. Thank you. And the next talk, Paul Granis, 25th anniversary of the discovery of the top quark. Please, Paul, turn on your presentation.
Okay.
We can see you.
You can hear me, and can you see?
Right.
Okay, so it is 25 years since the top quark entered our consciousness, and we have spent that time studying it in some detail. And so it is appropriate, I think, that we stop and understand what the top has been able to teach us and a sense where we might be going in future studies. Just one little word on the prehistory to the top quark. Back in 1975, when the tau lepton and by inference, the tau neutrino were discovered, followed by the discovery of the B quark a year later, and understanding that it was a member of an isodoublet, it didn't take very much genius to understand that there was something missing in the periodic table of the quarks. And since the mass of the B quark was about 3 times that of the charm quark, which in turn was... Same?
I think the question is whether you will show our slides or not.
Oh, I was showing the slides, I thought. Let me try again.
No, please try again.
Do you see?
No.
No, no.
You should push on the green button demonstration screen
Yes,
and
yes.
find out.
Yes, I've done that.
And find out what file you would like to make visible.
Yeah. All that is done.
But we can see only you. We do not see your
If
presentation.
you like, I can share your slides.
Fine, that would be fine, Peter.
Oh, yes, now we can see.
Okay, thank you. Well, and if you would go to the second slide, please. I'll tell you when to switch. Next slide. Back. That's all the way at the end. We need to go back to the beginning. There, thank you. Okay, can people see now?
Yes.
Top quark prehistory.
So, as I say, we need not have much genius to understand that there's something missing. And so there were limits that were set successively at the electron-positron colliders, Petra, Tristan, and then LEP, that went above this, this mass of 30 GeV for the TT bar bound state, did not see it. There was a sighting, or at least a reported sighting at UA1 at the CERN SPP bar S, looking at the at evidence for the top decay to a B and a virtual W, but this was later retracted due to an underestimate of the W plus jets background. And subsequent to that, the UA2 experiment ruled out top anywhere below the W boson, looking for the W decay to a top and a bottom. And then passing to the Tevatron, CDF, and then the D0 experiments search for the top quark pairs in the case where the top decays to a W and a B. And ultimately, D0 raised the limit to 131 GeV. And the Tevatron was the only place to seek the top. So next slide, please. Two Tevatron detectors, on the left, the CDF, and on the right, the D0. CDF started in 1987, D0 only in 1992. They were complementary in their initial configuration. CDF had a solenoidal magnet surrounding a tracking and importantly, a silicon vertex detector used for tagging B quarks. And the D0, no solenoid, but a hermetic, finely segmented uranium liquid argon calorimeter and extensive muon coverage. So in 1992, the two experiments began what is now known as Run 1. Next slide. The top mass window. We know a lot from precision measurements, largely at electron-positron machines, on the constraints for heavy particles. Virtual top and Higgs loops in both the Z and the W boson propagators modify the properties in a way that depends on the top mass. And so measurements of those properties can give you a window on where the top and indeed the Higgs boson can exist. So by 1993, those precision measurements from LEP and SLC, together with that top mass limit from D0, constrained the mass of the top to somewhere in the range of 155 to 185 GeV. It also set rather weak constraints on the mass of the Higgs boson. Next slide, please. The top decays 100% of the time to WB in the standard model. The Ws can decay to a lepton and a neutrino or to a quark antiquark. So the final states that can be reached from top pair production are completely determined by the way the two Ws decay. If they both decay hadronically, you have the highest branching ratio for the largest background. It's the yellow slice of the pie below. That's called the all jets channel. The lepton plus jets channel is that in which one W decays to leptons and the other to hadrons. That has a moderate background and also moderate branching ratio. And then there are the dileptons where both decays leptonically, and that's the smallest background, but the smallest the branching ratio. The original measurements only used electrons and muons. Tau ID was difficult and did not initially attempt the all jets background, all jets channel in which the backgrounds are high. B jets were identified by displaced vertex or by the semi-muonic decays of the top. And neutrinos, of course, were inferred by missing transverse energy. And later on, all the channels were in fact used for studying the properties. Next slide, please. By 1993, both CDF and D0 were seeing individual events that looked extremely interesting. The CDF dilepton event had two quite high transverse energy jets. One of them was B-tagged, had an isolated electron and muon of moderate PT, and a substantial missing energy. The 1993 D0 dilepton event had an electron, a muon, missing transverse energy, all with a transverse momentum above 100 GeV, and two moderate energy jets in a region where the background probability was extremely small. And if that event was hypothesized to be from a top anti-top pair, the mass estimate from the single event was in the range of 145 to 200 GeV. Next slide, please. In 1994, CDF published what they called evidence for top, in which they had two dilepton events, 10 lepton plus jets events, all with at least one B tag, and a background of about 6 events. They fitted the mass of the top in the lepton plus jets. What you do is to take all of the observed objects, sort them with the most probable association to the top or the antitop, use the missing transverse energy to infer the properties of the neutrino, and then reconstruct the mass of the 2 tops and plot the events as a function of that fitted mass. And you see on the right what that looked like for the evidence paper. Bump in the distribution around 175 for the expected TT bar signal, the background at a lower mass, and the data clearly favoring some component of the TT bar. The observed cross-section, however, was about 2 times that of the standard model, so there was at least an upward fluctuation. And the p-value was 0.26%, corresponding to 2.8 sigma. At the same time, D0 made its selection based on topological variables, the aplanarity, which is the smallest eigenvalue of the momentum tensor, and HT, which is the sum of the transverse energies of all the jets. And the plot on the left shows how that works for the different categories of events, the multi-jet and W-jet backgrounds at the top, falling dominantly at low A and low HT. The TT bar events in the lower left with a sizable component at large A and large T. And on the right, the signal region and the few data events. There were 7 events, the background of 3.2, probability of the null hypothesis, 7.2%, and the rate was compatible with the standard model top pair production. Next slide, please. So in 1995, early in the year, the Tevatron performance had been much improved. A magnet that was misoriented was reset. And by that time, both CDF and D0 had more than 50 inverse picobarns on tape and sensed that this was going to be enough for the top discovery. And so the activities ramped up to fever pitch, trying to finalize all the various analyses. And the 2 experiments proceeded quite independently. There was essentially no communication between them. There was, however, an agreement with the Fermilab director, John Peoples, that either of the collaborations could start the clock for discovery by submitting a paper to him, and then a 1-week waiting period would start, allowing the other group to complete their work if they could. And this induced a certain amount of sanity in the process, since one didn't have to fear being scooped by the other collaboration. And on February 17th, CDF delivered its paper, D0 followed, and 1 week later, on February 24th, the 2 experiments submitted their papers simultaneously to PhysRev letters. Next slide, please. So here's one slide on the CDF version of the top quark discovery. Their analysis followed the same strategy that the earlier evidence paper had done, but with an improved B-tagging algorithm. And with 67 inverse picobarns, they had 6 dilepton events, 43 lepton plus jets events, which included 50 B-tag jets in that sample. The estimated background was 22 event tags, actually. The fitted mass peaked, most likely fitted mass was 176 GeV with a spread of 13 GeV. The cross-section now had come back. The fluctuation had vanished by that time and was essentially compatible with the standard model. And the background hypothesis was excluded at 4.8 sigma. And on the plot on the right, you see in the shaded regions the estimated background for the lepton plus jets events as a function of the number of jets. And the points showed that for the 3 jets and the 4 jet and more, there is a significant excess in data over the background, and that was the evidence for the signal. And the fitted mass distribution looked rather similar to what we had seen before, a peak at around 175 GeV and a background that was peaking lower. So let's go on to the next slide. Look at the evidence from the D0 top discovery paper. D0 also refined its previous analysis using the topological selection, getting a signal to background estimate, which was about 2.5 times better than it had been the year before. And with 50 inverse picobarns, there were 3 dilepton events, 8 lepton plus jets events with a topological selection, and 6 more in which there was a evidence for a muon from a top from the BDK tagging the B jet. So the estimated background to those 17 events was 3.8 events. The fitted mass best fit was 199 with a very broad distribution. It was actually sort of two-humped, and a cross-section which was essentially that predicted by the standard model. Background only hypothesis rejected at 4.8 sigma, 4.6 sigma. On the upper right plot is a indication of what this HT selection does in selecting signal versus background, both for the dilepton and also for the lepton plus jets. On the lower left, we have the mass fitted mass distribution, again showing a clear excess of events at high mass and a smallish background at the lower mass. And on the plot in the lower right, a two-dimensional plot for the top that decays all to hadrons, to 3 jets, the 3-jet mass as a function of the 2-jet mass, where the top is expected to have a 2-jet mass peaking at the W and a 3-jet at the top. And the data clearly has a component of that, but a small component of the lower mass from the backgrounds. The next slide, please. March 2nd, the discovery was announced with the joint seminar of CDF and D0. This is a picture of the audience during the seminar. Clearly, it's an in-person audience, no social distancing, no masks, no one looking at laptops. We didn't have laptops at that time. And you can't tell, interestingly, whether the speaker is from CDF or D0. Next slide, please. So who gets the credit for this discovery? I think in both collaborations, there was a great sense of accomplishment, but a real understanding that there was a shared responsibility for the discovery. There were 6 or 8 different analyses in each experiment. They used the properties of all of the subdetectors that were in the experiments, set of complex triggers and a lot of software algorithms. So it's absolutely impossible to single out a few people who were responsible. It's intrinsically a team effort. And on to the next slide. But the question is whether it was the top. And so to try to settle that question over the next several years, the cross-section was measured to increasing precision and compared to the standard model, and that the theory also evolved to the point where nowadays it is at next to leading order QCD plus next to leading order electroweak, and the cross-section agrees very well with that what you would expect at the observed top mass. The branching ratios are as expected in the standard model. The charge of the object is measured to be 2/3. The CKM matrix element is consistent with 1, as you would expect for a 3-generation quark sector. The W boson helicity in the top decay to a W agree with the standard V-A standard model. And the top polarization was essentially 0 as expected, and the spin correlations were as expected. So indeed, it looks like it is the standard model top, but it is certainly an odd object because its mass now is 40 times that of the next heaviest quark, the B. Also, it has a very short lifetime, 3 × 10⁻25 seconds, which means that it decays before the QCD hadronization can occur. And so there is no TT bar bound state as there is for all of the other quark anti-quark pairs. Next slide, please. So top now is approaching middle age after 25 years. The Tevatron told us a lot about it, but now the LHC has taken over, and it's interesting to see what new information comes from the measurements at the LHC. Here we see the top pair production plotted as a function of the TT bar mass. And on the left, at the Tevatron, this is the D0 plot, going up to about 1 TeV for the TT bar mass before the rate goes to 0. The red histogram is the prediction of a standard model, which is therefore clearly representing the data very well. On the right, we have on a log plot the same distribution from Atlas, now going out to 3 TeV in the TT bar mass, thanks to the development of boosted the observation and handling of jets that merge together at the LHCs, allowing one to go to very high transverse energies. And there are no TT bar resonances or anomalies that are observed. Everything is as the standard model would have it. Next slide, please. The mass is probably the most important property of the top to understand clearly. And it has been measured in many different channels, in many different analyses. The ordinary technique is to reconstruct all of the objects in the TT bar decay into the top and the anti-top, and then calculate their invariant mass, either for the most likely configuration or for the average of all of them weighted. Different analyses are different, and to compare that to a set of templates from Monte Carlo, which are constructed for different assumed top masses. And what one sees in the Tevatron on the left and the LHC on the right is very good agreement with those templates and an ability to pinpoint that Monte Carlo mass to high precision, 0.37% at the Tevatron and 0.29% at the LHC. A couple of years ago, I've not seen a recent measurement there. But the problem is that, and these measurements have now become essentially systematics dominated. So going further requires something new rather than statistics. But there's a problem in that the mass that one measures here is whatever it is that is embedded in the Monte Carlo. And what you would like to have is a mass that has a clear theoretical meaning, something like the pole mass or the MS bar mass or whatever. And to do that is more difficult. It can be done, it has been done at the Tevatron and at the LHC in the plot at the bottom. If you compare the theoretical cross-section and the experimental cross-section, both as a function of the top quark mass, and find where they intersect, then one has a measurement within the standard model context of the pole mass. And at the Tevatron, the best measurement is from D0 with an uncertainty of 3.4 GeV. At the LHC, a very recent measurement from CMS makes a drastic improvement to 0.8 GeV by using not only the cross-section, but two other distributions and making all three of them compare the data and get good agreement between data and the theoretical. So here the LHC has actually made a very large step forward. Next slide, please. The TT bar production is asymmetric, forward, backward at the Tevatron because it is an initial state of antiproton and a periton, and therefore the periton is the top quark tends to go preferentially in the hemisphere containing the exit periton beam, and vice versa for the antitop. And that asymmetry comes about from the interference between leading order and next to leading order diagrams in the QCD production. Early on, those measurements had a rather large discrepancy between experiment and theory. And what's happened over the years, shown in the plot on the left, is the data has come down in the asymmetry. Here it's plotted as a function of the TT bar mass. And the theory has gone up so that the yellow line of the theory now comes rather close to the experimental points, and there's no more large tension between theory and experiment. At the LHC, with the PP initial state, you don't have that forward-backward asymmetry, but you do have an asymmetry in that the top quark is expected to be produced more forward than the antitop. And so you can do a central forward kind of asymmetry, which is quite small, but now at the LHC is beginning to be measured. It's less than 1%, and so this is a tough measurement. Next slide, please. Production of a single top has been a very important aspect of top quark studies. It's produced through electroweak diagrams, the exchanges of W's or the involvement of W's in the process. Three main processes exist: the T-channel exchange of a W boson, the S-channel exchange of a W, or the S-channel exchange of a B quark, producing a final state of a top and a W. The top W process is small at the Tevatron and was not seen there, but the other two were, the S-channel and the T-channel. At the LHC, the S-channel process is small and has not yet been seen, but the TW and the T-channel have been seen. And if you compare the T-channel, which both accelerators have observed, you find that the cross-section is very much larger, factor 50 or so, than at the tevatron, but that the precision with which that T-channel process is measured is essentially the same at the tevatron and at the LHC. So here again, one has a rather strong systematics dominated character to the measurement. Also, the couplings that had been seen at the tevatron have been measured again at the LHC. The W helicity, which is expected to have no right-handed component, the LHC has improved the tevatron limit by about a factor of 4. The top-bottom W V plus A coupling, which is expected not to exist, the tensor couplings, the LHC has improved over the tevatron by a factor of 2 or so. Next slide, please. And the LHC is adding a lot that is new that was never done at the tevatron. For example, top pairs or the single top can be produced with in association with another object, a Z, a W, a photon, another TT bar pair, or a BB bar pair. And all of those are windows into the possibility of new physics. One has now also observed the top Yukawa coupling at the LHC via the measurement of the process production of top, anti-top, and Higgs, with the Higgs decay into BB bar, gamma gamma, or ZZ star. Comparison of that with the indirect Yukawa determination from gluon fusion processes in which you produce a Higgs that decays to 2 photons, and comparing those constrains the possibility of new physics in the loops. Also with the Higgs, we're now getting into the second generation of the very recent observation of the Higgs decay into dimuons, so the evidence for it. Also, as the high luminosity of LHC comes along, we'll be able to search for new physics. For example, the flavor changing neutral currents in top decays to charm Higgs or into charged lepton non-universality. The plot on the left is the recent determination of the Higgs decay into 2 muons, showing that again, the couplings are falling on this proportionality to mass that is expected in the standard electroweak mechanism. And of course, like it always is the case, yesterday's discovery is tomorrow's calibration, and that's true for the top, where studies at the top have helped us fix the jet energy scale determination and also the BTEG efficiency for studies searching for new physics. Next slide, please. The self-coupling term in the Higgs potential is shown here, the lambda 5/4 term. That lambda runs, as does alpha S and alpha EM and so forth. And as Q squared gets large, lambda decreases and could in principle become negative. And if it becomes negative, then the Mexican hat Higgs potential turns over so that the absolute minimum is no longer at the usual vacuum expectation value location, but there is a secondary maximum that is a minimum that is larger at higher expectation value, or becomes unstable altogether, and the universe becomes unstable or metastable. The current values of the Higgs mass and the top mass indicate that we are probably in this metastable region, in that yellow region between instability and stability. Although the uncertainty is such that we can't really tell whether we are in that metastable region or in a region that is absolutely stable. It's interesting to speculate whether or not there's a clue here that nature has arranged things such that we live on this boundary between stability and instability. Is that significant or is it a coincidence? Presumably coincidences do happen. For example, if you look up in the night sky at the time of an eclipse, you see that the size of the moon and the size of the sun are the same, but that interesting observation, of course, has no bearing on anything. Let's go to the next slide, please. So what is the character of our expectation for what we will learn when the top becomes more mature still? Well, we'll have the high luminosity LHC, and with a very large statistics, we'll be able to go into kinematic regions where lower systematic uncertainties can be found, and therefore improvements on things like the pole mass can be made to improve. And we'll also get into the range, the region where very rare decays can be probed, and if found, will signal the presence of new physics. Future E+ E- colliders will go even further. For example, the ILC can scan the energy in E+ E- going to TT bar pairs, as shown in the right-hand upper plot. And if you do that threshold scan, you have a very precise measurement of the turn-on of the top quark threshold, enabling you to find to measure the mass to a precision of about 50 MeV, which is about 1/16 of the current precision from LHC. In the ILC, the Higgs mass will also be improved by a factor of about 10. So the plot on the left indicates the comparison of what we know now about this metastable region to what we will know in the era of the high precision E+ E- machines, shown by that dot in the middle, and will clearly resolve this question of what region are we in. It is also true with the improved precision on the top quark mass and also on the W boson mass, that the constraints on non-standard model physics from the comparison of the directly measured Higgs mass and the indirect prediction based on the top and the W will be one of the best indicators of the presence of new physics in the loops of the various diagrams. Okay, next slide, please. And I will conclude. So the biography of the top has thus far gone through infancy, where the top was discovered at CDF and D0 and opened the era of the studies. In its youth at the LHC, we are extending our understanding of the top quark significantly. In its maturity further on, we expect that the studies at the high luminosity LHC and a future E+ E- collider will bring qualitatively new insights, and that these will be important because precision top measurements explore the third generation physics, where we expect that the new physics should be the most visible. And it also highlights the question. The top Yukawa coupling is essentially equal to 1, and you can ask whether this is an anomaly or is it the standard way a quark should behave, and that the up, down, strange, charm, and bottom are the peculiar quarks in the universe. So thank you very much. It's been a pleasure to join you, if only remotely. Next year in Moscow, I would hope to join you in person. Thank you.
Thank you, Paul. Any question, please? Question in chat. I do not see actually, except thank you very much.
Hello, I have a question.
Yes, please.
Hi, Paul. It's very interesting that now when we talk about the top quark mass, we move from the early days of direct reconstruction of something that would be interpreted as a Monte Carlo mass to now a scan of cross sections for the most precise measurements that relate to the pole mass. Is there something to be learned about the comparison between the two? Maybe something that has to do with running of alpha S or QCD corrections at the top mass scale?
I think I don't know. I think it's difficult to pinpoint what it is that is in the Monte Carlos and how it relates to any theoretically well constructed mass. I suspect you may be right, but I don't think I'm able to articulate how that insight into a running parameter would come about.
That's something that I haven't heard discussed too much, but it might be an opportunity to turn this challenge around and maybe learn something from it.
Yes, it's an interesting question.
More questions, please. Okay. Paul, thank you very much for your very impressive report. And thank you everybody for participation in this session. I hope we will have a lot of interesting information now to think over. Thank you very much.
Yes, so we will have a poster session in 30 minutes from now in Discord.
I think we can start our poster session. First of all, I'm really glad to see you, and I welcome you to our annual conference. Of course, as you already know, due to health restrictions, this conference is held online, and let's hope this won't be a tradition, and the next year we will be able to see you all in Moscow. So I think we are ready to present posters, and I just want to say a couple of words about these. First of all, for presenters in the poster session, it is advised to stay with their poster. But of course, once, for example, you discussed the matter with people who are interested in it, you are encouraged to wander through other channels and look at other posters. But if you see that someone is waiting for you in your poster channel, please go back and enjoy the discussion. As you also see, we organized some tables and sofas for the people who want to have a chat and exchange opinions about the plenary session and the talks that were held today. There were a lot of really interesting stuff, and thank you again for the people who contributed to this. So my idea was to not only encourage you to share your posters and look for others and exchange your opinions, but also not let the talks to die out. Let them proceed in the table rooms and sofas and everywhere you can find place. So enjoy the poster session of our conference. Thank you.
Нас снимают на YouTube. Катя, а можете чуть-чуть вниз еще сместить на результаты? Отлично. То есть у нас есть разница. С ростом множественности разница растет между измеряемыми радиусами для двух систем. Очень интересно.
Means magnetic storms on the Earth, on the Earth's surface, was only 15th of December, and we can see the first area of increase of the first area increase of flux intensity. It was 20th of December, and it is earlier than magnetic disturbance on the Earth. And for the considered geoeffective coronal holes, the hodoscope response was detected earlier than the recorded disturbance of the Earth's magnetosphere by an average of 7 hours. And also in 61 out of 112 muon hodoscope responses to the considered coronal holes, a region of increased muon flux was observed, like on these pictures. We can see the measure response of muon hodoscope, and before that we can see one area with increase the cosmic ray flux, and we examined 112 magnetic storms during the sun's low activity. It was years like 2008, 9, 10, and 2018 and 19. Their storms were caused by coronal holes in the sun. In this study, we used the data of the muon hodoscope organ, namely the GSM-Fs. We noticed that in 54% of the cases, the main hodoscope response is preceded by an area with an increased flux of cosmic rays intensity, and we consider the appearance of this area as a criteria for early detection of geomagnetic disturbance in the next our works.
Yes, thank you.
Oh.
And what I'm wondering how, because now, if I'm not mistaken, the sun doesn't have coronal holes because of the 11-year cycle. How do you does the hodoscope work at all when the sun doesn't have any holes for that period of time? Or do you analyze the data that was previously gathered when the holes were there?
О, так, повтори еще раз, только чуть помедленнее.
What do you do when the sun doesn't have holes, coronal holes? Because I think there's a period of time where the sun doesn't have any, and it's right now. It's happening right now, I think.
Right now is minimum of solar activities, and так, скажи еще раз другими словами.
Okay, so there are minimum solar,
Помедленнее.
there is a minimum solar activity at the moment, right?
Yes.
Is there some research which can be done when the solar activity is at minimum?
Hello,
Okay, hello.
once again.
Yes, I understand you. Sorry, it's my computer is something is.
It's
occurring.
okay.
Mhm.
On which words you lost it?
Yes, I see you. Mhm.
Okay, from this, yeah?
It's okay. It's
Okay.
normal. Okay.
But from which moment you've been lost it?
Oh,
From
I interesting your detectors.
okay, from the detector, yeah?
Yes, it's okay. I already see it. Okay, thank you very
Okay,
much.
and
Thank
don't
you very
worry.
much.
And after we create these heat maps, about 15,000, we use it for train and test on to our convolutional neural network, and then we try to predict our coordinates and compare it on test sample with original coordinates. So using this, we can understand accuracy of our neural network. For now, for example, you can see it here. We have very good, I can say it very good, results to 7 inner photomultiplier tubes, and we use these 7 multiplier tubes to something like fiducial volume of our detector. That means this is the volume in which we can to do our analysis in the good way. Because, for example, outer PMTs have some, you can see it has some very big error.
Mhm.
Well, and after that, after we train and test our model, we can calculate the fully error of our model, and we get that, for example, total mean squared error for all PMTs, for all detector, is about 4 centimeter for trained sample and 11 centimeter for validation for X and Y reconstruction. This is a big value, but if you see on just fiducial volume, we can see that for 7 central PMTs on trained sample, we get 3 centimeter and about 3 centimeter too for X and Y coordinates MSE, and 4 and 3 centimeter for validation. That means on test sample on which we just firstly predict and then we compare with original coordinates. So we have 4 and 3 centimeters. And of course, we know that this is not the best result. Because of that, we just want to increase some statistic, construct new types of heat maps, because we know that set this value to 1 to see color distribution is not good idea, but it works. And further, we want to set this value to something like average from all PMTs around maximum value of PMT. Well, something like this.
Okay, thank you.
Oh, thank you.
Using also some hard detectors, but XY position detectors, but it's similarly can use some of it's a very similar. So it's your work was for me very interesting.
Yeah. On which detector you use your
silicon detectors?
Silicon.
Silicon detectors.
Okay. Is it
like
CPM? No.
No, it's how can I say it? Это нит как.
Okay. Okay. Understand.
Thank you very much.
Thank you.
Thank you very much.
Я все-таки с 0.15 отрезаю, и что-то примерно такие же числа.
Have YouTube stream as a guest. Hello, YouTube stream. We are discussing our poster.
Hello, can you hear us?
I can hear you.
Nice. So, this work is about the mini PSD readout system at mini CBM experiment. So, mini CBM experiment is a prototype of a whole big CBM experiment at FAIR facility in Germany, in Darmstadt. It consists of several detectors, and among them there is a hadron calorimeter named PSD. It consists of 54 modules, and each module has a sandwich structure and is a composition of lead and scintillator layers. We have optical fibers and read the scintillator signals through these optical wavelength shifting fibers, which are connected to the micropixel photodetectors at the end of each module. So, and for the time being, mini PSD is a prototype of the whole PSD detector system, and this year we've made a test on a beam at the FAIR facility where tested our electronics and the readout chain. So perhaps my colleagues will give some comments on this electronics setup and the results.
Hello, can you hear
Dmitry,
me?
we cannot hear you, at least.
Hello, can you hear me?
Yes, yes.
Okay, so the scaled for full-size CBM detector, the readout chain was development, and here you can see the schematic of the readout. There is two major parts: on-site detector and the radioactive sensitive cave site detectors. On the detector size include the MPPC sensor, LED pulsar, and temperature sensor, and in a 50 meters distance, the readout electronics will be placed based on FPGA. You can see the image of boards. On the right side, there is a ADC card with add-on, what was applied for Panda experiment and will be used for PSD at CBM. It was tested already in beam tested mini CBM experiment. The service board represented on bottom size is reduced to set up and control the readout chain. It includes the LED pulsar as well as temperature sensor driver, and the communication is implemented via MCU, which will configure the high voltage supply, and it's connected I2C to a DC board, and which receive the slow control via GBT connection. As a result, we can say that the major part of readout was tested. As I said before, it was integrated already in mini CBM DAC, which include prototype of common readout interface. We achieved the GBT link synchronization, including the sourcing clock from DAC system and with the clock switching inside FPGA. In the bottom right picture, you can see the measured waveform. It includes several points and was measured on with digitizing 80 megahertz. And to one of the feature of FPGA processing signals, its possibility to fit signals on the fly in FPGA to have more accuracy on timing and amplitude. And also the pile-up separation, because in fact the event rate will be up to 10 megahertz, and for PSD event rate will be up to 1 megahertz. And to distinguish the pile-ups, the fitting procedure was applied, and to have more precise, the clock was from 80 to 120 megahertz. FPGA firmware updates, and this will be tested on next mini CBM beam in March of next year. That's it from our side. If you have any questions, please ask.
Я сразу не заметил. Прошу меня простить. В общем, как это называется-то? Я потерял мысль.
Мы говорили про то, что
в других, да?
Передний калориметр, который в MPD будет стоять, он должен потом в CBM поехать.
Ну, нет, насколько я знаю, вообще все вот такие эксперименты, как бы, вроде бы это особо не афишировалось, но вроде бы везде стояли такие эти... Я просто слышал от кого-то такую мысль.
Да, но я имею в виду не то, что похожие, ну, не с такой же мыслью, а прям физически один и тот же детектор.
Может быть, но весь прикол в том, что тут даже еще не решили, с какой стороны, грубо говоря, фашкала ставить, например, этот.
То есть они в MPD не с обеих сторон стоят, или про что? Или ты про тот, который в BMT не говоришь?
В БМН, да, я не говорю, который, то есть...
А что значит с какой стороны?
Ну, типа, сейчас прикидывают сзади его ставить, чтобы смотреть там только то, что вообще не взаимодействовало. А могут там решить ради интереса поставить впереди, чтобы, типа, еще и разлетающиеся события, например.
Ты имеешь в виду
в общем...
ближе или дальше от мишени? Или что сзади, спереди?
Да. Ну, имеется в виду сзади, спереди от этого калориметра вот этого. То есть с этой стороны или там сзади где-то.
Ты имеешь в виду про годоскоп, говоришь, да?
Да. Куда его втыкать. Ну, собственно, переходим тогда уж.
Подожди, Сань, не торопись. Мне, в принципе, это не очень важно. То, что ты хочешь мне рассказать. Мне вот интересно, про центральность у вас кто-нибудь рассказывает, или это будут именно выступления?
Про центральность?
Да, сейчас какие-нибудь постеры у вас есть про центральность с помощью вот этих детекторов передних, которые вы делаете?
Каюсь, вот про это я не знаю. Точнее, я не помню.
Мне кажется, у нас у Вадима Волкова будет... нет.
Постер или выступление?
Нет, постеров у нас нет по центральности.
Улучшает нам ситуацию.
Ну да, у вас получается, что вот при вот этой точке, которая стандартный кат, это 80% acceptance. При 40% background rejection, получается, да? Будет даже выше. Если background rejection сохранять, то можно почти 100% acceptance получить.
Да, вот в этом и дело. Но при этом что-то тоже будет теряться. То есть вот acceptance карты, которые после этого строятся. Ну вот в трехмерном виде, может, не очень понятно, в чем тут разница между стандартными критериями и нейросетью. Но после того, как строится acceptance, а именно как отношение вот этих двух трехмерных гистограмм к исходной, к primary трекам, и после того, как выбирается вот зона с высокой эффективностью, то видно, что картина немножко меняется, да, то есть появляется много нового при каких-то ПТ и быстроте, но при этом и теряется, вот, например, при маленьких ПТ и отрицательных быстротах область, потому что на самом деле она сильно засорена фейками, которые, тем не менее, проходят стандартные каты. И в обычной как бы карте, которая в анализе данных на все это не присутствует, эта область сохраняется, что не очень хорошо.
Ну да. Получается тогда, что статистика справа, она побольше, да?
Там суммарно больше бинов в этой трехмерной карте получается, но это как бы проекция этой трехмерной карты на фи схлопнута. Ну да, там получается больше бинов мы берем, хотя какие-то вот получается теряем.
Ну это интересно, потому что сейчас много где, вот я просто в эксперименте Deep 3600 мы тоже применяем похожие техники, но мы используем несколько тоже классификаторов: Random Forest, XGBoost и сверточные нейронные сети. Но у нас, конечно, результаты более скромные. Ну, как бы мы их, собственно говоря, и начали исследовать возможности применения таких, МВА-анализа именно из-за того, что изначальные результаты были скромные.
А что там за установка, то есть?
Это вот однофазный детектор на Аргоне в Канаде, в SnowLab лаборатории, там по прямому поиску темной материи. Это вот немного похоже на то, про что сегодня вот Балаздыня рассказывал. Вот. Только он рассказывал про двухфазные эксперименты, как DarkSide, а Deep — это однофазная камера.
Но он какой-то как бы симметричный или нет,
Да,
потому что
он
есть вот особенность в
симметричный.
том, что forward acceptance, и он такой с дырами.
Ну да, я помню, я немного занимался на 61, когда в группе с Ильей Сюльженковым работал. И я помню, как детектор устроен, выглядит. Ну там, да, там он симметричный, с некоторыми, так скажем, особенностями детектор. Вот. Но он как бы он не на пучке стоит, он чисто как телескоп работает. Но вот мы тут тоже такое вот исследование, я смотрю, здесь несколько докладов, которые вот связаны как раз с машинным обучением. Интересная тема.
Ну, тут, кажется, все равно можно еще много всего улучшать.
О, да.
Ну, как бы интерес, то есть вот результат, который получился, это как бы новый acceptance. Но по большому счету можно же сразу вот эти обученные нейросети натравливать и на реальные данные и заменить критерии, которые вот сейчас стандартно используются, просто как бы этим черным ящиком, который будет говорить, хороший это трек или плохой.
Ну вот проблема как раз в том, что это черный ящик, да, у нас вот коллаборация к этому так именно к валидации результатов относится очень придирчиво. Именно к тому, вот, что это черный ящик.
Ну вот, соответственно, есть как бы вот вариант попроще, который у меня здесь на постере, это построить как бы карту, в которой все как бы повышена эффективность, и применять уже просто ее, как бы, выбирать какую-то кинематику в данных, это как бы уже не черный ящик, то есть это просто выбрана наибольшая эффективность.
Маска такая. Ну да. Вот единственное, что, конечно, мне интересно, вы сколько здесь вот уже попробовали данных обработать? Потому что я вот столкнулся с проблемой именно, как применить все эти методы, которые на Python, как говорится, реализованы у нас. У нас Python в связке с рутом. Именно вот вопрос, как обработать, когда там, вот, например, большие есть файлы, что называется, там триллионы событий, и Python просто такое огромное количество очень долго обрабатывает. И вот здесь вот возникает вопрос, как это как это провести. Пока что...
У меня на самом деле на этот вопрос ответа нет, да, то есть вот эти 10 миллионов событий, то, что мы там обрабатывали, это уже тоже занимало много времени и объема банально.
Не, ну там в 20 гигабайт свопа, после которого компьютер уже зависал. То есть это просто некий предел локального компьютера, scikit-learn уже не мог проживаться на компьютере. Поэтому 10 миллионов где-то.
Ну да, то есть скейлить это на еще большие объемы. Но это надо думать, как это сделать, да, то есть...
Ну да, это уже принципиально новый как бы шаг, уже не поисковое исследование, а прям продакшн такой, да, то есть надо серьезно вот всем сидеть за это.
Ну, вот
куда-то идти.
Продакшеном вот именно на питоне, вот как он есть, ну, не так все просто. Я знаю, что для таких массивных вычислений именно с большим количеством данных используются джавовские библиотеки Hadoop и Apache Spark. В них как-то можно как-то задеплоить, например, написанную на питоне модель, ну там нейросеть или еще что-нибудь, как-то можно задеплоить как на Kubernetes куда-нибудь или на докер какой-то, а оттуда уже его использовать. Но я, честно говоря, с такими, я так понимаю, это какие-то уже сложные облачные технологии, я с этим, честно говоря, не работал, плохо себе представляю, как это сделать. Поэтому у нас все работает пока следующим образом, что есть вот часть, написанная на питоне, а часть на C++ реализована, ну, на руте, по сути говоря. И мы сначала делаем такие scheme файлы, то есть применяем какие-то каты, которые отрежут то, что точно не нужно. Ну, типа там триггер не сработал или еще что-нибудь, чтобы событий было поменьше. А потом уже обрабатываем. Ну, как бы делим на куски и на кластер. Батч запускаем. Но все равно долго. Если такие большие файлы обрабатывать, то все равно много времени занимает.
Ну да, ну то есть у нас на самом деле тоже вот то, что мы из этих симуляций сэмплы делаем, это тоже же из рута,
Мгм.
и потом мы их уже в Python вставляем. Но, ну да, масштабировать это трудно.
Да, это одна из таких самых проблем.
В принципе,
Ладно,
у нас есть
спасибо.
какая-то в СПБГУ вот эта ферма и тоже специалисты по облачным вычислениям, но это надо с ними нам начинать общаться. Пока что более маленькая статистика.
Ну да. Ладно, спасибо, я пойду еще посмотрю, как
Мгм.
дела идут. Всего доброго.
Спасибо.
Уравнение 7. Ой, нас, кажется, стримят, и мы говорим по-русски, но ладно. В общем, если разрешить вот это уравнение, ты говоришь, что окей, мое определение скаляра Ричи будет постоянным значением, и ты будешь искать решение для e в степени альфа от t, то есть твою как бы вот передпространственной части в интервале вещь, которая за радиус говорит тебе, то там из решения, я могу позже показать в другом документе, понятно, что на самом деле все правильно, и на асимптотике мы получаем, из-за того, что у нас сфера очень большого размера, мы получаем что-то близкое к очень плоской вселенной. Ну, то есть аналогия вот у нас с Землей в чем-то.
Ну да.
Вот, а
Ну,
по поводу
вообще,
размера, ну вот это единственное, что это как раз-таки не ограничивает в том, что, ну вот мы живем, допустим, на поверхности вот такой огромной раздутой сферы, и как раз-таки вот просто факт в том, что условно свет там или еще что-либо не успело дойти, и, возможно, эта сфера чуть больше, чем она есть. Но она не,
ну да, то есть
конечно, количество порядков больше.
радиус наблюдаемой Вселенной много меньше, чем радиус сферы, по сути.
Ну, много это 10 в 5, да.
10 в 5. Ну, 10 в 5, мне кажется, что такое соотношение уже бы немножко была кривизна обнаружима. Тут надо сравнивать с космологическими данными по поводу измерения плоскостности Вселенной.
Ну,
Мне кажется, это стоит сравнить.
Окей, но если мы же как бы, когда решаем систему второго порядка, как у нас возникает в ФТР гравитации, мы получаем дифференциальную систему второго порядка из двух уравнений. И, соответственно, на выходе, когда мы численно решаем, мы имеем численные значения для первых производных и для просто значений функции, так? И вот ты видишь, что в формуле 12 это как раз-таки результат численных вычислений, что примерно к времени вот 1061 в планковских масштабах. Сейчас кривизна, ну, собственно, как бы соответствует тому, что мы видим, и производная по альфа тоже. Потому что, ну, мы параметр Хаббла сейчас имеем, там, чтобы не наврать, вроде 10 минус 31 электрон вольт, в планковские масштабы переводим, как раз-таки получаем 10 минус 61. То есть параметр Хаббла, вот этой производной по альфа, у нас в точности этому и получается равен. Плюс подставляем потом, так как у нас сейчас расширяется Вселенная, выражение для скаляра Ричи 12h квадрат, ну, получаем вот как раз-таки эту кривизну, которая сейчас есть. То есть как бы здесь нет никаких...
Современная.
Ну да.
Угу.
Потому что мы численно посчитали как раз-таки вот на этот момент времени значение этих величин.
Угу. Понятно. Ну, вообще, насколько я знаю, квадратичная гравитация, она более всего совпадает с данными Планка, то есть лучше всего прям в центре области допустимых значений параметров находится. Поэтому вообще все исследования около этой гравитации, они весьма перспективны.
Нет, просто на самом деле я тоже задавалась этим вопросом и смотрела ответ, пыталась найти, и сейчас есть современные, ну, я имею в виду там годичные или даже этого года работы в хороших журналах опубликованные, где люди пытаются как раз-таки найти, условно, лазейку, отойти от квадратичной вот этой теории гравитации. И сначала там, ну, грубо говоря, несколько лет назад они сказали, что да, все степени, которые будут выше второй, там кубичные, какие-то дробные, четвертые и так далее, положительные степени для скаляра кривизны функции ФТР, они будут иметь коэффициенты перед этими, соответственными степенями сильно подавленными экспоненциально, и в экспериментальных данных их невозможно найти. Ну, то есть пока что нет действительно не с чего полагать, что нужно добавлять какие-то дополнительные слагаемые. Однако вот в этом году, буквально в июне, вышла работа, которая говорит, что... Сейчас я чуть-чуть вернусь на другую часть постера. Вот как раз-таки, если мы берем 14-ю формулу для ФТР-гравитации, то они показали, что вот коэффициент А большой к коэффициенту А относится как... должен быть, вернее, по модулю их отношение должно быть меньше, чем 10 в минус 8. Я не помню точно цифру, 4 или 8, что-то такой отчетный порядок. Соответственно, ну как бы они не исключены экспериментальными данными, да, ты можешь добавлять маленькую добавочку, которая преимущественно ни на что не повлияет, потому что коэффициент будет очень маленький. Но экспериментальными данными это никак не исключено, плюс люди, ну, соответственно, не просто обрабатывают данные, а там реконструируют всякие потенциалы и так далее, исходя из этого вида, и считают скалярное тензорное соотношение для инфляции, и все у них там выходит вот как раз-таки с наложением ограничений на этот коэффициент. Так что если ты задаешь его маленьким, то никаких противоречий с тем, что сейчас имеется в экспериментальных данных, абсолютно нет, и люди до сих пор этим занимаются. Плюс для дальнейшей перспективы какой-либо на этот счет, если мы будем в многомерии, то там уже не настолько они прямо коррелированы с наблюдаемыми величинами этих коэффициентов. Сам понимаешь, да.
Ну да, ну да.
Вот.
Ну вот, я так понимаю, следующий шаг это взять, допустим, две сферы и посмотреть, как они друг относительно друга расширяются, да? То есть одна превращается во Вселенную, а вторая в компактное пространство, допустим.
Ну, поначалу, конечно же, хорошо бы доделать эту работу и посмотреть, как более точно влияет и начальные условия, и коэффициент. На самом деле здесь не только, как я сказала во время вступления, грубо говоря, к постеру, что зависит от начальных условий, а зависит еще и от значений коэффициентов, потому что, например, жаль, что здесь не продемонстрировано, но я думаю, что ты знаешь, о чем я сейчас скажу. Вот если ты берешь след от системы уравнений для ФТР-гравитации, ты вот получишь как раз-таки просто уравнение колебаний, осциллирующие для скаляра Ричи, так? И, соответственно, там была какая логика, что мы имеем вот такое вот уравнение колебаний, но у этого уравнения колебаний есть несколько режимов решения. И при выполнении там определенного соотношения перед первой производной и перед просто скаляром Ричи наступает вот режим, например, осцилляции. Во всех остальных решение носит просто периодический характер и не является колебаниями. А вот при наступлении этого режима все выполняется. Но проблема в том, что вот, я не знаю, вот я сейчас буду писать, я думаю, просто. Сейчас я попробую, чтобы ты видел, или... Я надеюсь, что мы скоро пропадем из стрима, но ладно. А здесь в Дискорде никак нельзя ничем рисовать?
Нет, тут только приложение можно.
Вот сейчас что ты видишь, да?
Что-то вижу.
Ну вот, если ты возьмешь обычную модель Старобинского, там будет что-то в таком духе, вроде 3h r с точкой, плюс вроде m квадрат r, так?
Да.
Вот. Соответственно, интересный факт, ну, относительно интересный, конечно, не очень, но факт в том, что h у нас это производная от альфа по времени, так? А m это наш коэффициент а. Соответственно, так как у нас вот эти вещи должны быть как-то пропорциональны, чтобы мы получили решение, содержащее осцилляции, то у нас получается естественным образом ограничение на начальное значение вот этой производной. То есть она скоррелирована с а. Чтобы наступили осцилляции, вот, например, в этой модели для там, чисел Старобинского коэффициент а должен быть намного больше 10. Это если просто...
Что означают осцилляции, то есть физически? Это вот эти, да, которые синенькие у тебя нарисованы?
Нет, вот мы сейчас обсуждаем модель Старобинского, это черная картинка на фигуре 1.
Ну,
Ну,
то
как
есть,
раз таки они означают, что вот в этот момент до этого у тебя на инфляционной стадии значение параметра Хаббла вообще
понятно. Ну, это то, что называется reheating stage. То есть,
Да. А здесь
мгм,
вот это соотношение как раз-таки производной и m квадрат в обычном классическом уравнении колебаний, это пропорциональность меняется, начинается режим осцилляции как раз-таки.
мгм,
Кривизна осциллирует, рост альфа замедляется, сфера уже не так экспоненциально быстро растет, соответственно, вот
мгм,
получаем переход на, грубо говоря, следующую стадию.
мгм. Ну и там частицы нарабатываются фактически.
Ну да, конечно, в этих квадратичных моделях смотрят там, как они, с какой скоростью, там, чтобы все тоже окей было в экспериментальных данных. Но
Ну да,
здесь
да.
гравитационный эффект используем, потому что очевидно, чтобы использовать такой подход для уже вопросов касательно частиц, то как бы вот здесь в уравнениях у тебя будет стоять, наверное, что-то с тензором материи, а не просто ноль.
Мгм.
Так что,
Ну да.
там берешь, и просто будут другие уравнения, но да, такие работы тоже есть, и там немного от стандартного космологического сценария есть различия, и люди это обсуждают. Ну и как раз-таки там может это влиять на все процессы в ранней Вселенной, там самый попсовый пример для формирования первичных черных дыр. Вот. Что-то в
Да,
таком.
интересно. Конечно, у меня всегда возникал вопрос в таких моделях про начальные данные. То есть, получается, от того, как мы выберем начальное значение, будет зависеть итоговая конфигурация. Хотя можно какие-то ограничения поставить, как ты говоришь, и тем не менее есть достаточно большая свобода. Правильно я понимаю?
Ну, формально есть свобода, но, опять же, напомню, что вот мы хотим посмотреть динамику субпланковских энергий. Допустим, мы задались таким вопросом.
Мгм.
Соответственно, вот формула снова 5, повторю. Мы знаем, что при этих энергиях у нас есть примерное значение параметра Хаббла. Ну, то есть в планковских масштабах это 0,1. Вот,
Ну, то
и
есть
мы...
мы некое естественное предположение делаем по порядку величины.
Ну да, это естественное предположение, но здесь просто на постере этого нет. На самом деле, естественный вопрос, а что будет вблизи этого значения? Понятное дело, что работа проделана вот, если там альфа будет какой-то другой вблизи вот этого значения, который относительно естественным кажется, или производный, потому что на этих энергиях, очевидно, эти конфигурации могут зарождаться абсолютно с разными начальными условиями. То есть это какой-то такой относительно правильный, что ли, подход, что вот у нас есть параметр Хаббла, поэтому ограничим вот так. Но на самом деле это не обязано быть таким. И в работе мы поварьировали все эти начальные условия. Ну, то есть как раз-таки у нас и остается. Вот для квадратичной модели, если мы c полагаем нулю, у нас коэффициент А, параметр, и параметр вот альфа-0 и альфа-1. R1 0, потому что, зачем нам высшие производные отлично от нуля в начальный момент времени, R с точкой, я имею в виду 0. Вот, а значение кривизны у нас из уравнения решается. Так что, остается 3 параметра всего лишь, 2 начальных условия на размер и производную для альфа, и просто параметр в функции f от r. То есть не так много параметров, и вот мы смотрим там тоже, как это влияет, потому что очевидно, что есть область параметров, которые, например, не способны вырастить сферу и вообще, в принципе, не приводит вот в начальном этапе к такому экспоненциальному росту. Вот. Соответственно, в дальнейшем вот мы...
Остается квантовой пеной, по сути.
Да, потому что, казалось бы, вот, еще раз повторю, что да, мы знаем параметр субпланковский Хаббла, но это не обязано быть таким и никаким таким.
Я понял. То есть получается, что вот ты как раз рассматриваешь начальную стадию формирования пространства, а я, наоборот, в своей работе рассматриваю конечную стадию релаксации уже. И вот эти вот вещи. Определенная комплементарность есть. Потому что я исхожу из уже готового вакуумного состояния пространства, которое стабильно, немножко возмущенного. А ты, собственно, рассчитываешь, как оно вообще формируется.
Да.
Угу.
Вот, но я
Да,
пока
понятно.
не вижу в дальнейшей перспективе, как у нас пересекутся работы.
Да, тут, я думаю, слишком большой объем исследований. Да. Ну хорошо, спасибо, Полин, большое, я понял.
Если
в
еще
чем
будут
суть?
вопросы, заходите.
Хорошо. Окей, я тогда посмотрю сейчас еще другие вопросы.
Да, окей, слушай, а вот вопрос только, я могу ходить по другим комнатам или это не очень хорошо?
Ну, в принципе, можешь, если кто-то зайдет в твою комнату, то лучше, конечно, вернуться, если они захотят.
Там опять кто-то ходит?
Да, у тебя здесь еще посетители.
Да, кто-то есть еще.
То есть я хотел несколько вопросов задать.
Ну, задавай.
Во-первых, то есть, во-первых, тут все делалось с помощью моделирования, правильно? Да, то есть вы моделировали.
Да, основная работа — это, ну, типа, моделирование в Java. Я писала скрипты в руте, ну, остальные графики — это вроде в Origin делались, плюс еще, ну, как бы визуализации, проверка того, что все правильно было запущено моделирование с помощью вьювера. Ну, вот он, картинки в левом угле — это вьювер. Ну, и
Вот отбор, собственно, гамма-всплесков, он планируется его использовать, ну, то есть вы, в принципе, его это хотите использовать для идентификации гамма-квантов в эксперименте во время набора данных, или это уже будет использоваться после того, как данные будут получены в обработке результатов?
честно, вот это более детальный вопрос, он скорее не ко мне.
Окей,
Ну,
хорошо.
я знаю, что это как бы относится к таким одним из основных задач гамма-400. Вот. Ну, там этих измерений энергетических спектров галактического, внегалактического, диффузного, изотропного гамма-излучения, поиск аномалий, потом сравнивание, есть ли эти компоненты с компонентами темной материи. Ну, вот, это как там одна из основных задач. Это потом поиск этих гамма-всплесков в диапазоне энергии определенном от 10 КФ до 10 МФ.
А вы планируете наблюдать эти гамма-всплески от каких-то конкретных явлений или просто хотите их пронаблюдать?
Что просто. Ну, и в частности, найти новые их источники. Ну, и пронаблюдать их в определенном энергетическом диапазоне и изучить в этом диапазоне.
Вообще, другие эксперименты, кроме того, что ты упоминала про гамма-всплески после ядерных взрывов, да, другие эксперименты, вот тут есть темп-счеты, но это темп-счет, насколько я понимаю, просто гамма-квантов, да, экспериментов,
Да, это
а не
эксперимент.
гамма-всплесков. Другие результаты по наблюдениям гамма-всплесков были какие-то, как их было много, что они
Я
вообще
знаю, что
наблюдали?
сейчас гамма-всплески достаточно так регулярно регистрируются. Ну, вот в Ферми летает больше 10 лет, и они там с 2010-го достаточно регулярно регистрируют их. Ну, у нас это не самая основная задача, но просто одна из основных задач, скажем так.
Мгм. Но у вас будет какая-то разница, да? То есть энергетический диапазон другой там.
Да,
или-
да, да, да.
Мгм. Хорошо. Окей. Спасибо.
Зачту тебя как первым посетителем.
Я польщен. Спасибо.
Мой спор. Нужно просто двумерную проекцию.
Ну вот, да, двумерная проекция.
Я просто не понимаю вот правый все-таки график. У тебя же каждая частица может прилететь в любое место, да, и по ИТ, и фи. И, соответственно, она будет... эффективность очень сильно зависит от того, куда именно полетела по углу частица, правильно? И это все здесь смешано в одну кучу.
Ну да, это заусреднено как бы.
Это усреднено. Но при этом мы же хотим корреляции между множественностью и pt. И как ты можешь отдельно pt корректировать, не глядя, куда частица полетела?
Там в тех членах, где есть корреляция, то мы используем четырехмерную матрицу, которую не нарисовать. А эта матрица используется для знаменателя, где сидит только pt одномерного спектра.
Все понял. Это которая омега pt там, да?
Да. Да.
А я думал, она именно вкрадывается как-то в саму сигну, в эти кросс-корреляторы.
Нет, в кросс-корреляторы вот и как раз должна четырехмерная матрица быть.
Слева же формулы есть, я только сейчас.
Да, тут есть формула.
У меня коронавирус, просто на него внимание утекает.
Так увеличивается то, что я показываю, да?
Да, очень хорошо. Я еще сам увеличил к тому же дополнительно.
Ну, короче, вот, то есть числитель, например, дельта или сигма, для него четырехмерная матрица. Для знаменателя вот этого здесь спектр нужно просто скорректировать.
Ну, кстати, вот этот n, ты его к числителю относишь?
Я беру его из числителя.
Ну да, то есть это как бы часть числителя. Это
Да.
не совсем.
Это не совсем отдельные, которые, да. Ну и да, это как будто просто знаменатель вот этот.
Да, просто омега pt маленькая отдельно корректирует.
Да.
Потому что иначе надо делать шестимерную матрицу. Опять же, потому что омега pt маленькая можно переписать через pt большое и pt запятая 2. То есть сумму квадратов.
Ну да. Еще можно сравнить, например, множественность я могу скорректировать просто в одномерном распределении. Вообще просто множественность. Двумерную, получается. Двумерной матрицы. Вот этой, собственно. А могу скорректировать вот это двумерное распределение птn. И потом посмотреть, как же скорректировалась моя множественность. Например, это вот здесь таблица. Первая строчка как раз из одномерного, а вторая из двумерного. И потом проекция на n. Ну и тоже видно, что есть разница, конечно. Но небольшая. Для данной статистики, я бы сказала.
Ну, в принципе, то же самое можно сделать и с pt большим отдельно.
Да.
Тоже же можно отдельно нарисовать одномерную двумерную респонс-матрицу pt и трехмерную.
Да, даже нужно, наверное, чтобы понять, насколько... Ну, я не знаю, насколько мы ошибаемся, мы поймем из этого.
Да, скорее всего.
Игорь, ты еще тут?
Да, я тут. Я пытаюсь, знаешь, что сделать? Понять, надо ли говорить или не надо про другие методы коррекции. Что у меня стал мигать твой постер. Что можно же корректировать on the fly, если ты знаешь efficiency map, ну и там acceptance map, я не знаю. Ты можешь корректировать прямо при заполнении. Сейчас я вспомню, какой лист это они делают. То есть ты сейчас корректируешь как бы уже интегрально, да, по всему acceptance, вот эти у тебя есть моменты, там n квадрат средний, да, просто n.
Да.
Когда они у тебя уже набраны, ты их корректируешь. Респонс матрицей, да?
Ну, как бы распределение я уже корректирую, да?
Перераспределение корректируешь. Блин, я просто пытаюсь понять, будет ли разница какая-то, если это on the fly делать, не будет ли это математически эквивалентно тому, что ты делаешь.
Когда мы думали про машинное обучение, вот там тоже был вариант на ходу это корректировать. Ну, только методами
Ты до сих
машинного
пор-
обучения.
Ты про машинное обучение до сих пор думаешь?
Думаю.
Мгм. Давай потом, может, обсудим это при случае. Ну, если ты почитаешь что-то и будут какие-то идеи, то
Мгм.
интересно же.
Просто, например, если мы натравим сетку, разобьем на бины, наш acceptance, везде будет разная эффективность, везде можно везде можно будет свою респонс-матрицу нарисовать, но тогда не очень понятно с bin migration, что мы будем делать. Да, то есть респонс-матрица нам не скажет, в какой acceptance у нас улетел трек, если мы будем смотреть конкретный маленький бин. Наверное, если мы будем расписывать все эти средние через суммы, и через суммы по бинам, там какие-нибудь кросс-члены должны будут вылезать, и мы не будем знать, как их скорректировать. Наверное, тогда можно скорректировать как бы отдельно вот так по сетке, а потом передвинуть ее как-нибудь. Не знаю.
Я тут просто думаю, что очень легко можно перемудрить.
Да, и тогда заусреднять там, ну это сложно будет. В принципе, что нам тут портит, то, что у нас не однородная эффективность по ити и по фи.
Разве это уже все не учитывается в респонс-матрице?
Но учитывается усредненно, как бы.
Ну, одновременно по ИТа, ПТ и ФИ.
Ну, ты усреднила, получается, когда ее строила, и сим, и рек. Поэтому в каком-то смысле учитывается, но в каком-то смысле размывается, потому что нюансов мы не видим. Потому что если мы возьмем acceptance очень вперед, то там будут только маленькие ПТ, и мы их там как-нибудь плохо корректируем или наоборот хорошо. И там будет одна респонс-матрица. А если мы потом возьмем опять весь acceptance, то этот участок там переобучится, и какой-нибудь будет сильный вклад от как бы другого кинематического участка. А в том acceptance мы будем, соответственно, этим средним корректировать неправильно. Не
Ну да.
знаю.
Может, можно разделить на несколько областей, попробовать.
What is it?
Yeah, it's a kind of quantum gravity process, as I've described. It takes place on the grounds of quantum gravity. Uh, the the mass of the black hole shrinks to the Planckian size, and after the Planckian size, then we have a linear metrical equation which allows us to imagine the white hole. So in this diagram, you can see white hole and the white hole, sorry, black hole and the white hole, and we have the singularity. So what happens here is the black hole shrinks down to the Planckian size, and then it emits the information it has into the other universe. So what we call as a white hole. This
So from the Planckian size creates a white hole. It's like it's some kind of Big Bang or stuff like this.
Yeah, this can be a solution to the Big Bang we have today. Yeah, theorized Big Bang.
It's very interesting. I have another. What about the holography principle? The idea that all the information inside black hole is actually contained on the surface of this black hole. How can this principle can connect can be connected to your study, or maybe not connected?
So yeah, the holographic principle is something like we can think it as a remnant, I guess, because yeah, information stored in remnants that would be more similar to the information like it is something stored at the singularity, right? So yeah, I guess it is stored in the Planck size, and that's what it is about.
So singularity exists inside a black hole, but uh, um, a distant observer can't see singularity. It see the event horizon, and so the remnant, as I understand, is something is something equal to the event horizon, but inside the black hole. So if so for distant observer, information stored inside horizon on the surface of a horizon, but inside the black hole, it seems like the information stored in the remnant. Am I right, or?
Pardon, please, I didn't understand your question. Can you reframe it?
So distant observers see that information stored on the surface of a black hole. This is a holography idea. But internal observer, which is inside a black hole, see the remnant, see the singularity, and all information for this observer stored in this singularity. Am I right? Am I right in understanding this?
Yeah. So the information of the object is lost in the idea of holographic principle. More clearly, it's against the laws of quantum reversibility. And yeah, so this is an undergoing thing. Till today, we have these theories, and this is the best theory I've thought. So I've presented this, and yeah, there can be anything inside a black hole. It's predictable, but we cannot. It needs a lot of it needs a lot of technology development advancement. So it's not confirmed that we have a holographic projection, and holographic projection is not constantly like taken into account because of the quantum principles it fails to. So hope I answered your question.
Okay, thank you very much.
Thank you.
Есть какие-нибудь вопросы, могу еще рассказать.
То есть работа в том, что в создании пейпера FHCO для BMN и MPG, так?
Ну, да, разработка системы управления для этих детекторов.
Понял. Интересно. Спасибо.
Величины. Вот. Это крайне правая картинка. Величина, соответственно, фон. У нас получилось здесь 2,12. Ну, также еще были исследованы площади нормированных сигналов ворот гейт 1, гистограмма представлена на крайнем левом рисунке, и гистограмм площадей ворот гейт 2. Ну, там значения, они примерно такие же, как и в стандартном методе, собственно. А вот метод, в котором мы брали отношения площадей в воротах гейт 1 и гейт 2 нормированных сигналов, у нас получилось больше 2,12.
То есть, по сути, разрешение получилось почти в 2 раза лучше, да?
Ну, нет, если сравнить стандартные методики, у нас здесь 1,62, а тут 2. Но не 2 раза. 2,12. 1,5 где-то.
Ну, в общем, на треть.
Ну да, да.
Хорошо, спасибо.
Пожалуйста.
И тут показано, как он эволюционирует во времени. Это синие полоски. Красная– это масса центральной черной дыры. За счет захвата легких черных дыр она растет, но масса центральной черной дыры, но растет незначительно. Ожидалось бы чем-нибудь побольше.
Вот как. А еще раз, оранжевая кривая что нам показывает?
Оранжевая– это зависимость массы центральной черной дыры от времени. Там просто кластер непростой, там типа есть еще очень тяжелая черная дыра, которая в центре. Вот, и она тоже создает там какой-то гравитационный потенциал, и вот это вот все.
А за счет чего ее масса растет?
За счет того, что она поглощает более легкие.
Ага. Ага, так. Что-то хотел спросить. От чего зависит, поглотит ли центральная черная дыра все остальные, или все остальные разбредутся, улетят в разные стороны? То есть вообще эта система, она получается неустойчивая, да?
Почему?
То есть получается как? С течением времени их количество не будет меняться в
Количество кого?
черных дыр?
Будет. Но
Вот.
очень медленно. Тут такая же идея, как в галактических центрах. В галактических центрах тоже есть тяжелая черная дыра, и, насколько мы видим, она не поглощает галактику.
Ну да.
Но это для наблюдаемых галактик, и там массы поменьше, вот, потому что захват, он крайне редко происходит. Это вообще довольно запутанная штука, потому что не очень понятно, как все устроено законом сохранения энергии, потому что когда частицы поглощаются черной дырой, то куда девается энергия? Как бы вопрос куда? Не очень понятно. Вот, и тут может быть интерпретация такая, что когда, ну, во-первых, у гравитационно связанной системы отрицательная энергия, и когда будет поглощаться какая-то частица центральной черной дырой, то эта энергия отрицательная, она будет передана в центральную черную дыру. В результате чего энергия системы, она увеличится. Она будет по-прежнему отрицательной, но чуть ближе к нулю, чем была до этого. И в результате этого, согласно теореме Вириала, будет происходить расширение кластера. В общем, очень запутанная штука. Ну и все.
Ну да, так сразу и не разберешься. Ладно, спасибо большое за объяснение. Чего?
На здоровье.
Ты не стримишь?
Всего массива, то было бы гораздо эффективнее. И можно было бы канальность просто сильно повышать. Вот. Или использовать более низкоскоростные линии связи, относительно низкоскоростные. Так, как работает деконволюшн? Вот его идея заключается в следующем, что если мы возьмем, посчитаем фильтр деконволюции как через обратную функцию, это теорию рассказывать, может быть, немножко долго, это лучше смотреть что-то конкретное. Саму
Я
идею.
понимаю саму суть, да.
Да, сама идея. То есть берется, грубо говоря, фильтр, который прогоняет сигнал через обратную функцию. И он пытается восстановить исходный дельта-импульс.
Сколько математических вычислений примерно? То есть какие и сколько?
Там получается многочлен, не многочлен, по сути, многочлен считается, но сейчас скажу, у нас тут фильтр 4-го порядка, соответственно, 5 отчетов берется, и надо для вычисления новой точки, следующей точки, надо предыдущие точки перемножить на коэффициенты и сложить. Получается, сколько там, 5 умножений и 4 сложения. Либо это можно распараллелить. Можно для оптимизации выравнивать, там домножать, чтобы не возиться с вещественной арифметикой, можно домножать коэффициенты, например, не на 3, целых 0,28, какой в зависимости от передаточной функции получилось, а можно это умножить на, условно говоря, 1000, и мы уже можем переходить с небольшой погрешностью на арифметику с целыми числами. Это менее энергозатратно и быстрее, и в том числе в реализации в железе или в плесе. Кроме того, можно подобрать коэффициент таким образом, чтобы выравнивать результат. То есть нам же потом этот результат, чтобы получить исходное значение, надо поделить на 1000. А если мы изначально коэффициент зададим умножающий 2 в степени, то для получения финального результата нам достаточно будет просто сдвиг сделать.
Понятно.
Да. То есть мы переходим, с одной стороны, к целочисленной арифметике, что более практично может быть, и финальный результат получаем достаточно удобно. Причем мы можем получать результат, как вот у нас тут АЦП 10-разрядное, мы можем сдвинуть на столько же разрядов и получить те же 10 бит, как итог. А мы можем сдвинуть, например, на 2-3 разряда меньше и оставить, по сути, дополнительно 2-3 бита в результате, чтобы уменьшить несколько погрешность округления. Тоже вариант. Это вопрос реализации арифметики и оптимизации округлений. Это отдельный вопрос. Значит, смотрите, тут суть деконволюшна в чем? По отчетам на выходе АЦП делается обратная свертка. Она считается коэффициенты этого фильтра. Это обычный KIH-фильтр с умножением и задержкой. Поэтому получается, мы для расчета следующей точки мы берем результаты предыдущих расчетов.
А если сигналы немного плавают во времени, что начинаются они не всегда в одной точке?
Имеется в виду начало импульса.
Да.
Да, это естественно. Мы никогда не можем синхронизироваться на 100%. Это невозможно. Соответственно, смотрите, тут идеальный вариант. Если у нас отчет АЦП совпадает, выборка АЦП совпадает по времени с импульсом, то у нас на выходе фильтра теоретически должна быть одна палка, которая соответствует, вопрос пропорциональности, потому что там есть коэффициент передачи, и тут на рисунке они нормированные. На самом деле там значение числа будет другое, но это просто считается через коэффициент передачи. это можно нормировать, он фиксирован. Зависит от соотношения постоянных времен, частоты оцифровки, коэффициента передачи канала и так далее. Вот. Это идеальный случай, у нас тогда на выходе одна палка. Если же у нас импульс пришел между отчетами АЦП, то фактически получается как, что мы не можем сказать, что это был левый отчет или правый отчет. Это где-то между ними. Поэтому на выходе мы будем иметь две палки, то есть которые левее и правее сигнала. Они будут в пропорции делиться в зависимости от того, куда ближе. Вот.
Ну, если я их сложу, то я не получу. Всё равно.
Нет, почему? Складываете, получаете.
Ну, так по картинке не скажешь, по правой.
Так, ну тут, видимо, немножечко нарушена пропорциональность, чуть-чуть завышен второй. Вот. Но складываются отчеты, и получается, то есть просто общая амплитуда, она перераспределяется. Вот. Соответственно, это что-то наподобие спектра сигнала. У нас есть временная область, у нас есть частотный спектр, где для синуса у нас вот одна гармоника, одна палка. Да? Соответственно, получая синус, мы можем выяснить, какая гармоника была на входе. Вот. У нас только здесь импульсные характеристики. У нас есть импульс, и этому импульсу не в частотной, а во временной области соответствует отклик. Вот. Отклик, кстати, соответствует именно входному сигналу. Поскольку у нас именно дельта-импульс, то и на выходе фильтра мы должны получать дельта-импульсы.
Ну так, ладно, применительно к реальной физической задаче.
Если у нас импульсы накладываются, то у нас картина следующая. Вот с правой стороны у меня показаны два графика. Вот первый импульс видно, и второй точно такой же, наложенный на него. Той же амплитуды. Так вот, фильтр деконволюции, он дает реакцию на каждый импульс по отдельности. Он считает первый импульс и на него реагирует, дает палку. Но в данном случае левая картинка – это показ, когда у нас…
Sorry?
What exactly you cannot explain, I mean, dark matter or?
Okay. So you mean the model? The model is
Yes.
about dark sector. So the
So
physics.
dark matter.
Yes, basically, yeah,
Okay.
dark matter. Yeah. There is a dark sector, and there is only one particle in the dark sector that can talk to a standard model particle via kinetic mixing. There is no other portal with the standard model, and this dark photon can decay to 2 muons, and we are trying to look for dark photon whose mass is very small. So dimuon invariant mass is very small, and that's why, because of the trigger threshold, we couldn't do that.
And
So
which exactly small, what value do you mean?
yes, so in order to overcome the trigger threshold, what we did is the following. So the reason why we have these PT cuts in the trigger is that from LHC we are getting this very high rate of events of about 40 megahertz. And then in the first level of trigger, which is a hardware-based trigger, we call it level 1 trigger, it is reduced to 100 kilohertz. And then we have a software-based trigger, high-level trigger or HLT. There, the rate further reduced to 1 kilohertz. So 1 kilohertz of rate translates to a bandwidth of 1 Gbps, because the bandwidth is event rate times event size. And event size, for our case, the raw event size is 1 MB. So 1 kilohertz times 1 MB is the bandwidth. It's the threshold beyond which we cannot go. So now if we want to relax the PT cut on the muons, then we will be accepting much more event. So this 1 kilohertz number will be much more. So we need to reduce the event size a lot accordingly, so that the product of these two still remain very, very small. So that is what we did, and this is the idea of data scouting, that we increase the rate a lot by relaxing the PT cut at trigger level. But on the other hand, we save information only of those objects which we are going to use later in the analysis. And for normal triggers, we take the raw data and send it for offline reconstruction. Here we did not do that because it's a lot of data and it will take a lot of resource if we want to reconstruct it offline. So no raw data was saved. This way we save a lot of storage space, and no offline reconstruction was done. This way we save a lot of time, reconstruction time. So what we do is we use the muons that are reconstructed already at the trigger level, because our trigger level reconstruction is not too bad. It is very similar performance compared to offline. So, and you can see that in the plot, if I zoom in this plot a little bit. So this is a plot showing dimuon invariant mass, but these muons are reconstructed at the HLT level. And you can see that all the known resonances are very well seen in this plot, starting from Z, which is the highest one, and from very, very low mass one, eta, can be seen here. And so this is a trigger that we developed specifically for our analysis. And so we wanted to do the search in a very big range, actually. And this is what you see
But
here.
this trigger is prescaled.
No. It's taking all the events. It is unprescaled.
Unprescaled.
Yeah.
Okay.
So so this trigger was developed in the beginning of 2017. So we have missed the data of whole of 2016. That is what you see in this plot, that when we plot the dimuon invariant mass with standard triggers, it is 137 femtobarn inverse. And when we do the same plot with scouting triggers, it is only 96.6 femtobarn inverse. But even then, below 45 GeV or so, the standard triggers have very little event because of the we lose in acceptance because of the trigger threshold. And since the scouting trigger have very low PT threshold in trigger, so we gain a lot, almost several orders of magnitude more events was taken. And then we did the analysis in so basically it's the same analysis. One is done using scouting triggers up to 45 GeV, and another is done using standard triggers, which is from 45 to bigger mass values. And the analysis strategy was basically the same, except for the muon identification, we used slightly different muon identification for scouting, because all the quantities were HLT level quantities, whose performance was slightly different. The cuts were optimized accordingly. And using this,
You haven't found it.
we haven't found it. Yes,
Okay.
we place a very strong limit. Our limits are actually was the strongest. This black one is our limit, and we compare it with LHCb limit. And at the very low masses, we are competitive with them. Not always better than them, but very, very similar. And as we go higher in masses, we do better, of course. But yeah.
What is the biggest deviation?
The biggest deviation was about, I think, this point here. It was never crossing 2.5 sigma. So mostly these ups and downs that you see, they are within 2 sigma band, but some of them reached like 2.1 or 2.2, but they all look like local ups and downs. So we also had this plot separated by years. So only 2017, only 2018, and then we combined. None of the excesses looked like they were present in both years. So they were totally uncorrelated, and the excesses were not increasing by adding more data. So that's why we think they are just statistical fluctuations.
Yeah, I think so.
And then we also provide a model independent limit where we just see the cross section times branching times acceptance in the y-axis, so that if theoreticians are interested to translate it to their model, so they can do that.
Okay, interesting study, and this study of the trigger. Yeah, good.
Atlas also have this trigger. I mean, Atlas also have this similar trigger level analysis, but I think you have it in the jets only, not in the muons. But I'm fairly easily you can also do it for muons, I guess.
Yes, I think so. Because I'm working in the multi bosons, so I'm not interested in such low energy triggers.
Mm-hmm. What are you
I'm
working
working
on?
with high energy. Yeah.
You are working on high energy objects.
Yeah,
Okay.
yes, I'm working for in the search of VDS processes
I
like
see.
the ZZ or the gamma electric.
Oh, that's very interesting. Do you have a talk in this conference?
No, my students have several posters.
Oh, okay. That's nice.
Yeah, but they are mostly about some methodologies and about some phenomenology also. So we don't have some kind of official results, but we have some results around our studies in Atlas.
Okay, yeah, I mean, getting things approved from CMS and Atlas is really a painful thing.
Yeah. But phenomenology always possible to publish some phenomenology. Maybe, for example, in your study, you can use your limits and like translate it into the terms of some models. You can try to constrain some models. It is possible, but it is something between the theory and experimental work.
Yeah, sure. Yeah, that sounds
It is
interesting.
publishable.
Yeah, right. Yeah, we can think about that actually. After this got published beginning this year, I moved to something else. But yeah, you are right. I should also try to do something more with the limits.
Yeah, it is possible, and it's really important if, for example, if it isn't, if you need some more papers, maybe if you need to put some acknowledgement for your grant, because we in Russia needed our grant. Our grant programs, they want us to put some acknowledgement, and we cannot put an acknowledgement to Atlas or CMS paper. Like to the personal grant, it is not possible. So yeah, we are trying to do it like this, to have separate papers and to put acknowledgements to grant.
Yes, indeed. Because this is also one problem I'm facing with. I'm now looking for jobs, like permanent jobs, because I am a postdoc now, and people often ask me that, okay, you are saying that you have written CMS papers, but the CMS paper have 3,000 authors. So
Yes.
how do I believe that it's you who contributed?
Yeah, it is also true for Russia and even for our authorities, for even in the scientific community. Sometimes when I'm writing the grant application and then the reviewer writes me like, okay, uh, I will not give you money because I'm not sure that you have done this, and I'm not sure that it will not be done without you,
Yeah.
like this.
Yes, this is a common problem everybody is facing, really. This sucks.
Okay, thank you. Very interesting study.
Thank you very much. I really had a nice time talking to you. Thank you.
Okay, bye.
Bye.
यूट्यूब स्ट्रीम हो रहा है ये अभी तुम्हारे से ना?
यस सर।
अच्छा तुम एक बार बता दो मुझे, एक बार डिस्कस कर लो।
You use some source light?
Yes,
or
we use
radioactive source.
Yeah, we use the Takal as some calibration systems, and so we use two of them to isolate.
First slide.
Sorry.
I didn't see first slides. I didn't.
Yeah.
So you use cesium and also
the laser light. Yeah.
So and you for that plot you use laser light or
for
cesium?
this, so basically you have the cesium source that this calibrates the tiles and the fibers and the photomultiplier tube, and the laser is responsible for calibrate the photomultiplier, and by subtracting the response of the laser to the cesium source, you can isolate the optical part of the Takal. So the optical part is the tiles and the fibers, and this is what I mean by this part here in this equation. So I use these two systems to isolate the optics and to calculate this relative light yield.
Okay, thank you. Yeah,
I don't know if you want, I can try to explain a little bit better.
Yes, I understood.
Okay.
Thank you.
Okay. And
What about these plots here on figure 6 with this yellow?
Не, у меня тоже только грузится.
Что я могу с этим сделать?
Я могу попробовать постримить. Загрузилось.
Угу. Я уменьшил частоту, может быть, но там все равно ничего не происходит. Хорошо, в общем, FHCAL – это калориметр, который мы разрабатываем в лаборатории в Троицке, в ИЯИ. Устанавливается на несколько экспериментов, включая NPD в Дубне. Вот. Уже сейчас он в каком-то виде установлен, собран на эксперименте BMN в Дубне. Установлены все модули калориметра и электроника для съема сигнала, и фронтенд электроника, и встал вопрос об управлении, для чего мы разрабатываем систему DCS или Slow Control. У нас была система, которая использовалась раньше у нас в лаборатории или в ЦЕРНе на NH61 на аналогичной калориметре. Но сейчас встает вопрос ее производительности, потому что на MPD, в частности, будет больше каналов, больше модулей калориметра, 2 калориметра, разнесенных под управлением 2 системных модулей. И поэтому нужно эффективно с ними взаимодействовать, потому что иначе простой опрос всех параметров, всех модулей затягивается на несколько минут. Это не очень удобно в работе, если приходится это перезапускать или... В общем, узкое место в самой этой DCS-системе – это физическая линия от системного модуля к электронике. Она выполнена в виде шины RS-485, по ней идут команды запрос и ответ определенных параметров установки, включая заданное высокое напряжение, какие-то коды ошибок, состояние температуры. Система DCS должна считывать эти параметры и, например, с характерным временем в секунды реагировать на ошибки или с временем вроде минут выдавать команды температурной коррекции, потому что считывание через силикон PM очень чувствительно к температуре. У них меняется гейн. Соответственно, разрабатывается новая система DCS, которая в перспективе также должна быть включена в DCS всего эксперимента или прозрачно предоставлять данные с электроники или в будущем как-то более умно их себе сохранять и публиковать. Значит, эта задача решается с помощью программного обеспечения на питоне. По количеству системных модулей есть несколько очередей команд. Для 2 системных модулей, соответственно, будет 2 очереди. Методом проб и ошибок определено, насколько быстро шина может эти команды переваривать. В постере есть табличка. И, в общем, мы надеемся в несколько раз поднять утилизацию этой шины обмена. Таким образом, в несколько раз быстрее передавать эти команды. И это еще можно умножать на 2 по количеству системных модулей. В общем, смысл работы в разработке такого программного обеспечения для управления калориметром.
А в триггере не планируется как-то использовать FHCAL?
Для MPD, опять же, не могу ответить на этот вопрос. По опыту эксперимента на 61 передний калориметр, там он под названием PSD, Project Aspect.
Of interest. And if we look especially for the eta mesons, then what we are going to, or we are studying at present, that eta mesons optical potential that can be used basically to study the eta meson bond states with the nuclei.
Okay, I see. And what will be the next step in your study?
Actually, in this, what we are showing here so far, what we have done, we used we used some earlier work of one group where they have used the chiral perturbation theory and some relativistic model to calculate it.
Can you explain what means multi-phase transport model?
So actually, it is a heavy ion collision model. In this, we set all the initial conditions for a collision. For example, we set the particle like a gold collision we are doing, or whatever we want to collide. Then we set everything, whatever conditions are required, and then we get the output, which we analyze in form, like we get the output as coordinates, time coordinate, mass, and px, py, pz coordinates, which are analyzed further to get the experimental observation.
Thank you.
Hello?
Yeah, I hear you. Thank you. And what's the main idea of your work?
So my main idea of my work is to study the rapidity distribution with and without mean field potential. So basically, in the AMPT model, we don't the original model. It doesn't include the mean field potential from chiral model. Okay, so it included the potential from chiral perturbation theory. I changed the the input of the AMPT model by giving the potential which is in the chiral SU3 model. So I connected the theory with the experiment in this way. For self-interaction term is written. Using the expression in the dispersion relation, I calculated the energy. That energy is given as an input in the AMPT model. Okay, with that we study what will be the changes in the rapidity distribution in the mean field and without mean field. So what we observe is, without mean field, in the mid rapidity regions, we have a k plus by k minus ratio, which is higher. But when we have a field, we see a drop in the rapidity in the k plus by k minus production ratio. This is due to the potential, the energy of the kaons reduces. And mass of kaons is modified in the presence of mean field.
Okay. Well, it's very interesting work, I think.
Sir, I can't hear you clearly.
What?
Sir, I can't get you clear.
Ну и также для минус на третья. И, графики кингов имеют такой вот вид. Это у нас черно-синяя для вот этих топологических секторов. Ну и минус на третья для... Ну, это красное относится к минус на третьей. Вот. Только тут важно, что тут, как ты можешь заметить, такой для красного одна часть выражается таким образом, другая часть выражается таким образом. В случае x больше нуля и в случае x меньше нуля. В x равно нулю она не определена, но легко находится ее предел. И, по сути, зависимость такая гладкая получается. Вот. Это, основное. Также тут рассматривается асимптотика при стремлении n к бесконечности, для всех решений таких вот. И, вот она показана. В случае других секторов она 1 делить на n1, минус 1 делить на n и минус 1, он симметричный будет ему.
Okay. Have a good time. Yeah, thank you, Alexei. Bye. Hi, Lumonishi. Sorry if I... Andre.
Степенную зависимость, в сути. Сейчас я как Parallel asymptotics. Parallel asymptotic. Yeah. Вот. И по сути это все.
А для чего вот эти ваши расчеты, где их применяют? В какой теории? Что за теория? К чему она?
Это теория полей. Сейчас, кстати. Сейчас я... Секунду.
Да, я не тороплюсь. У меня еще целых 40 минут.
Я понимаю. Мне надо подумать. Это... Секунду, я сейчас скажу. Это... Блин. Сейчас. По сути, это...
Калш типами.
Quality control электромагнитных калориметров. Такое. 772. Кто-то есть в 772? Да, там есть человек.
Площадей нормированных сигналов ворота гейт 2. Значение у нас фон получается.
Я просто смотрю, у кого какие постеры.
Может, тебе рассказать? Или так, или что?
Давай, послушай, интересно.
Давай. В общем, тема была это аналитическое приближение функции распределения нейтрино в сверхновой с коллапсом центральной части. Сверхновая с коллапсом центральной части уже достаточно долгое время является частью современной астрофизики. И как, наверное, известно, ну, а может и неизвестно всем, то моделирование взрыва сверхновых продвинулось достаточно давно, но ответа на успешность взрыва нет еще пока что. Но достаточно хорошо известно, что нейтринное излучение играет достаточно важную роль в данном процессе. Кроме моделей сверхновых с коллапсом центральной части, где важную роль играет нейтринное излучение, есть также магниторационные модели взрыва сверхновой, где важную роль играет генерация сильного магнитного поля. Ну, возможно, даже в тех моделях нейтринное излучение играет достаточно важную роль. Так как среда сверхновой для нейтринного излучения, она, возможно, даже лишь частично прозрачна, то уравнение переноса должно решаться совместно с гидродинамикой, и это достаточно сложно, поэтому его можно решить только численно. А результаты, которые получаются при моделировании, да, численные, их достаточно сложно использовать в каких-то других задачах. Одной из важных таких частей описания нейтринного излучения является их одночастичная функция распределения. Если знать эту функцию распределения, мы можем оценить влияние нейтринного излучения, точнее взаимодействие нейтринного излучения с материей сверхновой и оценить их вклад в динамику взрыва. Это, например, одна из задач, но еще есть множество других. Да? Поэтому нам важно знать приближение для функции распределения нейтрино непосредственно в сверхновой, чтобы оценивать какие-то процессы, как она там взаимодействует с материей. Вот, в принципе, поэтому мы использовали одну статью, где есть аналитическое приближение, и оцифровали оттуда данные. У нас не было доступа к численному моделированию, к данным численного моделирования, поэтому мы оцифровали данные и использовали приближение, полученное там. Нам удалось его проанализировать, и в случае для того, чтобы перейти к мы перешли к более удобной переменной y, проанализировали и получили, что вот данные численного моделирования могли бы приближаться вот такой функцией. Это показано, кстати, на графике. Вот у нас получается G-дата — это оцифрованные данные статьи, а f от ry — это наш кандидат на функцию приближения. Это показано, кстати, на графике. На функцию, ну да, функцию приближения, или другими словами, на функцию распределения, функцию углового распределения нейтрино. И дальше мы оценили вклад данной функции в сравнении с функцией GRY, что было представлено в статье. Мы вклад относительный, оценивали в терминах локальной концентрации нейтрино, где NG — это интеграл пропорциональный, взятый от функции GY по DY, а NφO — это интеграл, взятый от функции φ от RY, то есть от нашего приближения, которое было найдено. И получилось, что наше приближение может описывать порядка 90% нейтринов сверхновой. Вот. Помимо этого у нас получилось найти параметр AR, но получилось найти значение, точнее, вот приблизить его законом только для приближения, да, а для численных данных у нас не получилось подобрать что-то хорошее, потому что было достаточно мало значений, только для 4 R. Приближение, да, а для можем сказать только приближенно, что может описываться квадратичным законом. Потому что было достаточно мало значений, только для 4 R. Ну и, в принципе, в результате мы можем сказать, что наша функция распределения поможет, более-менее может быть использована в оценке, да, нейтринных процессов и описывать их более 90%. Ну, точнее, да, тут я немножко запуталась, неправильно сказала. Наверное, надо будет сказать, что наши функции распределения можно описать более 90% нейтрино в сверхновой. Ну, это относительно углового распределения. Да. Вот так вот. Ну, наверное, тут не вся информация на постере представлена. Вот. Поэтому не очень получилось.
Acquire or veto B-jets because some of the models produce B-jets and some of them don't. And so when you require or veto them, it improves the sensitivity. Our backgrounds are estimated. The standard model backgrounds are estimated by Monte Carlo, and we normalize this to data. And then we have these reducible backgrounds, which are due to objects that are misidentified. We call these fake leptons.
You means use real-time data from Atlas, or you are doing simulation kind of thing?
So we use data that has already been collected between 2015 and 2018, and we also use Monte Carlo simulation.
Okay.
So, in this plot here on the right, for example, looking at the first bin, the first column. Here in this region, we require at least 4 leptons, and then we require where the leptons are consistent with 2 Z bosons, and then also we have a loose requirement on missing energy. So you see so in the histogram, the solid colors is the background estimation, so it's mostly Monte Carlo, and then the black dots are the number of events that we've collected in the in the data, which corresponds to this energy and this amount of data. So it's mostly Monte Carlo, and then the black dots.
Okay. Okay, Gabriel, thank you.
Sure. Thanks for your time. Enjoy the conference.
But
Please.
Can you conclude all your?
So, this search in particular, we were searching for this specific model in either 3 leptons in the final state, and by leptons means just electrons or muons, or 2 leptons in the final state, in which these 2 leptons are of the same electrical charge. And this because there is a specific phase space and specific models that we are trying to target with them. So far, for the recently published results, no, in the region of the phase space we are observing, no excess with respect to the standard model has been observed, which means that we are able to test the standard model in that specific phase space, which is very reasonable. So our knowledge even on the standard model itself may not be as precise. And therefore, we set limits on the masses of these particles. In the top plots, you see for the 3 leptons models, and the bottom one for the 2 leptons same sign.
Okay.
Yeah. If you want more details about how these analysis, the search is performed, I can talk about this.
Okay.
So, yeah.
So you have plotted this comparison of observed data in the experiment SM background. Okay.
Right. So in these plots, for instance, for the 3 lepton analysis, in these 2 top plots here, we see many different search regions which are being specifically designed to target for this signal model. And the colored stack plots represent the standard model processes which may contribute to such process. So this is our expectation for the standard model. The black dots represent the data that we measure, the data yields that we measure in this region, whereas the dashed lines represent the signal that we're trying to search for. As you can see from the bottom part of these histograms, which represents the significance in terms of number of sigma of data, how much data is distant from the standard model prediction, we see that all of the data are within 2 sigmas of the standard model prediction. And therefore, we cannot claim even to have observed an excess because the convention is 3 sigma.
Yes. Oh, what about the, are you studying this, any particular drawbacks of standard model or just?
Any particular drawbacks, you say?
Standard model, yeah.
So our main objective is to search for this specific supersymmetric models. But while searching for them, you usually go and search in specific regions of the phase space for which even our knowledge of the standard model is not that well precise. And this gives us also a way of testing whether or not the standard model prediction power is suitable or not. For instance, if we see an excess, how much we quantify that excess, how much our knowledge, how much our expectation is different compared to data. This is actually true, for instance, in the last 2 bins of the plots that I've just shown you. The plot on the right, which are called DFOS, signal region DFOS 1 and 2, for which we see an excess of about 2 sigma. And the reason for that is that in these particular regions, a standard model process is dominant, is actually quite significant, and we don't know much about it. And this is actually the triboson production. So a standard model process where we produce 3 W or Z bosons and the decay into a final state with 3 leptons. This is actually a result that's been recently been mentioned this morning in the standard model results for MATLAS and CMS. The point is that the Monte Carlo and prediction regarding this standard model process is not well known yet, and therefore we cannot make exact predictions regarding this specific process, especially in bins where this process is dominant or subdominant. Therefore, we have highlighted in this particular phase space this triboson process has a mismodeling in our current Monte Carlo knowledge, and we can improve on top of that. So it's never a losing game. It's always something that helps us test our knowledge of the theory, the standard model, and in the meantime search for a new theory, an extension of the standard model that could also solve some of the problems that the standard model limitation that the standard model has.
Yes. Okay, that's fine. Can I ask you about one other question? What does supersymmetry says about why there is a negative charge for each positive charge? Why there is a charge conservation? Related to your,
Well,
if you want to, say a few comments.
where there is this supersymmetric correspondence between fermions and bosons. So there are some phenomenological consequences about the charges of the particles in the final state that we're looking for, but the main correspondence happen within fermions and bosons. So there may be some theoretical constraints about the charges of the particles in the final state, but there's not an actual a priori assumption. And it depends, again, on the specific supersymmetric models that you are taking into consideration.
Okay.
In this case, we are considering a supersymmetric model, which is called minimal supersymmetric standard model, whereas we introduce as least particle state that we can possibly have in order to have this new symmetry being conserved. So the symmetry between fermions and bosons. I hope this answers your question. Unfortunately, I'm not a theorist, so I'm not in.
No, you explained very well. Thank you. Okay, thank you, Marco.
Thank you so much. Hello, there's plenty of people here. So if any of you have any questions, please go ahead.
And maybe can you repeat your talk again, please? For new here.
Right. I'll just give an overview of what this search is about. So I'm focusing on the search for supersymmetry.
Более сложные модели пытаемся применить к 2HDM. Вот. Ну и на этом, мне кажется, вот, ну, пока будет закончено, продемонстрирована, собственно, методика.
Понятно. А еще раз можно вот про графики? Просто не очень понятно, что эти линии значат. Это результаты чего еще раз?
Ну вот.
И там просто не видно, да, вот что.
Сейчас покажу. Да, ну вот мы можем посчитать, собственно, выражение вот этих самых EFT-каплингов E4 и F5. Для стандартной модели мы можем это посчитать. Ну, это просто мы вот эти вот диаграммы, ну, учитываем только лагранжан взаимодействия в стандартной модели. И все. И вот здесь приведены как бы амплитуды, это же такие комплексные штуки. Вот. Ну и каплинги, соответственно, это тоже такие комплексные штуки. И вот здесь приведена зелененькая линия, это полный вклад стандартной модели, то, как это в стандартной модели без расширения реализуется, именно ее действительная часть. А вот это вот красная, это ее комплексная часть. Ну и аналогично для вклада чарджина, то есть какой вклад сюда внесут именно вот эти вот новые частицы наши. Ну это вот реализовано для распада гамма в z-гамма, z-z-гамма и гамма в z-z. Мы просто это все посчитали, выразили через лямбда. Вот если выразить это через лямбду, мы просто получим вот такие вот распределения. Ну и все, собственно. Тут, не знаю, понятно объяснил?
Да, ты можешь правее показать их?
А там, в смысле, правее?
Ну вот, там просто только левая часть этих квадратов была показана. Понимаю, что это для разных каплингов. Просто, то есть вы смотрите как раз-таки отклонение от значений вот посчитанных, так?
Ну, нас на самом деле интересует вот суммарный вклад, да, то он, в принципе, насколько он это будет отклоняться от стандартной модели, но вот тут мы как бы, ну, представляем вот метод того, как отсюда можно параметры вот этого расширения стандартной модели ограничить. Ну, пока не получается точности коллайдера, еще немножко нужно. Тогда можно будет.
Почему именно в этих каналах это как-то смотрится вот для MSSM-модели? Или не только в этих вот похожие вещи рассматриваются?
Ну, можно и другие, в принципе, каплинги рассматривать. Мы взяли такие, для которых ограничения сейчас хорошие получены просто.
То есть у них просто адекватные ограничения уже есть. Понятно.
Ну и все. Ну вот для там другой модели, которую мы сейчас тоже рассматриваем, это там модель с двумя хексами, 2 HDM, там есть надежда, что на самом деле может быть там при определенных значениях параметров вот этой вот теории, может быть там некоторые ограничения, то есть можно поставить будет, вот при некоторую область отсечь. Таким способом.
То есть 2 вырожденных хекса вот в этом расширении или...
Да. Ну, по сути, да.
А они какие по, там, не знаю, по массам и так далее? Просто не очень вообще с этим
А,
знаком.
Ну, там их массы связаны, как бы, там есть отдельно, собственно, у них вакуумные средние, там V1 и V2, и вот есть связь этих вакуумных средних, одно с другим связано через там фермерскую константу, вот, и масса одного там более тяжелого хекса, она тоже связана с массой более легкого хекса, как там, по-моему, если не путаю, корень из m более легкого в квадрате плюс v1 в квадрате. Если не перепутал, вот примерно вот так вот. Ну, то есть они там связаны их массы, то есть однозначно как бы они не померены, просто известна связь между их массами и все. Ну, как бы, если бы они были померены, то ну, второй хиггс бы нашли просто. Ну вот.
Понятно. А дальше вы, то есть, просто будете ждать новые данные или, типа, что вы в этом направлении будете что-то еще смотреть и, не знаю...
Я же сейчас немножко в другое направление ушел. Ну, я вот, наверное, лично я буду дальше немножко другим заниматься.
Понятно.
Закончим эту работу. А Евгений Юрьевич и Никита, они, я думаю, да, будут дальше продолжать.
Понятно. Ты сейчас чем-то там двумерными вихрями
Да.
занимаешься вроде. Понятно. Это ты в аспирантуре где-то или это просто сменил научника?
Ну, да, я в Скалтехе. Ну, и сменил научника.
Ну, понятно. Ясно. А почему ты так решил? Или, ну, типа, предложили поработать, было интересно, согласился? Или давно хотел?
Я долго думал вообще, чем мне дальше заниматься. Тут YouTube стрим, правда. Я про свои жизненные проблемы начну. Ну, на самом
Можешь потом ответить.
Давай потом.
Окей.
Немножко.
Если есть уравнение Больцмана кинетическое, то в правой части у него стоит интеграл столкновений, и приближение Фоккера-Планка состоит в том, что учитываются только взаимодействия, которые там изменяют скорости на маленькие значения. И там этот интеграл столкновения очень неплохо упрощается, что позволяет его посчитать. Собственно, весь подход.
Мгм. Ну, а результаты какие?
Ну, результаты такие, что кластер со временем расширяется. Вот здесь можно посмотреть на профиль плотности. Синяя – это в начальный момент времени. Но он на r в квадрате домножим, потому что так лучше видно. Вот. И тут есть крестики, которые соответствуют радиусам, содержащим какое-то количество процентов массы. Ну, самый левый – это 1%, 10, 50. Видно курсор? Я не знаю.
Да, видно.
И вот это 90%. Вот, и видно, что если он изначально 90% массы держит под одним парсеком, то к конечному моменту времени это все переходит в, ну, где-то 10 парсеков. Тут не видно засечки, но она вот есть на зеленой, по-моему. Вот такие дела. Ну и там устанавливается очень широкий изотермический слой, по всей видимости. Вот тут нужно умозрительно провести прямую, ну просто прямую без наклона. Вот если тут провести прямую без наклона, то это зависимость r-2. Я надеюсь, понятно, да, из построения, что это так?
Я думаю, да. Я просто, смотри, у тебя увеличивается радиус, а плотность, умноженная на r квадрат, остается постоянной. То есть плотность падает, что ли? Вот получается, что
Плотность,
раз радиус увеличивается,
плотность падает в центре, кластер расширяется. Интеграл под плотностью сохраняется. То есть масса
то есть
полная сохраняется, именно сам кластер, он увеличивается в размерах, и поэтому плотность и падает.
со временем, да?
Ну
Как
да.
R. А в конце они так достаточно резко. А сначала они растут, причем, да, потом выходят на константу, а потом резко падают.
Ну да.
Но при этом размер кластера увеличивается не... Хотя это логарифм, конечно. Шкала
Но размер
логарифмическая.
кластера в 10 раз увеличивается. Он был изначально парсек, стал 10.
Да, а плотность упала, соответственно, в 100 раз, да? Или даже в 10 тысяч раз.
В центральной области, ну да, чуть больше 1000.
Не странно это, нет? То, что...
Нет, это не странно.
То, что если в 10 раз увеличился радиус, а плотность упала в 10 тысяч раз, а не в 1000 раз.
А почему это должно быть странно?
Ну, не как r в кубе, а получилось как r в четвертой.
R в четвертой?
Ну, в 10 тысяч раз. А здесь...
ну так профиль плотности уже изменился. Но вот тут, если, как вы рассуждаете, имеет смысл сравнивать только красную и фиолетовую, потому что они более-менее похожи. И тут и будет, что в 100 раз. Ну, красная — это на 1 миллион на 1 миллион лет. Там просто в центральной области есть центральная черная дыра, и вблизи центра процессы очень быстро идут, потому что, во-первых, черная дыра в центре, она легкая, и вокруг тоже болтыхается очень маленькая, и там устанавливается стационарная зависимость для профиля плотности, которая r в степени минус 7/4. Это стационарное решение уравнений. Если выключить любые потенциалы гравитационные от распределения черных дыр, оставить только центральную черную дыру, которая создает потенциал единицы на r, то будет стационарное решение r в степени минус 7/4.
А вот расти она начинает в определенный момент не для...
Что?
Сейчас, нет, я пытаюсь сообразить. Просто графики, которые представлены, имеют некоторую третью ось, связанную с годами, которые написаны в подписи. Я пытаюсь сообразить, как оно эволюционировало.
Я могу просто показать зависимость радиуса, который содержит какое-то количество массы от времени. И там
Давай.
будет видно, кто как эволюционирует.
Давай.
Это радиус, содержащий 50% массы для разных типов черных дыр.
Мгм.
Вот. Ну, тяжелые сжимаются вначале за счет динамического трения, а легкие, рассеиваются на тяжелых, разлетаются, и в конечном итоге все выходят на одинаковую зависимость в степени 2/3.
Ну, то есть, как и должно быть.
Ну да.
А кто у нас в гостях?
Ну, видимо, я, Радик и Владимир М. Я не знаю, правда, кто это, извините.
Ну,
можешь,
то есть
пожалуйста,
опять
показать
ты
свой
свой.
плакат? Да.
Плакат
Покажите,
висит.
пожалуйста, да. Его, нет, его еще, вот сейчас. Да, хорошо. Вот. Я так понял, нас неожиданно посетили.
К нам еще кто-то зашел?
В интернет нас вещают в прямом эфире.
Нас вещают в прямом эфире?
Да.
Ну,
Я
давайте
думаю,
что-нибудь
для
скажем.
вновь пришедших можно вкратце ввести всех в курс дела, о чем это вообще.
Если нас вещают, то на каком языке ты
Тут
лучше?
вновь пришедшие некоторые товарищи в курсе, о чем это. Если
Подожди, к нам
Владимир,
прямой эфир
просто
подключился.
я тоже соавтор этой работы, да.
Владимир Владимирович, там говорят, что к нам прямой эфир
Здравствуйте.
подключился.
А вот,
Можно на прямой эфир
да.
поговорить.
Просто зашел на минутку узнать, как там у вас обсуждение, если там есть какие-то вопросы или нет.
Ну, на прямой эфир мы будем что-нибудь говорить?
Ну, вообще, один какой-то вопрос есть. Можно вернуть, пожалуйста, обратно? Вот про вот это вот как раз в левом нижнем углу, про систему антисовпадений, да?
И что ты хочешь услышать?
Как она вообще работает?
А поконкретнее вопрос можно?
Ну вот, как бы сказать, вот вот у нас есть событие протон попадаешь и событие, когда гамма-частица попадает в детектор. Вот, когда попадает протон, то видно, что вот эти вот АЦ-элементы срабатывают. Вот. Ты, получается, говорила, что это система антисовпадений, да?
Мгм.
Как получается, вот она вообще работает, не совсем понял.
Ну вот, видишь, она в прямоугольничках, да?
Прямоугольничек, да. Что это из себя представляет? Ну,
В
элементы.
смысле, что она из себя представляет?
Ну да, в чем это как реализовано?
А, Владимир Владимирович, вы тут? Ой, честно, я не очень помню полный состав.
Я, вроде говоря, не слышу ответов и не вижу презентации. Здесь у меня что-то не совсем
Ну,
правильно.
там спросили, что собой представляет
Вот это.
антисовпадательная защита. Из чего она состоит? Которая наверху. AS top и AS left. Ну, по принципу работы, что заряженные частицы, в них остается отметка, а у незаряженных, ну, в общем, как мы видим, отметок не остается. Молчание. Ну ладно, также тут видно выделение, раз уж нас камера снимает, давайте скажу еще что-нибудь. Также тут видно, что...
Я не знаю, вы меня слышите или что?
Слышим,
Просто что-то
слышим.
тут
Да, вас слышно.
не совсем непонятно. Это был вопрос или
Это был
что?
вопрос, да.
Это
Про
вопрос был насчет
антисовпадательную защиту.
антисовпадений. Ко мне
Да,
или
это
к Анне?
у меня вопрос.
К нам.
Ну, здесь антисовпадение – это просто станциляционный счетчик. Там заряженная частица в станциляционном счетчике оставляет сигнал обязательно, след оставляет заряженная частица. Помните ядерную
Да.
E
физику? dE по dx, там всегда формула Бёте-Блоха, 2 МВ на грамм. Любой протон должен там дать сигнал. А толщина этого детектора примерно 2 грамма. 2 грамма на сантиметр квадратный. Поэтому все заряженные частицы, они там отмечаются.
То
А
есть...
гамма-квант, он, соответственно, не проходит без взаимодействия 2 грамма. Длина, если помните, какая радиационная длина-то в пластике?
Ой, не совсем, если
Из
честно.
ядерной физики. Примерно 40 грамм. Это такая величина, в которую полезно помнить всем физикам. Сейчас я, секундочку, да. В общем, это вот 40 грамм, поэтому там практически гамма-кванты не взаимодействуют с осциллятором. А вот толщина у него там 2 грамма. Поэтому вот такие гамма-кванты.
Now, let's talk about signal processing. A charged particle flying at the surface of the scintillation counter interacts with the electromagnetic fields of atomic nuclei, experiences radiation losses, emitting photons that interact with the molecules of the inorganic scintillator. Then, when excited state molecules return to the ground state emitting photons, in the blue and ultraviolet range, the charged particle energy loss is proportional to the capacitor charge, which is located after the shaper. So, therefore, scintillation detector developed by us can be used as a spectrometer. The results of the beam monitor detectors calibration on the synchrotron program showed that such detectors are suitable for recording the time resolution profiles of electron fluxes called in TGF. As you can see, the results of these calibrations are presented below. So figure 4 shows us signals distribution from the beam monitor. Results of the beam monitor separate detector calibration on the Bahra's synchrotron. So further, figure 5 describes the results of the beam monitor detector time resolution measurements for one electron bunch, and figure 6 describes as a signals distribution from the channel 2 from the beam monitor by time resolution measurements. Also, the next stages of our work was to simplify and reduce the cost of the development because we are trying to make a satellite probe which will detect events about TGF on low orbits or in the stratosphere. We have two configurations. And to simplify and reduce the cost of the development, we used a single board computer BeagleBone Black based on the system-on-chip AM3358 Citara processor and the Kubus framework for software development. In addition to the framework itself, a custom Linux system is used. This light software framework for satellites provides the ability to work with sensors and other equipment through already written IPs that allow us to concentrate on writing scripts and programs for data processing. So, as you can see, the pipeline we are using is presented in figure 8. You can see GitLab CI/CD pipeline, continuous integration, continuous deploy here. So, this scheme implements the possibility of a simple update in a couple of commands. We're trying to show that Odin develops practices and tools such as GitLab, Ansible, molecular unit tests will increase the efficiency, and by doing this, we will be able to write the correctly working code as efficiently and as quickly as possible. So, further, we developed a conceptual design of the CubeSat format probe structure. As you can see on the figure 9, it consists, the body of the devices consists of 2 frames, some kind of a dual frame system. So, shock-resistant outer frame and inner frame. This design was created to protect electronics from extreme conditions during a stratospheric balloon launch and from stress at the subsequent landing. So, during the development, this design also helps us to use it in various configurations of the satellites because this dual system is give the opportunity to place shielding or solar panels between them, and this will make it easier to use various configurations. So, to sum up, during the development of our project, or during the development of the CubeSat format probe, we prepared the scintillation detector. Also, furthermore, we are trying to furthermore, sorry. In this project, we presented the detector prototype for a CubeSat application, and as well as development and also conceptual design of the probe, as I said before. So we are trying to use DevOps practices and to integrate it in the software development. Also, we make we make various tests on that synchrotron, and it was shown that the detector similar to beam monitor detectors used in the calibrations of gamma M400 telescope will be successfully used for detect the electron fluxes, which presumably are the sources of TGF. Also, we consider the possibility of adding cesium iodide activated barium crystal, bismuth orthogermanate crystal to the project. Doing this will help us to detect not only electron fluxes causing TGF, but the radiation from the TGF itself. So also, there are several stages of the further development. We need to finalize the hardware platform, test the prototype in laboratory conditions, create an inertial navigation system for the probe, optimize the software, and make the final test launch to the stratosphere, and further a standard sample of the device for function on low orbits. So I'd like to finish with a few words about my project. The phenomenon studied in this project is not fully understood yet, and the results of the project can be of interest to the high current electronics and will help to correct the results of the experiments. So that's all. Thank you very much for your attendance. If you have any questions, I'm happy to answer them.
Ну да, в принципе, у меня есть один вопрос. А зачем это все нужно?
Oh, so shall I answer in English or in Russian?
Должна на русском. Я не принципиально.
Хорошо. Сама цель нашей работы — это создать образец устройства, которое будет давать возможность регистрировать такое явление, как TGF. Я говорила об этом в самом начале работы, и явление это новое и до сих пор пока что не до конца изучено, не зная его природы. Есть только предположительные догадки об его происхождении. Но было доказано то, что оно возникает в слоях атмосферы, где то, что возникновение этого явления влияет на результаты других экспериментов. Поэтому
А в каких слоях атмосферы?
Около 30 километров. Я ссылаюсь на работы авторов. В конце моей работы есть список литературы. Если интересно, вы можете ознакомиться с ним. В данной работе я представляю концепт устройства, которое поможет изучить это явление, получить больше данных о нем. Мы представили детектор и, протестировав его на синхротроне Бахра, выявили, что данный детектор может использоваться для регистрации потоков электронов, вызывающих TGF, Terrestrial Gamma Ray Flash, данное явление. Вот. Сейчас много различных экспериментов с ним проходят, так что мы попытались сделать, возможно, что-то новое, попробовать создать устройство.
Понятно, спасибо.
Вам спасибо. So, hello, everyone. Good evening, and welcome to my presentation. First of all, let me thank you for coming here today. And my name is Tatiana Kurmasheva. Shall I start? Oh, okay. So, as you can see, one second. As you can see on the poster, today I will talk about my project. So let's begin. Nowadays, most of the satellite data is obtained on low orbits. The formation of
Потому что
Приложение, честно говоря... О,
Так, наш конфиденциально снаружи. Тут стримы. Так. Сейчас мне нужно отлучиться, пообщаться с Алексеем.
E pronto. E
YouTube stream So what are you doing in this particular? I can see your uh, graphs here. Can you zoom this?
Yes, sir. Please wait a minute, sir. Sir, is it okay now?
No, can you please zoom it more? Okay. So by which method you have plotted these bars and all? Is it from the MATLAB plot or what?
No, sir. This is basically from the root. In this, what I have done is I took the AMPT data and I manipulated all the data using root.
Okay.
So basically,
So-
these bars denote the error in our calculation. This is automatically done by root.
Okay, what kind of error you are considering in your calculations?
Error, sir, basically the error we calculate delta x in any quantity, whatever error we get. You know.
Yes. Okay. So how can you conclude your work?
Sir, in conclusion, my work is based on means studying the rapidity distribution with and without potential of kaons and anti-kaons. So we have included the potential from the chiral SU3 model in our AMPT model. With that, we have studied what are the rapidity distributions without and with potential. Here we can see clearly when the potential is included, the blue ones, the blue graph, in the mid rapidity region,